Coffee break. Then we're going to have in the second block of the day the generative models talk by Ruben Villegas and two spotlight talks by Jose Ochoa and Germán Mato. Then lunch, and after that we're going to have the GNN's talk by Ari Ribeiro and the sponsors talks by Cohere, Hilda, and Asap. And then the Graph Neural Networks talk 2 by Gonchi Mateos. And followed by the sponsor talks by Ajesic, Trio Labs, Quanam, and then we're going to have the practicals on the many different topics, but in particular forecasting, GNNs, and ML technologies and data governance. And then, today is going to be the longest day of all. We're going to have like a little 30-minute break, and then we're going to have a little workshop plus Q&A plus panel on how to write a great research paper from 8 to 9. There's going to be food. And it's going to be amazing. Here. Yeah. The attendees including Dr. Cho, Sarah Hooker, and Joan Bruna for the how to write a great research paper. And probably someone more to be determined that I can kidnap before the day ends. So, yeah, without further ado, I'm going to introduce the next speaker, Kyung-Yun Cho. I'm going to pull up his bio really quickly on my phone, even though I know him very well. He was on my thesis committee, and generally he was giving me advice during my entire PhD, which was amazing. Very, very nice guy. So hold with me for 2 seconds while I pull up very smoothly the bio on my phone. So, Kyung-Yun Cho is an assistant professor of computer science and data science at NYU, New York University, and a research scientist at Facebook AI Research. He was a postdoctoral fellow at University of Montreal until summer 2015 under the supervision of Professor Joshua Bengio, and received a PhD and Master in Science degrees from Aalto University in early 2014 under the supervision of Professor Karhunen, Dr. Tapani Raiko, and Dr. Alexander Ilin. He tries his best to find a balance among machine learning, natural language processing, and life, but almost always fails to do so.
All right, thank you for the very generous introduction that was written by me, but okay. Well, I'm very glad to be back here, and Martin asked me to give a lecture on natural language processing, and I was like, how am I supposed to give a lecture on natural language processing in this era of ChatGPT? Right? All you need to do is open your browser, chat.openai.net or org, and then enter, log in with your Google ID, and then you start asking ChatGPT about natural language processing. It's going to tell you everything out there that you need to know about natural language processing. So I was thinking, and then I thought, okay, let's try to go back all the way and then try to talk about some of the very basic concepts. And then so, it's going to be a lecture without any mathematics. There's going to be even fewer math equations than the Guillermo's talk yesterday, which was very surprising to me. So let's start talking about what intelligence is to start with. This is a slide that I almost always use whenever I teach my course at NYU. So, what are considered intelligent? And then I often start by saying that, well, our monkey is considered intelligent. Almost everyone in the lecture room is going to agree that, yes, monkeys are intelligent. And then, I'm going to continue with, how about birds? Are birds intelligent? Clearly, birds are intelligent. And then I continue on, are bees intelligent? Then about, let's say, 2/3 of the class say that yes, bees are intelligent. And indeed, they are very, very intelligent. The bees actually fly several tens of kilometers, if not hundreds of kilometers away, find the flowers and all those honey, and be able to come back, memorize exactly where it was, and then be able to communicate the location to all the other bees in the hive. I would say that's more intelligent than most of us actually can do. Without Google Maps, what can we do anyway, right? And then we talk about okay, how about the earthworms? Earthworms, they don't look that intelligent, but what they do is that they're going to sense the level of the humidity, and then be able to react accordingly by either coming out of the earth or not, or staying inside. And then that seems like a nice reaction that actually considers the environments and then trying to maximize how well it can survive. So maybe not too intelligent, but perhaps somewhat intelligent. And then we continue on, right? So how about some of those bacteria? Are they intelligent? And we are just coming out of our rather still kind of ongoing pandemic. So our virus is considered intelligent. Maybe, maybe not, right? So that's a point at which really a bit confusing. So is intelligence just a reaction to the environment? If that is so, then the viruses are definitely intelligent. They actually do adapt quite rapidly, and then the way in which they evolve themselves is quite remarkable. But then at this point, I always ask the question: okay, what makes us somewhat unique from all the other intelligent beings on this earth, right? What makes us actually separate from birds or the bees or whatnot? So one way that actually sets us apart is language. So our language is extremely unique. In fact, some people will tell you that, some of those gorillas actually do have some kind of language to communicate with each other. Some might say that the bees, the example that I took, I mentioned earlier, bees do have some ways to communicate where all those flowers are and so on. But then compared to those means of communication, human language is extremely unique and extremely much more sophisticated. At the end of the day, it is one of the only communication means that has evolved over time by the nature that is compositional and productive. And it's also open-ended. In fact, we create new words every day. And in particular, in this era of TikTok, you all know that there's new phrases, new words literally every day, and then we just make them up. And then we can actually use all those new words to communicate new ideas from one to another in a very efficient way. And it's also extremely abstract. Bees can tell each other about the exact location of the flowers and whatnot, but in our case, we can use language to talk about all these high-level abstract concepts. In fact, if you think about it, whatever you're seeing on this slide and whatever you're hearing from me has actually absolutely nothing to do with the reality, if you think about it. It's all extremely high-level abstract concept. So then one may think that, so language is good, but the language alone is not enough because the intelligence definitely arises from experience. And if you think about how we know things, that is by interacting with the things. We have to see things, we have to hear things, we have to touch things and taste things. And then also we need to think about how we learn new skills, right? Skills are actually the thing that sets us apart from the many other animals as well. And then how we do that is by we try them out. We're going to walk, run, backflip, cook, and everything in order to actually learn how to do all those things. I don't think there is any more reinforcement learning lecture in this summer school or any other summer school these days. I wonder, where did reinforcement learning go? But anyway, okay. But that's how we learn it. Wait, hold on, I see some RL people, but okay, I don't know. I looked at the schedule. I didn't make the schedule, so you gotta ask the organizers. But then you start wondering, is that really all? Do we actually try all these things in order to learn the new skills or to learn, obtain our intelligence? That's definitely not true. Because here in this lecture hall, I'm pretty sure not a single one of us has ever been to ancient Greece ourselves. No one has done that. No one here was alive back then, like 3,000 years ago. However, somehow almost every one of us here knows how people actually lived in ancient Greece. That's really weird. So we didn't really have to experience firsthand how people lived back then, but we have the knowledge about it. And also, as far as like, oh, okay, so we are in South America. It's a bit different. At least in Northern Hemisphere, almost no one has ever been to Antarctica or even nearby. But here, I guess, it's not too far, right? So not too far. But, okay, so if you're from Seoul, Korea, which is actually on the other side of the Earth, from Montevideo, like exactly, there's no way we would ever get to Antarctica ever, right? But somehow I know already that the penguins do live in Antarctica. I've never seen them myself. Well, I've seen them when I was in Australia, but not in Antarctica, but I somehow know that in Antarctica there are penguins. So how do we know all those things? It turned out that it is actually the language that expands the horizon of experience. I've read about it, read about ancient Greece, I heard about the penguins that live in Antarctica and so on. So in other words, really the natural language is really important, or human language is important because it expands the horizon of experience, and then thereby for us to actually have a kind of distant perception or the collective perception, and also somehow historical experience as well. So this is the reason why language is still important, even though all we need to do is open up the browser and then go to chat.openai.ai or net, I don't know, whatever that is. Or one day Google is going to release their Bard eventually, I guess, and then we'll be able to try it. But which day, who knows? So anyway, so this is the reason why the natural language processing, I believe, has survived, unlike reinforcement learning at this summer school. And then I'm going to continue to tell you what are kind of the foundations behind the more of a modern natural language processing from here on. By the way, I want this to be as interactive as possible, so if you have any questions, just raise your hand, and then we can actually have a conversation. My guess is that with the ChatGPT, there may be some more questions than usual. So yes. So any questions so far? Everyone agrees with me that the bees are intelligent and everything, yes? And the penguins do live in Antarctica, yes? All right. So then one can imagine that although language is definitely not a sensory, let's say, perception, but we can think of the language as yet another way, extra way for us to perceive the world. It's just like, in fact, vision. We're going to perceive the world that is surrounding us via language. And because, how do we know that? Because, we're going to hear from others about how they are perceiving the world. That actually allows us to perceive the world via language. And then we also can even sense what others are thinking. What kind of thoughts do others have in my surrounding area? However, at the same time, language is unlike, let's say, vision, audio, or whatnot. Why is that? Because the language was a result of our intellectual capacity, not, let's say, physiological, let's say, capacity. And then what that means is that it's really not natural at all. Although we call it natural language, there's nothing natural about language that we speak. It's all super artificial. And in some sense, one might say that whatever we say is by definition fake because it doesn't really reflect the reality as it is, but it goes through the huge filter that is called our brain. And then what this means in technical sense for us to build a natural language processing algorithms as well as a system is that there is no inherent notion or the natural concept of similarity. So one example I put here is 3 words in English: quit, quiet, quiet. They have absolutely nothing to do with each other in terms of their meaning or what they represent. However, in terms of the spelling, they're like one letter apart from each other. So this actually gives us a sense of, how the similarity that we perceive and the similarity in their meanings are completely disassociated in natural language processing. And in fact, it gets even worse because there are more than 7,000 living languages in the world. I'm not saying that they all have the writings, but when it comes to spoken languages, 7,000 languages exist. And then spoken languages are what matters at the end of the day because the language started way before writing started. Writing is a relatively modern, let's say, artifact that started only, let's say, several thousand years ago. And then the interesting thing is that among these 7,000 languages, we can pick any arbitrary pair of languages, and then we can always go back and forth. And then that's what we often refer to as these languages tends to be complete. So if I say anything in English here, I can almost always translate the entire thing into Korean without losing any meaning there. But unfortunately, at the same time, these languages, however, rarely share any common forms. So you see quit, quiet, quiet. On the right column, that's corresponding Korean words. You see that there's absolutely nothing that you see between these two that are being shared. And indeed, that's true. And then the spelling is different, writing system is different, how we pronounce them is different, and how we're supposed to, let's say, inflect them is different, so everything is different. Although there is a central meaning that is transferable from one language to another without losing any of the, let's say, details. So then how we need to think about, can we then automatically get some kind of notion of similarity out of, for the natural language from data? And then we go all the way back to the, let's say, mid-20th century or early 20th century, where the first actually said that, okay, a word is characterized by the company it keeps. And then this is what we often refer to as a distributional hypothesis. And then what distributional hypothesis tells us is that the meaning of a word, now we're going to go into the full text soon, meaning of a word is not in the word itself. As we have seen, quit, it doesn't really have a meaning itself. I could have actually very well replaced it with a corresponding Korean word, and then the meaning is going to be preserved. So the meaning is not in the word itself, but the context in which it appears. I need to look at the context in which the word appears, and then the meaning of the word automatically arises from that. And then this context should be interpreted broadly. Of course, in early 20th century and early 21st century, when we talked about the context in natural language processing, that was only about language. But now, we are still in the 21st century, but the times have changed. So we need to think about the context in a much broader sense. We're going to include images that are actually accompanying text. We're going to include audio. We're going to include the control signals that accompany, let's say, language. So, and then one example that I took is that this elephant trunk snake. If I just write elephant trunk snake, it's largely nonsensical word, or the composition of the words. However, if you put the image together, you kind of, let's say, almost immediately notice what elephant trunk snake is. And this is elephant trunk snake, by the way. And then this is what I mean by the broader context. So we're not going to worry too much about whether we're talking about language, images, audio, or whatnot. But this whole, let's say, concept is going to be applied to the multiple modalities simultaneously. But, words at a time. And then the one way to characterize or the use or the operationalize this distributional hypothesis is trying to look at the co-occurrence statistics. So let's say I want to know the meaning of a term NYU. What do? I'm going to go to Wikipedia and then search for NYU. Oh, of course, nowadays you go to ChatGPT, ask, what is NYU? It's going to give you a very long, 99% of the time correct answer. 1% of time is going to make a few things, but it's okay. We try 100 times and then we take 99% of the time this was the right answer, right? But let's say it was pre-ChatGPT, we will go to Wikipedia, I'm going to search for NYU, and then what I'm going to do is I'm going to collect all the sentences in which NYU appeared. And then as you can see, in fact, all those sentences in which NYU appeared does describe somewhat where NYU appears and then what NYU does. And then what I'm going to do is I'm going to pick up some of the words that appeared frequently, but not too frequently, right? Because things that appear way too frequently tends to be what we call functional words. And then they are there to make these sentences fluent, but not necessarily to convey any particular meaning. So I'm going to pick phrases that are just appearing at the right frequency. And then let's see. So NYU appears together with the New York University, appears together with the university, appears together with the center, school, and so on. And then you can already see that what NYU means from here is that NYU must be something to do with university, and then maybe what stands for, may stand for New York University. So then it turned out that what we need to do is now collect all those sentences in which NYU appeared in Wikipedia, and then we're going to start counting how often other words or the other phrases co-appeared or co-occurred together with NYU. And then what we can build is what we often refer to as a word co-occurrence matrix. Now on the rows will correspond to individual words of which we want to know the meaning. And then columns will correspond to the words that appear together in the context with the particular word that corresponds to the row. And then we're going to literally count. It's going to be pretty sparse, as you can imagine, because there are so many words. But we don't really write down the things in all possible ways, but rather that reflects the actual meaning. So we're going to collect all these counts and then say that they take one row and then say that this count vector is what that particular word's meaning is. It's really that simple, right? So this is like the basics of the most important, let's say, concept behind the modern natural language processing. We go into a gigantic corpus, could be internet level, Wikipedia or whatnot. We're going to literally count how often things appear together. And then once we have this gigantic count matrix, we're going to take each row, and then we say that, okay, that the vector, this count vector that corresponds to that row, is exactly the meaning of the word that corresponds to the row. I'm using correspond way too much, but. So then how do we use it? We can now use this word vector to see which other words are similar to this particular words. If the vectors are similar, we said, okay, they must have the similar meaning. Kind of makes sense, right? So why is that? What this distribution hypothesis tells us is that the meaning of the word is in the context in which it appears. And what that means is that any words that are similar to each other must be replaceable. That is, they must appear in a similar context. And then we call them having a very similar words. Unfortunately, this counting matrix alone turned out not to be that useful because it's very high dimensional. If you think about all unique words as well as the unique phrases and everything, there are so many of them. But the amount of the data you get, even if you collect all the data in the entire internet, is not enough. So curse of dimensionality, although some people started to claim that, well, curse of dimensionality, not really the thing because we can train neural network, but turned out to be actually real. Exponential growth is an exponential growth. So what that means is that most of these vectors are extremely sparse. And then by looking at the, let's say, dot product or the L2 distance or whatnot, doesn't really tell us too much because almost everything is just orthogonal to each other. And you compute the dot product, they're all zeros anyway. So it turned out that what is really important is that we need to now rely on the technique of the matrix factorization. So we're going back again about 120 years and talk about the PCA here, right? So make a gigantic matrix, too sparse, not easy to work with. Now we're going to use a low-rank approximation to that. And then it turned out low-rank approximation is also important in optimal transport, as we learned yesterday as well, right? So it's all PCA at the end of the day. And then here, on natural language processing, PCA, right? So we start with the N words and then M co-occurring phrases. So it's an N by M matrix, and we're going to compress it into the N d-dimensional word vectors and M d-dimensional phrase vectors. And then D is going to be substantially smaller than either N or M. And by doing so, what we get is we get a much denser vector representation, d-dimensional vector representation of both the words and the co-occurring phrases as well. And then this actually is a really interesting concept. By compressing these count vectors that are extremely sparse and large into a lower dimensional space to save the space, so let's just call it save the space, what happens is that's how the generalization as well as the notion of the similarities automatically arises. So, all the reasons why we use these deep neural networks these days can be thought of as, can we extract a better notion of the similarity out of the data we have? And how we do that is by compressing that huge amount of data into a lower dimensional space. And in order to save the space, similar things will have to map to a similar points in this lower dimensional space. And then that's how we know about the similarity. And there's a question, yes?
Sorry, so you were talking about context, right?
Yes.
So what is the relationship between context and D?
Yes, okay. So I'm talking about the context. So in this particular way, co-occurrence matrix, rows corresponds to words, and then columns corresponds to all those co-occurring phrases. And then these co-occurring phrases are how we characterize the context. And then once we have that, this count matrix is very sparse because you can imagine that all possible phrases in the word, huge number of them. So what we're going to do is we're going to use PCA to make it lower dimensional. So we're going to get these d-dimensional vectors. So what we need to do is that this d has to be pretty small. But that's very easy because M is gigantic, it is combinatorial. But D, we can just fix it to some constant value. So that's the relationship. Okay, and then what it means is that, okay, so, well, instead of, let's say, counting and then use the counts as they are, what we're going to do is we're going to simply replace a count with what is being predicted. That is predicted as the dot product between these two vectors, d-dimensional vectors. The first one is a word vector, and the second one is a phrase vectors. And then the word vector size is precisely what we, I guess, used to, because no one really cares about it anymore, used to call word2vec. And then that's the 2012, and then it was actually one of the revolutionary thing that happened to natural language processing. Of course, the history of, let's say, getting this kind of dense word vector goes all the way back to 1998 and 9, when the neural language model was proposed from the University of Montreal by Yoshua Bengio and others. And also, I think in 2007 or 8, when the Jason Weston and Ronan Colbert and others proposed that, okay, we need to build a neural net to do the natural language processing almost from scratch. However, it was 2012 and 13 when Tomas Mikolov trained this, trained this large PCA model. So it doesn't sound great. But anyway, fitted the PCA on a large word co-occurrence matrix, and then show that once we do that, these word vectors are going to be, in fact, compositional in the meaning space. So we could subtract, add, multiply all these word vectors in order to see how this word, the meaning of the word changes. And then I almost believe that this was the figure that changed the perception of what we mean by natural language processing in 2013. So that's the kind of, let's say, talking about how we get the meaning of the word. And then if you think about it, of course, word is always the beginning of, let's say, texture, meaning behind any text. So any question at this point? Is everyone in agreement with how amazing this figure is? Yes? I'm pretty sure Thomas is going to like it, but Thomas has moved on to the artificial chemistry, so I'm not sure if he actually cares, but this was indeed a revolutionary plot, yes. But, words are just the first step in the ladder of natural language processing. I took away this plot from a book from 2006 on how to build a machine translation system from scratch using the principles coming out of the computational linguistics. And then here, of course, no one builds machine translation system in this way anymore. However, this is actually quite, useful to think of. So first, we have the words. And then we're going to look at how words are composed with each other in order to form a fluent sentence. That's a syntax. So we do the syntactic analysis. Once we have the syntax, we now want to know about the semantics. What is the meaning that arises from this particular composition of the words? And then once we do that, we want to actually throw away everything and then get to what we call interlingua, or the meaning. What is the underlying meaning? And then how we generate should be that we're going to put some semantics based on the actual, let's say, abstract notion of the meaning. And then we're going to put the syntax in order to form a fluent text. And then we're going to turn each and every one of these, let's say, units into actual words. And then that's how we're going to generate a sentence. And then we only got to the word, right? Wait, was there a question? Sorry. No, okay. All right. So, and then what we have just talked about is just about words. It's only about words. And then the words are really nice. And then the plot that we just looked at in the previous slide was great. However, it's very basic notion, right? But it turned out that in knowing how to extract the meaning of the word out of the large context by relying on the distribution hypothesis is exactly how we can now compose the meaning of the words into the meaning of a bigger chunk, like phrases, sentences, paragraphs, or the entire document. Because it turned out that the saying that context gives rise to the meaning of an individual word is equivalent to saying that the individual words and their composition give rise to the meaning of the text. So here was a word, and then we looked at in what kind of context it appeared in order to figure out the meaning of this particular word. Because whatever that can be replaced in the same context should have the similar meaning. Thereby we say, okay, that's how we characterize the meaning. But then you can also say exactly the same thing the other way around. What is the meaning of this context? And context is text, is by looking at individual words, and then what were those words that appeared in the context. So it's essentially just flipping the coin the other way around and then saying that, well, we're going to now learn how to compose the meaning of these words to form the meaning of the entire text. And in fact, the composition is highly relevant to the meaning of the word because it turned out looking at just a word is not enough for us to precisely characterize or identify what the word represents because of all this issue of the word senses. Every word that you can imagine, almost every one of them has more than one meaning. So for instance, this is actually coming out of the model that I trained together with my collaborators back in like 2016 or so. So we trained a machine translation system. And then, as I said earlier, counting, prediction, training neural network, feeding PCA is all the same thing. So we trained a model, and then we looked at the word vector of the word notebook. And then I just ran again PCA. PCA is exactly what happens everywhere. And then I look at the two first principal components, and then I looked at the nearest neighbors according to individual, let's say, principal component. And what I get is that the first principal component corresponds to the notebook as in the actual book that has papers and then on which you can write, which is increasingly rare. But still, that's the first principal component, probably due to the historical artifact in our corpus. But the second principal component corresponds to these electronic devices. And then what that means is that if we just look at the notebook, this word, and then look at this word vector that was produced from the count vector of the notebook, we cannot really exactly tell what the precise meaning of this notebook is because it can have multiple meanings. And then furthermore, what it says is that these word vectors, in fact, encode multiple degrees or the multiple dimensions of the similarities. It's not just a one meaning that it encodes. It actually encodes all those different ways in which the things can be related to each other. So then how can we disambiguate between these two, let's say, ways, two things that notebook, the word, can represent? And how we do that is by looking at the context in which the word actually appears. And then that allows us to resolve this ambiguity. So for instance, if I read the text, I use a notebook to join the lecture online. Because there was a word online in the context, I can now immediately tell that this notebook is my laptop. It's not the note that I write something on. So looking at the context actually tells us between these two potential meanings, which one we should choose. So this is how we actually choose the meaning, yes. Yes.
Is there a reason why they're aligned with the principal component axis?
Yes. That's a great question. The question is that, okay, why do they align with the principal components? There's absolutely no reason why that should happen. But the one interesting thing is that when we get these kind of word vectors, not in this kind of training on neural network, but in a really doing the matrix factorization of the word co-occurrence matrix, we're essentially using dot product as a way to measure the similarity. And then principal component analysis also does a bit of the dot product basis factorization. So I think that's the reason why when we take this kind of word vectors from the word to vec and then run this kind of PCA-based analysis, often many of those senses actually do align very well with the principal components. But in reality, no, there's no reason for that to happen. And this is somewhat cherry-picked, somewhat, only a little, yes. Not everything happens like that, yes, sadly. But okay, any other questions, just in case? Oh, there you go, yeah.
Can we have similar insights or is there research about other kind of embedded UMAP or
Yeah, so I've used the principal component analysis, but the principal component analysis is just only 120-year-old technique to do the visualization or the lower dimensional projection. You can use UMAP, you can use TSNE, you can use any of the methods in order to do the visualization. But which visualization method is the right one to use is very much up to the application area that you're working in. And generally, my sense is that unless the visualization is absolutely necessary for your analysis or the presentation, you should never actually project it down to the two-dimensional space. That's my view, yes. All right, yes. So then, now can we use this concept in order to build a system that's going to automatically extract the meaning of the entire text? And then that's where the idea of this attention mechanism that is at the foundation of the transformers that are eating up everything, not only natural language processing, but also computer vision, audio processing, music processing, genomics, the protein design, and everything you can imagine. except for the Apple Watch, apparently, yes. Except for that, everything, we have transformers are eating everything. And then in fact, the reason why transformers are really powerful is because of this attention mechanism that allows us to disambiguate all these inherent ambiguities behind this kind of word vectors. So let's take this example as an example. Now we can always turn individual word in this text. Now words, subwords, tokens, all the same thing. So let's say those were just words. We can actually go with the letters as well, but that just makes my slide really, really crowded. So let's say we're going to stick to words. So we're going to turn each and every word into a vector, including the punctuation marks as well. And then now I want to know the vector representation that's going to resolve the ambiguity, inherent ambiguity in the vector representation of the word notebook. Then what we are going to do is we're going to look at what notebook is, the vector of the notebook is, and then we're going to compare it against every other word. And in particular, in this case, we're going to compare it against the vector of the word online. The fact that the IC online vector should tell me that, which one of the word senses of the notebook should be used. And then based on this, we're going to assign a weight. Is the word online important for me, not me, but the attention mechanism to resolve this ambiguity that is within the word vector of the notebook? And then we're going to do that for every single word that you can imagine. We'll try the lecture. We'll try the and then everything you can imagine. And then eventually, we end up with the weights that are given to all the words within the text. So let's recap. We want to resolve the ambiguity in the vector that corresponds to notebook. In order to do that, we need to first figure out which other words in the context we need to consider with respect to this word notebook. And the attention mechanism is going to assign different weights. And in particular, higher weights to the words that matter for the attention mechanism to resolve this ambiguity. And once we do that, we're going to multiply each and every weight with the original vector, and then we're going to sum them all together. Because what happens is that now I know that the online is important, lecture is important, it's going to have a high weight. While on the other hand, punctuation marks are not going to be important. Doesn't really matter whether we are using join or not, or the two, we're going to have a very low weight. And then we compute the weighted sum of this, and then this weighted sum of all this contextual vector as well as the current vector that is the vector of the notebook is going to be a contextualized word vector of the notebook. Now we have a new vector of the notebook that is not only about the word notebook, but also about the actual context in which it appeared. Not it appears, so that's how we got the word vectors in the first place, but now we want to look at the particular instance of the context in which the notebook appeared. And then this kind of attention mechanism is how we, in fact, take into account all this context in order to resolve any kind of inherent ambiguity in the meaning of the word. And then this is how we compose the word vectors. And then we can do it over and over for every single word. So we want to disambiguate the word sense of the lecture. Lecture can have multiple meanings. We can have the join as a multiple meanings, online as a multiple meaning, and we want to resolve them all together. And then that's how we use the attention mechanism. Same thing for every word. And we're going to add in a bit of a nonlinear projection because the nonlinearity is the key to the success of deep learning. I believe Joanne probably talked about it yesterday. But Joanne talked about probably up to 2 hidden layers only, because that's what he can prove. But in reality, what we do is that we're going to stack them so many times, right? Tens, if not hundreds of times, in order to gradually compose the context, in order to resolve the actual meaning of individual words, little by little, all the way until we can actually resolve it as much as we can fully. So, and then that's how we end up with the transformers. So we start with the input, that is a sequence of the words. We turn them into the word vectors. That's they often called the embedding layer in PyTorch or JAX. I don't know. I tried JAX only once. I think PyTorch is fine, especially with the version 2. Yes. So embedding layer, and then we're going to put the attention on top of that. But the attention alone is not enough because attention is inherently linear operation. It's just a weighted sum. We add a multi-layer perceptron, so the nonlinear layer on top of that in order to turn them nonlinearly. And then, in the middle, we need to add in, let's say, normalization layer as well as a residual layer in order to facilitate learning. But it's the same idea. We do that over and over and over and over as much as we can. And then as you have learned yesterday, probably is that what is the most important thing? We make neural net as large as we can. We just make it as large as we can in order to make learning easier and for this model to be able to capture all the idiosyncrasies that exist within this kind of corpus in order to really generalize to new concepts and new ideas. So how does it actually learn to disambiguate, right? That's the question. I just said that, well, that's what the attention mechanism is going to do. But I didn't tell you how to implement it. It's like literally a black box that I put there. So how does it actually learn to do so? And then where do we get this kind of word vectors to begin with? So it turned out that the most important thing that we're learning again, ever since, let's say, beginning of, let's say, mid, let's say, 20th century, is that we gotta learn from data, right? So we can't just write it down ourselves. So in the history of, for instance, machine translation started in, let's say, mid-50s in 20th century, right? And then initially what they wanted to do was really build a machine translation system by writing down all these blocks or the modules themselves based on what we know about language. That effort, unfortunately, did not succeed, as we all know now. And it's the same thing here. We don't know how to write this down exactly ourselves. If we knew, we wouldn't do any kind of machine learning, right? So we need to think about what is the right objective function that we need to define and minimize or maximize with respect to the data we have in order to make this attention mechanism do what we want it to do. So let's see. If we know the meaning of a sentence, we must be able to fill in the missing words. This is going to be our objective. Our objective is that if our system or this attention mechanism actually know how to compose the words and to get the actual meaning of individual words or to identify the correct sense of the word, then this model or the attention mechanism must be able to fill in missing words given the context. So for instance, I use a blank to join the lecture blank and period, then our model that knows how to compose the words into form a meaning of the entire sentence should be able to tell that, okay, the first blank could be filled in with a notebook, laptop, phone, Zoom. The second blank should be, online, remotely, in person, or whatnot. So you should be able to know that. And similar thing, if I use a notebook too, and then complete blank, then the model that actually knows how to compose the meaning of these individual words in order to form a meaning of the entire text should be able to say that play StarCraft every day. That's what Koreans do. If this lecture was in Korea, everyone would have gone, oh, yes. Or, I use a notebook to train a convolutional network. Yan is not here. That's so sad. Yan would have gone, yes, that's what I do every day. Or what I used to do, I guess, in 80s, okay? And I use the notebook to record my ideas and so on. So this completion should be doable if this model actually knew how to compose all these meanings of the words to form the meaning of the sentence. And then that's the idea of the language modeling comes in. So I'm using the Maskit language model as an example, but these so-called autoregressive language models all are the same thing. So given some observed words in the context, could be on the left side alone, right side alone, some intermediate, let's say, words in the text, these models should be able to fill in what are missing. And the Maskit language models, or what we started to call it BERT in 2018, is where we trying to mask out some of the words in the input, and then trying to ask this transformer to predict what are those missing bits in the input. And then that's how we make these transformers that include the attention mechanism to learn how to compose all those vectors in order to get the meaning of the entire text. And then it turned out that there's nothing that we actually count ourselves or run PCA. We just use the backpropagation with the gradient, the stochastic gradient descent with appropriate, let's say, regularization techniques just to train the entire thing. And then we can actually do that on the hundreds of the millions, or if not hundreds of billions of the text snippets that we collected to train a model that has hundreds of millions or now hundreds of a billion parameters. And then we can actually train them. relatively easily, relatively, right, relatively. Still very expensive and very difficult, but we can train it from scratch. And then what happens is that we now do see, in fact, in the case of the bird, without any supervision, we do see that the words are actually going to be clustered based on the context in which they appear. So for instance, this is a figure from the Cohere Riff UNL from 2019. And they looked at the word that corresponds to either lie or li, right? So there are many different senses of the word lie here. And then what they did was that they fit in all these different sentences into this bird, the attention mechanism, that's going to compose the, let's say, context-specific word or the contextualized word vector. And then what you see is that it does take into account the context and then group the different, let's say, contexts according to their inherent or the resolved, let's say, meaning or the sense of the word li or lie. So there's a lie down, or the lie as an untruth, the lie as in geographical, so the placement, and then I think there's a mathematical li as well there. Mathematical sense li, as in like the li group and whatnot. And then this really became a standard approach to NLP. I'm just using a mask language model, but if the masking is done only on the right side, that's going to be the autoregressive model. So we train these models, and then if you want to really solve the problem as well as we can, we're going to collect some more data, and then fine-tune the model in many different ways, but generally just fine-tune it to minimize or maximize, let's say maximize the classification accuracy or minimize the cross-entropy. So this is the end of the part 3. So I have only one final part actually left, or the 1.5 part. Is there any questions on this kind of, let's say, how we can now train these language models in order to extract out the meaning of the text? Now, not just a word, and that actually allows us to solve these amazing things. And then up until point, this is exactly what is happening behind the curtains of all those ChatGPT and whatnot, in addition to the data, more data collection. Yes, the question.
So, out of curiosity, how long is the channel for the transformer? So, what is the length of the context? Let's say a paragraph, a page.
Right. Okay, so the question is that, when we train this kind of transformers, either masked language model or the autoregressive models, how long is the input, essentially, literally, right? And then it varies depending on how you build it. But nowadays, some of these big models, they go up to, let's say, 10,000 tokens, or if not 30,000 tokens. But that's a really large model. It takes a lot of time to train. But if you want to do it on your own laptop or something like that, you can go always up to, let's say, 5, 12, or 1,000. And then that actually does cover mostly, let's say, any kind of paragraph already. We all think that we write really long, but whatever we write tends to be really short. So it's okay. All right. Yes. I think that using a microphone will be helpful. I can hear you.
Yeah. Now I got lost in the last picture, like in the clustering. So each dot is the word, or is it a
yes.
sentence?
Okay. So I didn't actually explain it well enough. Okay, let me just talk about it briefly. So what they did was that they took the word lie, and then go through the entire corpus or the validation corpus to find the sentences in which the word lie appeared. And they collected all those sentences, and then fed individual sentence into BERT, and then collected the final contextualized word vector that corresponds to lie. So each and every dot in this plot corresponds to a sentence in which the lie appears. So 1 dot, 1 sentence. And then they used, if I recall correctly, UMAP here, in fact, to project it down into a 2-dimensional space to see if the sentences that are talking about the lie in a very specific ways are clustered together. So that's what you're seeing on this slide. Yes. Yes.
The answer that you just gave about the 10,000 plugins.
Yeah.
I'm just thinking that I did not understand it, because you gave this beautiful explanation in terms of context.
Mm-hmm.
But now the number of tokens is 10,000.
Mm-hmm.
That's like too long in context.
Oh, I see. Yes. So if the context is 10,000 words long, is it really meaningful context, right? That's absolutely a great point in the sense that when we think about the meaning of the words or the disambiguation, we think about the very local context alone, right? But then of course, we know that if you only look at the local context, that's not enough often, because there are indeed a long-range dependencies. And then that's actually what makes people who are good at literature, apart from the people who are not good at literature, is that can they actually maintain a long-term memory of what has been written long ago, so that they can disambiguate the issues much better. So for instance, I think even if we think about sentences, when we go into this magical realism from South America generally, right, Brazilian authors and so on, some of the sentences are like 2 pages long. So, really the distance or the length is quite ambiguous as well, because, as I mentioned at the very beginning, there's no, let's say, inherent notion of the similarity in natural language. And then the nice thing about these transformers, as well as the attention mechanism, is that we actually do weigh individual word differently. So, however, if it's so far away, so that that should be irrelevant, it's going to put a very low weight automatically, if it's trained well, yes. So it should be okay. 10,000, 100,000. Our goal is to actually be able to train this kind of model to take into account the entire series of books as a context. Okay. So we talked about language as in extracting, NLP as in extracting the meaning of text. But obviously what is really fascinating these days with the ChatGPT and whatnot is how these models are able to communicate ideas to us. So these models can actually produce very, very fluent text. That's what has actually made everyone, let's say, totally, let's say, excited and amused by ChatGPT, as well as the future version of the Google Bard, I guess. So let's talk about the generation quickly. And then if you think about it, generation is simply the other side of the coin. So for us or anything to understand language, there has to be another side, the other side, that actually produces language as well. And in some sense, it makes sense, right? If I could understand language or the meaning of any text, and I want to say something or to write down a text that corresponds to something that I want to write, I'm going to just try all possible text snippets until I know that the meaning of the particular text snippet corresponds to what I want to say. So in a sense, if I understood, I should be able to produce. But that's only in principle. We all know that we often are much better at reading than writing. That's the reason why there is a Nobel Prize in literature for people who actually write, not people who read, or maybe some critics as well. Yeah? So there is a bit of a difference. So let's talk about that difference here. So what does it mean? So the very basic thing is, as I said, in principle, generation is really nothing but classification. Let's say I want to build a image caption generation system. I'm going to look at this picture. I'm going to go through all possible ways in which text can be written, and then I'm running a gigantic classifier that's going to choose the one caption that describes this input image as well as possible. And that's true for the machine translation as well. I'm going to look at this Korean sentence, and then I'm going to try to see, out of all possible English sentences that could have been written, which one is the correct translation of the input. It's all just classification. But it is not really classification, or the naive classification that we think of, because in classification, we often do not assume any known structures among all these classes. We say that these classes are at least conditionally, so give an input, independent of each other, and then we're going to assign some scores to that and then choose one. But that's clearly not true in the case of natural language, as you can see already on the right side of this slide, is that every class that corresponds to a different way in which the text can be written is related to all the others, because they share some kind of underlying compositional structure. So what we want is that we want to turn this problem of classification over the combinatorial or the exponentially many classes into a simpler problem, or the composition of a simpler classification problems. And this is based on the idea that each and every class, that is each and every possible, let's say, text snippet, is a composition of simpler units, such as words, phrases, letters, and whatnot. So if I wanted to generate a giant panda bear is resting leisurely, then what I'm going to do is I'm going to first classify or to generate the first word, A, and then given that A, I'm going to classify, predict the next word, that is giant, panda, bear is resting leisurely. And then what that means is that in the case of the machine translation, we're going to start with the Korean sentence. 판다가 한가로이 쉬고 있습니다. And then we're going to first predict the first word, A. And then given that first word, we're going to now do the next classification, solve the next classification problem that is given 판다가 한가로이 쉬고 있습니다. And A, what should be the next word? We're going to predict it as giant. And then, okay, yep, perfect, 10 minutes, yes, that's perfect. And then given 판다가 한가로이 쉬고 있습니다, and A giant that have already been generated, we're going to solve the next classification problem. And then that is to predict panda. And then we continue on and on and on until we actually decode out the final word, which is almost always a special symbol that says, okay, the generation has ended. And then when and how we make these models properly generate those EOS is my research. But unfortunately, Martin was insistent on not talking about research, so we're going to skip. We say that just works. But you see the idea. We just predict the one word at a time. And then the prediction of the next word is essentially the classification. So all these autoregressive large-scale models are indeed just a series of classifiers that we have built, but with the caveat that we always use the same classifier everywhere. And then that's how we get the statistical power and the efficiency here. So then, so just summarize, at each step of generation, we solve a classification problem that takes as input the source sentence or the source. Could be sentence, could be question, could be context, could be an image, or could be a video or audio, and then trying to look at it together with what has been generated so far, and then trying to classify that combination of that into one of the all possible unique next tokens. And then we just do that over and over. This is how we generate the problem. It turned out that it's really easy to turn Maskit language model or any kind of language model that we talked about, about 15 minutes into this kind of generation system. All we do is we concatenate everything. And then nowadays, as I said, NLP is eating up the word. So we're going to serialize everything. Anything that we can serialize, we're going to serialize into a sequence of discrete tokens, or it could be continuous vectors, that's fine. We're going to put them as the input to this transformer. And then eventually we get one vector at the very end that summarizes what has been said so far. And then based on the vector, we're going to predict what the next word should be. And then what the next word should be is just nothing but softmax classification. And some people say that, we might want to do the continuous vector-based regression, blah, and blah. No, just use a softmax that's going to solve everything for you. That's what we have learned over the past 10 years. Yes, we thought we could do better, but John Bridle, who actually coined the term softmax in 1991, I'm pretty sure he didn't know that we would use softmax like literally every day. Who knew? But anyway, so and then now you can imagine how we actually serialize the images is that we can use convolutional network transformers or whatnot to get these vectors out of the attention mechanism, and then again feed it in together with what has been generated so far. And then that's how we're going to make this kind of generation systems. And then these are all just all over. This is a very old example I took away from the IBM's demo. IBM's demo is not necessarily the top notch, and still it works pretty well, right? So that's really amazing. And then this idea is behind everything at the moment. Speech recognition, machine translation, dialogue systems, automated alt text generation, ChatGPT, whatnot. Everything uses exactly the same technology. You will learn later today, actually this morning, from the Ruben about the different types of the generative models and the different paradigms. Unfortunately, in this kind of, let's say, combinatorial space, so far autoregressive models have been just much better than all the other paradigms. And everyone, including myself, we always try to try something new, but autoregressive models that have been engineered really well seems to be the king at the moment. And we'll see. So to wrap up, in fact, one thing that I want to talk about is a fundamental issue of statistical natural language processing. And that's going to connect very well with the lecture tomorrow or the day after by Sarah Hooker on the ethics and the fairness in machine learning. And the issue is that it's all statistics. Let's take as an example, leaf and a banana. Now, pink leaf and pink banana, blue leaf and green banana, yellow leaf and pink banana. These all look somewhat weird, but most of which we can actually tell immediately that all four of them on the top row are leaves, and then the bottom row are bananas. We can tell, right? You could tell, right? Yes, yes. I think that we should be able to tell these are leaves and bananas. And then if you recall what I said at the very beginning, the meaning does arise from statistical patterns, statistical co-occurrence patterns. But then we start wondering, okay, based on this idea, is it possible that the leaves and bananas, these two words, are in fact similar to each other? They don't look similar at all. We know that they are very different. But what if they are similar? Well, indeed, they are somewhat similar in our mind as well, because both of them grow from trees. Yes, bananas grow from trees. Yes, I mean, I've never seen them growing, actually. But I believe so. And then both of them are mostly edible as well. We're going to make a maple syrup out of it, for instance. That's not out of leaves. But we're going to have the cabbage wraps or something like that. And those are not leaves either. But anyway, okay. And then bananas, we can eat them. But we know that they are similar. But one thing we know for sure that I'm quite certain is that they are not similar because they have similar colors. Leaves are not really necessarily like yellow always. Bananas are often not, let's say, leaf colors. So when we say leaves and bananas are similar to each other, their colors are going to be the last one that we think of. They just don't have the same color. However, if you go into Google Ngram Viewer, which indexes all the contents in Google Books and then build this gigantic table of the counts, you can now search for green leaves, yellow leaves, red leaves, purple leaves, blue leaves, and then seeing how often they were used relatively to each other. And then you can do the same thing with the bananas. Green bananas, yellow bananas, red bananas, purple bananas, blue bananas. And then what you see here is that the order of these colors between these two, identical. And if statistical patterns or the co-occurrence patterns were the thing that we rely on solely in order to find the meaning of the word, leaves and bananas are essentially the same. Because if I look at those 5 different words that appear together with the leaves and bananas, that are green, yellow, red, purple, blue, relative frequencies of them, identical. So then we'll say that, well, look at my count vectors, they are same. But that's clearly not. And then that's what we call as a spurious statistical patterns. That is a pattern that is apparent, but not actually valid. And then this will be on one particular example of this kind of spurious patterns creeping in. Yes, Martin? Yes, I'm going to actually talk about this soon. So the validity, so the question is, what does valid in this particular context mean? Now, valid has to be defined in the context in which you're actually defining these spurious patterns. And I'm going to talk about what valid means in this context of natural language processing in about 2 slides. So the reason, actually 1 slide, but okay. So the reason why this kind of spurious patterns actually do exist and can be fundamental issues behind the modern natural language processing is because statistical patterns in the text reflect both intrinsic meaning as well as the extrinsic use of these words. So here the validity is going to correspond to this intrinsic meaning, but not the extrinsic use. That is how we use these words. So those are two different things. Now let's look at one example. Now, medical doctors and nurses. In fact, these are the icons or the illustrations that I got out of Google image search. I went to Google image search. I said, okay, nurse illustration or the nurse icon. And then these were the top 2 that I got. And then I went to the same Google image search. I searched for doctor. I think I did for the medical doctor. And then icon or the illustration. And then these 2 were the top ones that I got. Well, actually, sorry about that. The right ones, right and then left ones are the ones that I got, the top one from the Google image search, and then the other ones are from the second page. So the top of the second page, I should have been more careful. And then what you see is that, okay, the occupation of being a medical doctor, occupation of being a nurse, have nothing to do with the gender of a person. Because the intrinsic meaning is that the person who actually treats patients is doctor, person who actually assists and treats the patients is nurse. And there's nothing about the gender. However, you go again into the Google Ngram viewer, and then you are going to look at the search for the, okay, he is a doctor versus she is a doctor, and then she is a nurse versus he is a nurse. You'll see that they are completely flipped. And then what that means is that the statistically saying, if you only looked at she and he as a context or the words that co-occur together, we're going to actually mix in this extrinsic use pattern of the words doctor and the nurse. And then that's how these kind of superior statistical patterns are going to creep in. So what that means is that these statistical patterns, although have been extremely, extremely useful and helpful in building these amazing modern natural language processing as well as the generation systems, are not enough. They alone cannot really distinguish between intrinsic meaning and extrinsic use of these words or the text. And then what that means is that we somehow need to go beyond the statistical paradigm if we wanted to build a true, let's say, language understanding systems. And then as Martin just pointed out, we're exactly on time. So if you have, can I get some questions or how does it work? Yep, if you have a couple of questions, I'd love to hear about them. Thank you. A microphone will be nice, yes, to have.
Just a question that, like you were talking about the multimodal paradigm. In one slide, we saw an image with a convolution and then an attention layer. Yeah, the question is, what's the context in terms of images, right?
Yep, so in this case, this is just the one example of how we can build this kind of system. There are many different ways to build it. But you can imagine that, well, we had an image, but one thing that we know is that the transformers, as well as this kind of recurrent network, any kind of sequence models, do prefer sequence because that's how we implemented them. Then we need a way to serialize whatever the input that we receive. And some of things are easy to serialize. The audio, they're like essentially serialized by that definition, but the images are not, videos are not. So then we can use another type of the neural net in order to get a vector representations where the vectors can actually encode all the information about the content as well as the position of the corresponding parts. And then we're going to put them as if there was just a sequence of word vectors we got from the text. Then it turned out that these transformers can do some magic in order to find the right representation of the text that we're going to predict next.
Yeah, okay, so it's like you make the image like a sentence in a way, like it has like an order.
Sorry, so can you speak up a bit?
Like you make the image in a way like a sentence, like it has a certain order, so you can do like the same trick. Like there is a context in that sequence.
Yeah. Image is a context in this case, yes, absolutely.
One more question?
Oh, there? Yes. So, yep.
Thanks for the excellent presentation. I have a question that after your talk, I know better, but in the same way, I would like to hear the answer from someone with more experience like you. For you, what's the principal difference between natural language processing and a standard conversational interface that don't use it?
Oh, yeah. So the question is, what's the difference between natural language processing and this conversational search or the AI systems that we started to see recently? They're essentially the same thing, right? They're essentially the same thing not because they are same as they are solving the same problem, but because it turned out natural language processing or computer vision, all those domains have traditionally been defined by the problems that we solve, not by the techniques that we use. And then nowadays, the techniques started to be unified across many different domains, including natural language processing, computer vision, and whatnot. And then that actually makes it quite easy for us to move back and forth and also even say these outrageous things like all those things are same thing more easily nowadays because the underlying techniques are all the same indeed. Now, I'm not really an expert in the conversational models or the conversation search. If you have a question about conversational search, my former PhD student, Rodrigo Noguera, who is sitting there and who gave a talk yesterday, he's my information retrieval search guy. So yeah, you should just ask him, yes.
Please, another round of applause for Joe.
Thank you.
Hello, we're gonna move to the spotlights now, and in particular the next spotlight is from Adriana Pagano. Adriana Pagano is a full professor in translation studies at the Federal University of Minas Gerais in Brazil. She's a research fellow sponsored by CNPq and FAPEMIG, and has been engaged in multidisciplinary projects exploring NLP for text comprehension, natural language generation, and human post-editing of machine translation in several domains, including healthcare, environmental protection, and online dispute resolution of consumer complaints. She is currently coordinating corpus annotation of dependency syntax in Brazilian Portuguese and investigating gender bias in machine translation.
Thank you. I think I'll need help.
Yeah, it's okay. Hello, can someone from the video thing help us? Very good.
Can I have the mic? Thank you. Okay. Good morning to everyone. First of all, let me thank the organizers for this kind invitation. Thank you for being here, and congratulate the organizers on this wonderful conference. Well, I think I'm the odd person out here. I'm a trained linguist. I'm not a computer scientist. And this will be interesting because we have just had a wonderful talk on natural language processing. And so I think there will be some issues here to discuss. But this was very, very good indeed. Okay, let me start by saying where I come from, where we are. This is Brazil, state of Minas Gerais. You can see this on the map. The city is called Belo Horizonte. The name of our university is Universidad Federal de Minas Gerais. There are other people here also attending from this university and city. And we have a center, which is a center on computational linguistics. You can see the logo down here. And this center, the acronym is ADA. It's an obvious reference to Ada Lovelace, whom I'm not sure you all know. And this is an interesting thing because we are a computational linguistics center, but we also support and contribute with natural language processing. Just for you to have an idea, we have our core team. Our core team is made up by myself and very young researchers. Most of us are trained linguists. Some of us have a mixed background in the sense of my colleague Evandro, he's a computer scientist and a linguist. Maria is an engineer and a linguist, but we are basically linguists. And how can you do computational linguistics and natural language processing in a language program in an arts faculty? This is because we have many collaborators. As you can see, some of them at the top here. Most of them have a computer science training or engineering training, and this has made it possible for us to develop this computational linguistic center. Well, what is computational linguistics? And I think this brings some issues that were presented a couple of minutes ago, right? I don't know if you're aware, but normally there is a very famous saying in artificial intelligence. I'm not going to quote this person, but it runs more or less like this. Every time I dismiss or I sack a linguist, my productivity increases. Right? Of course, we linguists do not agree with this saying because I would say that every time computer scientists have a problem with language, they knock on our door. So this is my answer to this saying, right? Now the thing is, what's the difference between computational linguistics and natural language processing, right? As we see it, right, computational linguistics has to do with, as I'm stating here, trying to find models to explain how language works. And this is of fundamental importance to us linguists, because we want to know how language, which you call natural language, actually works. And we also want to support, right, all these tasks, studies, and applications that are connected to natural language processing. And as my colleague said, natural language generation, understanding, and information retrieval. Many of my students don't get this difference very clearly. So I brought an example, a very quick example of what we call computational linguistics. So in computational linguistics, we have a study on language, and this study has as a name per se to find out more about how language is used. This is a study carried out by a collaborator of ours, Tiago Castro Ferreira, at Tilburg University, and this is the Vareg corpus. So basically, I mean, this is just an example. This is a corpus of referential expressions in natural language, and the idea is to see how we human beings produce referring expressions when we construct texts. What are referring expressions? I mean, we have an example here. Is when we introduce an entity in discourse, right? And then we want to talk again about this entity. So what do? Do we repeat the same name? Do we use a pronoun? Do we just leave it blank because there's no need for that? So this is a whole issue that is not very much studied or known yet. So in this corpus, there was human annotation carried out and a comparison between human annotation and machine annotation of referring expressions. And so when you look at the comparison, some very interesting things can be found out. Particularly these have to do not only to grammatical categories. I think most of you remember what a subject is, or an object, or all these language terms, but also they have to do with the scope, right? As we were discussing a couple of minutes ago. Are we talking about a sentence? Are we talking about the whole text? Are we talking about a paragraph? And it has to do with recency. Has this entity been mentioned way before the text? Is it very close? Is it distance, right? Distance between mentions. So this is a typical study on computational linguistics. So we do this because we want to know more about how language operates and works. Now, natural language processing is a little bit different because we are doing, we're exploring models and we are doing research on language because we have some application in mind. Now, I'll come back to natural language processing in a couple of minutes. Now, how do we do this in a language center? Because we don't have people who are computer scientists, who are trained computer scientists. So the first thing is to develop human resources. And how do we do this in our center? We invest in a series of courses that are accessible to language students. So basically, as you can see here, we try to persuade students to program in Python. We teach about natural language processing, computational linguistics. We do a little bit of robot journalism with social science and human science students. And this is the way we work to develop human resources to carry out research in computational linguistics and support natural language processing. I'm going to talk very, very briefly about some of the projects that we have been carrying out, and I hope not to exceed my time. Let me mention one of the projects we have been developing for the last couple of years. This is called Diabetes. This is obviously a reference to the disease, a chronic condition, diabetes. And this is a joint project in which the nursing school, medical school, computer science department, the language department, we all participate to create resources in order to help people manage their chronic condition. In these resources, we use basically what we call curated information. So we use technologies that have been curated by domain specialists, and we develop a Q&A system on diabetes that is curated by our medical students. So this is not the same as GPT-4. I mean, these answers to these questions are curated by domain specialists. We did the same with COVID-19. We developed a system during the pandemic. This was a joint effort by the medical school, computer science department, and the language department. We had a chatbot, Anna, and this chatbot was essential to screen people regarding symptom severity during the pandemic when there was complete lockdown in our city, and also to provide a Q&A system to answer people's questions. And we try to do this, again, curated by medical specialists at a time where there were lots of fake news in the media, and the health ministry in Brazil was not so clear about which policy to follow. So this was essential in that sense. Another research strand in NLP that we are developing is annotating corpora, particularly in the healthcare domain. Brazilian Portuguese is a very under-resourced language in terms of corpus, in terms of models, so we need to provide resources so that then we can run all these models, right? So in this case, this is a corpus we are annotating. It's already annotated for entity recognition, named entities. We are annotating syntax, dependency syntax. The idea is to match both and to use this annotated corpus to fine-tune our generic models, and particularly for the healthcare domain. We have also invested in robot journalism, particularly in sensitive domains. Our robot journalists, you're going to think they are like dinosaurs because we still use a pipeline, and this pipeline is very, very, very traditional. We don't use neural networks. And why that? Because neural networks tend to hallucinate, and these are very sensitive domains. This is our robot Damata. He or she, it reports on deforestation in Brazil. So basically you can follow the pipeline here. We read information, satellite information, select content. There are a series of steps here till we render text, and the text is published on a Twitter account. And this is done periodically as we have new information from the government. We had a similar robot during COVID. This is Corona Reporter. This is no longer active now, but it was very helpful during the pandemic because we could report the number of cases, number of deaths in Brazil during the pandemic. We still do a little bit of sentiments and emotional analysis. In order to do that, we are working with Go Emotions text set, data set by Google. We have a translation, a trained model in Portuguese. And basically what we are doing is doing experiments in online forums text. This is an example. We did an experiment on online dispute resolution platforms. These are platforms where people complain a lot about things they have purchased and all that. And in this case, we wanted to know whether complaints, the kind of emotions that we could find in complaints by female and male users were similar or not. So we are characterizing user profile. We did the same for online health forums, like the diabetes, hypertension ones. And in this case, you see, we were comparing an automatic annotation by our model and human annotation. And you can see that the co-occurrence of emotions is very different. So the thing is, our model is not still very good, so we need to train and fine-tune this model, and that's what we use, human resources and annotation. Finishing, okay? And my time. There are many ongoing projects. You can see some of the topics here. We are looking at gender bias in machine translation. We are fine-tuning some machine translation engines in Portuguese for the healthcare domain, assessing risk in healthcare information, and developing virtual assistants for healthcare professionals. Our collaborators are here. Our sponsors are here. I thank you very much for your attention, and please make sure, if you're interested in exchanging information, collaborating, getting to know more about our center, please make sure you talk to me throughout the week. Thank you very much.
The next speaker is Pablo Barceló, who is a full professor at the Pontificia Universidad Católica de Chile, where he also acts as director of the Institute of Mathematical and Computational Engineering. He has a PhD in computer science from the University of Toronto in Canada. He's a principal researcher of both the Millennium Institute for Foundational Research on Data and the National Center for Artificial Intelligence. He's the author of more than 90 technical papers, has chaired ICDT 2019 and ACM PODS 2022. He is currently a member of the editorial committee of Logical Methods in Computer Science. From 2011 to 2014, he was the editor of the database theory column in Sigmund Record. His areas of interest are database theory, logic in computer science, and the emerging relationship between those areas and machine learning.
Thank you very much. Thanks for the invitation to this wonderful event. So I want to talk about recently launched center in Chile as a way to try to enhance collaboration with other centers and other groups here in Latin America. Yeah? So I'll talk about CENIA, which is the National Center for Artificial Intelligence, which was launched in Chile about a year and a half ago. It's a state-funded research center with researchers from all the main universities from the country, right? So today it's a non-profit corporation that in its vision promotes AI at the service of people. So what is the mission of CENIA? It's to transform Chile into a pillar of AI development in Latin America. And the way we are trying to achieve this goal is through three main axes. The first one has to do with research, ideally research of excellence, tech transfer, and outreach. And I'll briefly describe each one of these components of the center. So we have tried to be as inclusive as possible with the center. What it means, academics with a senior affiliation produce and publish more than 90% of AI research in Chile. So we have tried to gather all the people who are working in AI in Chile under this common umbrella. Yeah? So far we have 67 researchers and more than 100 students from 10 universities in 5 lines of research. And the goal is that through this diversity to ensure a multidisciplinary vision about the challenges that we face. Our research is divided in 5 main lines. The first research line is called Deep Learning for Vision and Natural Language Processing, that is core machine learning. The second one, that is the one that I lead and that I will try to talk more in detail later, is about neurosymbolic AI. The third one is where computer scientists interact with neuroscientists and psychologists trying to get a brain-inspired AI. In research line 4, we have mathematicians and physicists working on physically informed machine learning. And finally, and perhaps trying to give a coherent view of all these other research lines, we have a human-centered AI, right? So remember that at the core of our institute, of our center, is to have an AI that is at the service of people. And this research line tries to achieve this goal. So we have brought together people from at least 10 universities, as I said, most of the universities that do research in Chile. We have also been doing tech transfer. One of the duties of these centers in Chile is to bring money from the industry to complement the money that the state is given to the project, right? So we have to interact with several companies. And in fact, we are doing that, but also we are doing at the moment several projects with the state. And I'll talk briefly about them because I thought that it could be of interest to some of you. For instance, there is this problem of cancellation of surgeries in Chile that means an annual loss of $52 millions approximately. So our proposal, and this is the thing that we are working with the health ministry these days, is to make use of AI to optimize pavilion use through discrete event and multi-agent simulations. And we expect with this to have a 12% reduction on the cancellation cost of surgeries. We're also working with a service that is called Chile Atiende, that is like a portal with which citizens interact in order to find procedures that they require from the government. The problem is that citizens have difficulties finding these procedures and they require generating a lot of frustration. No? So our proposal is to train a natural language processing model in Latin Spanish using local text corpus based on GPT-3. So we are already working on building this, and the idea is that this will be available as an open source product for applications of other users. And finally, in terms of tech transfer that we are working with the state, we are working with the Interior, is it the Interior Ministry? Yes, Ministry of Interior and Public Security. So there is this public safety issue that there are very few people who monitor many security cameras, missing out on incivility and crime events. And we are proposing to create a model that tracks images and associates anomalous events with the different incivilities. Yeah? So again, the pre-trained model will be left as a an open source product. Now, in terms of the third pillar of our work, which is outreach, of course, a center like this has to do a lot of different things in terms of outreach, right? Dissemination to society. But I'll mention one that I think could be of interest to several of you, which is that we're trying to build an AI index for Latin America. Yeah? So currently, there is no document that shows the state of the art and the practice of AI in Latin America. There are documents that describe this very well for North America, for instance, or for Europe, right? But these documents are not, they do not reflect the reality of Latin America very well. And this affects because there is an absence of a common framework that prevents a serious, informed, and multilateral conversation between AI actors. So our goal, AI actors. So our goal is to build, is the construction of an AI index that considers the cultural and material context of Latin America. We are already working on this. You are all invited to participate if you want. I mean, like we are talking with people from all these countries that are shown in the figure. The index is built along three main dimensions: the enabling factors for AI in Latin America, the level of development and adoption, and the level of governance in all these countries. So we have international support from several important organizations like the Banco de Desarrollo de América Latina, UNESCO, la Organización de Estados Americanos, and companies like Amazon Web Services or international centers like the Stanford University Human Center, Artificial Intelligence Center, right? So, if you feel like you want to participate or collaborate with this AI index, I would be happy to talk to you or put you in touch with the people who are developing this in Chile. Okay, so I have like 3 minutes left, if I understand well. Let me talk more in depth, if possible, about the work that we are doing in this research line on neurosymbolic AI. Yeah? So what is neurosymbolic AI? The idea is trying to combine robust methods based on machine learning with the reasoning explanations generated by the symbolic representation of knowledge. That is combining machine learning with knowledge representation somehow. Yeah? Why? Well, because we want to help neural architectures to reason better, to learn with less data, to better generalize to new domains, to provide explanations for the decisions they take, and to try to establish causal relationships among others. Yeah? So neurosymbolic AI is a very, very broad topic, and we are not so many in our group in Chile, so we have tried to focus on 3 areas. Not necessarily these are very core neurosymbolic AI topics at this moment, but are related to this, and we are trying to expand to other topics in the future. So the first topic that we're working has to do with knowledge graph embeddings. We know that semantic networks are used in artificial intelligence to represent knowledge, and they can be used to provide domain knowledge to neural networks. So the way in which this is done is by developing a numerical representation of the semantic network, of the knowledge graph, as an embedding. And what we want to do is to understand the nature of the embeddings that are being computed today based essentially on graph neural networks or in recursive algorithms. And on top of that, we also want to develop new foundations and methods for the area. Yeah. So here there are a couple of papers that we have been working on combining relational graph neural networks for knowledge graphs together with understanding the expressive power of these things and what they can do and what is their computational cost, essentially. Yeah. So the second thing that we have been doing is computational social choice. So today, what is computational social choice? It's the study of mechanisms to add individual preferences in terms of a collective one. So today, machine learning techniques are starting to be used to perform such an aggregation. And what we want to do is to work on computational social choice mechanisms for the selection of projects and scientific papers and for the idea of liquid democracy. So we have started to work on that. We have a paper submitted on that that is about the use of computational social choice techniques together with machine learning techniques to do selection of papers in conferences. And finally, another thing that we're working has to do with explainable AI. There are several lines that we have tried to follow. I'm finishing. It's the last slide. Yeah. So for instance, several scores and queries have been proposed to explain AI result. Very little is known about its computational cost and about their suitability to explain things really in different domains. And we are trying to understand the computational complexity of these scores and also trying to design declarative languages to specify explanations in different situations, right? So here there are two papers that we have been working on. One has to do with the complexity of computing sharp scores, and the other one has to do with the complexity of computing probabilistic explanations for decision trees. That's it. Thanks.
By the way, before we leave for the coffee break, one little announcement. If the people from the posters that have posters from yesterday can take them out so that the people that have posters today can put them in, that would be amazing. And we have time for one question for the speaker. Over there.
Hi, I was very interested about your application of ChatGPT to deal with people. I was wondering if you were planning to assess what kind of interactions this technology can deal with and which ones need to be taken over by humans so that are beyond the capabilities of the technology. I don't know if you have looked into it or are you planning to?
Well, sorry. Well, this is not a project in which I'm working directly. This is a project that Xenia and its team of engineers are working on. I'm quite sure that they are trying to look into these topics, but I can definitely put you in touch with the people who are working on that if you're interested, yes. Thanks for the question.
One more round of applause. And by the way, the coffee break is going to be until 10:50, so we have a bit of time to catch our breath before coming back.
Yeah, maybe. Yeah, let's start, right? Let's give them 1 minute.
Wait, what?
No, just wait a little bit.
Oh, yeah, it's fine, no worries. Yeah, let's wait for them to sit.
Okay. Hello, everyone. Welcome back. Our next speaker is Ruben Villegas, who works as a research scientist at Google Brain. Ruben received his PhD from the Computer Science and Engineering Department from the University of Michigan. And interestingly, Ruben is also a former national basketball player from Ecuador and was among the top scorers from the national championship. Ruben has made significant contributions to the fields of generative modeling, self-supervised learning, and multimodal learning of videos. His research focuses on leveraging the time dimension to learn more general and compositional representation. Please join me in welcoming Ruben.
Thank you. Yeah, hi everyone. So I'm here to talk about generative models. So what are generative models? So generative models are a statistical model that you can generate data from some distribution these models can either be of the form probability of X or probability of X or Y and X. This is in contrast to the discriminative models, where you try to compute the probability of some label given some data. And some examples here, here's some examples from a generative model where you have this bunch of dogs being kind of modeled, and the cats, and then you have this, on the right, the discriminative model. So the difference here is that for the generative model, you want to kind of model all the details of these dogs, so you can generate multiple different types of dogs and everything in between. While for discriminative models, on the other hand, you just try to find the differences, which doesn't necessarily mean that the model will learn all the details of these inputs. It just learns what's different between them. So some examples of some recent generative models are dialogue systems that we've seen in the form of ChatGPT. Here's an example of Lambda. Other examples are video generation models, for which this one's not playing, but it's a video generation model such as Image and Video, and Fenaki, for which I'm a part of, and image generation models. And also one of, in my opinion, the first ones that at least I was wowed with back in 2013 from Alex Graves, which generates, actually this handwriting is generated from text as well. So it's kind of like this, similar to what we're doing right now that everybody's excited about, but with pencil strokes. You can generate text from handwriting from text. And as well as music generation, which recently Music LM came out, and it generates music that looks just like, it sounds like real music. This is moving too fast. So in this talk, I will focus mainly on generative models of images and video, and just discuss some popular, the most popular, which are the diffusion and transformer-based generative models at the moment, and just highlight the differences and advantages, disadvantages of each. So some recent history of generative models of both images and video include if you guys have heard of the GANs, VAEs, and flow-based models. So the GANs are where you train this neural network that kind of tells you whether something comes from a distribution or not, the data distribution. And you train another neural network that learns to map some random noise to a point within the distribution. And in some adversarial training paradigm, these two compete to the generator to generate something that looks just like the training data. The data distribution, the discriminator learns to find the problems that the generator has while trying to simulate this data distribution. And the one problem with this approach is that it's very unstable to train, and so people have looked into multiple ways to do this generative models. Another one is the VAE, the variational autoencoder. In this approach, we learn to map the data samples. We learn to model a proximal posterior, which maps the data samples into some latent variables, and then we learn a decoder that maps those latent variables to the data sample. And then you can generate just some random latent variable and generate some data. So one, I guess, caveat from this is that there's this approximate variation of lower bound, which is not exact, and then there's some issues that come from that. And then the flow-based models at the end, which also, again, generative models, you map the data to some latent space, and then from the latent space you can generate data, and there's some requirement from these models are that you have a function that you can invert easily. You have to make sure that this function that you use to map the data to the latent variables is invertible. And yeah, so here's some examples. On the left, images, and on the right, videos. So as you see, in the image domain we made even before the current diffusion approaches, we made a lot of strides towards data that looks just like real data. And these are all a mix of GAN and GAN and VAEs and flow models. And saying on the video domain, we haven't made that much progress in terms of the realism, but still we had some models that can generate like driving scenes or this person that looks like it's dancing and so on. And these are all based, again, on GAN, VAEs, and normalizing flows. This is, okay. Let me just do this. So yeah, the first one I'm going to talk about are the diffusion probabilistic models. So this approach actually came out in 2015. And what this approach does is, this models is the data distribution by a forward and backward process. The forward process takes in some data and then gradually adds some noise to that data until you have something that is indistinguishable from the original input. And then, or it's indistinguishable from noise. And then from that noise, you can invert that process and then get some sample from the data distribution, from the data that you're trying to model. So that's basically the highest level way that this can be explained how it works. And so in the diffusion paradigm, we have this forward process that is modeled by this Markov chain that you see here, where you have some previous data samples, and then you have a distribution that simply adds noise to those previous steps. So related to what I showed before is the steps, these noising steps that you see here. So this forward process just adds a little bit of noise to the data until you get to some standard Gaussian distribution. And this is parameterized by usually by this standard normal, by this normal distribution, where we just have this beta parameter that it's time dependent. And we simply basically scale the previous data or noisy data and then just add some noise. And then this, the good thing about this kind of like stepwise denoising is that it gives us some type of path towards the data distribution that we can learn with some neural network in order to generate data. So then we have the backward process, and this is parameterized by this P theta. And this backward process basically just takes in some step in the forward process that I showed before and tries to denoise, to generate the distribution of the data sample after a single denoising step. And this is parameterized by this mean and standard deviation that come from a neural network, given the previous noisy input, and some time step that tells us where in the noising process we are. And training, to train these networks, basically we do an objective similar to variational lower bound. But the difference is that in variational lower bounds, this Q here is an approximate posterior, which actually is this network that maps the image to some latent representation. But in diffusion models, the difference is that this posterior is actually the forward diffusion process, which actually destroys the data a little bit compared to the previous diffusion process, which is different because you're not really extracting some latent representation. You're just adding a little bit of noise to the previous latent representation generated by diffusion. And then we have this prior here that is modeled, that's modeled by a neural network that is simply, what it's doing is just trying to match that noise, the inverse of that noising process. So that's good. So once we have this objective, we can decompose it. So this is the variation lower bound of comparing the distributions that I mentioned before. And on the left, here's the final step of the diffusion process, LT, which basically is just trying to make sure that this forward diffusion process achieves some, in this case, standard Gaussian distribution. But since the forward diffusion process is not learned, this part is just, at least in this case, it's fixed, so we don't care about that. And then on the right here, we have something that's a reconstruction, basically, step, where we have the first noisy output, and we try to reconstruct the input, and this is L0. And then everything here in between is just the diffusion process, where you have the forward diffusion process and you have the backward diffusion process, and you're trying to match the distributions so that they match, so that you can actually undo the diffusion process. And so one cool thing about this is and we're separating this by time steps for a reason, because we have this Markov chain, but at the same time, there's a cool thing where this forward diffusion process, if you let this this alpha t equals to 1 minus beta, and then this alpha bar t equals to the product of this alpha sub to t, you can actually compute any step in the diffusion process in closed form. And at training time, you don't actually have to simulate the entire chain that you see here. In diffusion, you can actually just sample some random step during the diffusion process and simply optimize that part of the objective. You don't have to simulate the entire diffusion process, and this makes the training much faster, thanks to that closed form of the forward diffusion. So yeah, from that, we move on to like what most people are using, which are the denoising diffusion probabilistic models. So what they notice in this paper is that during the forward diffusion process, basically what we do is taking the input data, we scale it by some value here, and then we just add noise. So that's basically what's happening during the diffusion process. So what if instead of, as previously, instead of computing some parameters that gives you the denoise data and the next time step in the denoising step, why don't we just learn to actually denoise the data instead of actually generating the distribution? So actually to remove a little bit of noise from the data. And this is basically the motivation for this paper, and it actually turns out it works really well. And so one thing that they do is, so let's say they ask themselves, what happens if we allow this standard deviation from the backward diffusion process? What happens if we just allow it to be fixed? If we allow this to be fixed, the variational lower bound that I showed before simply becomes this square error between means, and this is the mean of the forward diffusion, and this is a mean computed by some neural network. And the C are just terms that don't depend on any of the learnable parameters. So if we allow this, then we have, if we parameterize this, the xt that we had previously, if we parameterize it by this form, basically the forward diffusion process. So if we parameterize it like this, our objective becomes what you see here, and then the mu that we compute from using a neural network simply has to match this. And then what if we parameterize this mu by this objective by this form that you see here, and we simply let the neural network just predict the noise that has been added to this data at time t. And if we do that, then we arrive to what we see here, which basically just requires for us to have some neural network that learns to predict how much noise has been added at the current time step in the diffusion process, and all we do is just match noises, which at the inference time, all you have to do is just basically just remove this noise at the current time step during the backwards diffusion process. And this is basically their objective. And another thing that they notice is, so they have this weighing term here on the left that comes from just literally just deriving the variation of lower bound. And what happens if we remove this and we end up with this objective, which is even much simpler. And they also, some interesting thing is that they find that with the way objective, you get this inception score, which is used to measure the quality of images, and fresh inception distance, which is the FID. If we remove this weighing term, actually the performance improves at the cost of the lower bound. So you can, what the authors argue about this is that this allows the model, removing this weighing term allows the model to just focus on the most important bits of information in the image, such that you get some image that resembles the actual data very well, instead of worrying about imperceptible pieces of the image that don't really matter. And this allows for what you see today. So from here, so this is just basically just kind of introducing what all these methods are based on. There's some variations, but they're basically based on this. From this, there's been work like cascade diffusion models, or known as Imagen, which they apply this diffusion process in multiple stages of resolution. On the left here, you have the text as input. Then from that text, you generate some low resolution image. And then you simply, the next stage is you upsample that resolution given text and using the diffusion process, and you end up with very large images with high levels of detail due to the diffusion process, because it's an iterative process that is kind of refinement. The first few stages of the diffusion process find some high level semantics of the image, but then the next stages kind of refine the image so that you see what you see in this, you get what you see in these examples. And these models are also amazingly able to generalize to crazy images like this dog playing a guitar and this eagle made of fruit, which are some interesting findings that these models can actually take some piece of text and then reflect what that text is describing into the images that you see here. And so there are other versions of this using, again, DDPM. The so-called stable diffusion, which maybe most of you or some of you have played with, which instead of doing this cascade diffusion process, they do first extract some latent representation using some BAE. Just have an image, compress it into some very small latent space, and then do the diffusion process on that latent space. And the good thing about this is that it saves all of these steps in multi-step cascade diffusion models. You don't have to do all these steps to get a high resolution image, because you do it on the compressed representation. You can have a large image, compress it to some representation, and then do everything in that representation, and then just decode from that to the images that you see here using the decoder in some variational autoencoder. So one caveat from this is that you rely on the compression method that extracts the latent representations from the images to model all the details, and sometimes, as maybe if you compare the Imagen here against these encoder first diffusion later models, then you get less detail. But still you get some type of generalization given a prompt like that octopus on the right. And so besides image generation, lately there have been works on video generation using diffusion. And on the left here we have, this is Make a Video from Meta, where they do a similar thing to Imagen and to Imagen Video on the right, where they have a bunch of cascade diffusion models for upsampling in time and space, and but start with some low resolution generated video. And but the difference from this and Imagen Video is that Imagen Video has actually assumes text video pairs, while the model from Meta doesn't assume, it assumes text image pairs, but the videos are assumed to be unlabeled. But again, these methods can generate videos that you see here. Although they are limited to a few seconds of video, they still look very high quality and realistic given the prompts. Yes, so these are, oops, what happened? Yes, so this leads us to the, if you have any questions, please feel free to shout them out or maybe leave them for the end. But from this, we move to transformers-based image and video generation. And this is actually something that I've used, and it works, at least for me, well. I haven't used diffusion yet, but yeah, mostly use transformers. So from previous talks, I'm sure you heard about transformers. So transformers, attention is all you need, were developed by, actually mainly for language. But people found out that, and the reason it's for language because you can kind of tokenize language into some discrete tokens, but what people found out is that if you can discretize your input, you can apply it on whatever you want. And this has been applied on computer vision, music generation, image, video generation, reinforcement learning, and so on. So, and the cool thing about transformers is, I guess, this attention that lets you kind of grab information that you need and to put it in your outputs. And there's two pieces in the original paper, the encoder and decoder transformers, and people have used either the encoder, the decoder, or a mix of both while working on their task. So the main thing, again, is the attention. And attention, basically, what it's doing is you have some query, and you have some keys and values. And given this query, you compute some similarity with the keys by doing some dot product. And then, and this, again, these queries kind of go with each one of these, or are mapped to each one of these values by, to each one of the keys in parallel. So you compute similarity, and then you compute an attention weight that lets you, basically allows the neural network to learn to choose information based on that similarity between queries and keys, or keys and queries. And then based on those similarities, based on the attention weights, then you can just weight the values, and then you get a final output Z based on what the attention finds. And this is yeah, just regular attention, and the queries come from some other input, and the keys can come from another input. But there's also a version which we call self-attention, where everything comes from the same input, and you can compute features using attention. And this is, hold on. It's not animating, okay. So as I kind of mentioned before, we can have multiple queries also where we compute not just like one attention vector, but a whole attention matrix where you can compute a bunch of different outputs using attention. And also, besides that, you don't just have like one branch of attention that you compute. You can have this multi-head attention where your inputs kind of split in multiple heads, and you compute multiple different features using attention, which allows the model to kind of decompose the input in different ways and extract useful information for whatever task that you're trying to accomplish. And so here's the attention architecture, the transformer architecture. And as I mentioned originally, the first step, here's using the text example, the first step is a tokenization step, where you just split your input into some discrete sections. And after that, you can map these discrete sections into some vectors that come from a vocabulary of vectors, and you map, in this case, the indices to some vector in that vocabulary. And with images, the same. You, with your patches, just kind of map into some vector within some vocabulary during the tokenization step at the beginning. And you compute an embedding. And then the one, I guess, caveat from the transformer on its own is that it's permutation invariant, or not caveat, but at least for this application, you need to have ordering, so you have to use these positional encodings that let the transformer know where in the sequence it is at the moment. And this is not just for language, also in vision we do this, also maybe some of the video stuff to add like the time, position in time, and so on. And here, all you do is just add some number. Of course, this is just like a simple example. You add 10, 20, 30, but you can actually learn these positional embeddings or have some fixed version, but that gives you some positioning within the sequence. And the multi-headed self-attention, as I mentioned before, it basically just computes a bunch of different feature vectors from the same input with different attention masks applied during the key query value computations. And the next piece is this pointwise MLP. And then this is just, there's no communication between the tokens happening here. This is just a forward process, just some neural network that computes some representation. And what people have observed is that it's kind of like a pondering type of or like knowledge storage that happens within the transformers. And this actually, when people scale up the architectures, this contains the bulk of the parameters. And yeah, I call it one by one convolution because it's just an MLP. And another thing that they found useful is the use of residual connections. And the reason, so they found it to actually improve trainability. And this is because these architectures are very deep. So the gradients may, they may vanish or something may happen. So adding these skip connections actually let things flow in a better way. And another thing that they found is that layer normalization is another thing that helps, so that the values just don't go in every layer. They just don't get out of control, so you can just normalize. And there's two ways that they've used, which is one of them the post-norm and the pre-norm that currently being used in each transformer block. Yeah, and so the encoder usually, so think about this in the kind of translation. The encoder is very heavy, usually because you take in all the input and then you compute some representation using transformers. It doesn't, at least in this case, people have used it differently in other cases, but in this case, it has nothing to do with the output. So it's just encoding some input that you want to, in the translation case, of course, translate. And then it leads us to the decoder transformer, which is the same process. Basically, you have some embedding that you map your input to. But in this case, you're actually modeling this probability of Z, which is the output in this case, given X. And the output for translation, for example, is this detective investigated. And then the cool thing is that this transformer output lets you can model this probability of Z in a type of like token by token approach, where you have probability of, you just use the change rule of probability, and you have probability of Z given X, Z2 given Z1 and X, Z3 given Z2, Z1 and X, and so on. And you can do this within the decoder transformer. and you can generate one token at a time. So once we have this PSD, we actually, during actual sampling process, you do it in either whatever way you choose. You can have greedy or beam search or whatever that you want to use during the translation, in this case translation phase, when you sample the next token. And so one way to train these transformers in an optimized way is that you can use, let's say, so if you want to compute every one of these Z's and then optimize them, given the previous ones, you may think, okay, I can do this one by one, but that doesn't have to be the case. We can use a modification of self-attention where instead of every token looking at everything in the sequence, in the output sequence, you can have the token only look at everything before. And then you can optimize all of these next frame or next token prediction probabilities. You can optimize it all at once by using this self-attention into one huge matrix multiplication. But then again, at generation time, even though you can do this, the training part very efficiently, at generation time, you still need to do sample one at a time. Sample one word and go to the next, or feed it back into the model and continue sampling. This is what's called autoregressive decoding. And the other thing that is used is this, in order to condition on your input, you use so-called cross-attention, which is, again, it's the same, except you're doing attention with the conditioning input and all the outputs. You just compute these key query values, the keys and the values come from the encoder, and then you have your queries from your decoder, and then you just compute this matrix multiplication that is not self, but it's like cross because it's on some other input, and in order to compute the next prediction. And this allows the model to actually, once you want to predict the next token, you can look at the entire input and what you have generated so far and decide what information is the most important to predict the next token. And then you can do some type of, I guess, I don't want to say reasoning, but some type of reason about what's been seen so far. Yeah, it's and because yeah, self-attention it's so widely used, people call it attention, but like, at least most people that I've talked to call self-attention the one that actually looks at everything, and the other one cross-attention. The one that looks at the input and the one that kind of looks at another conditioning input is cross-attention. And then again, feed-forward layers and the softmax output at the end. And this just lets the model decide which token to predict next. So this leads us to, so there's two ways that people do this. For example, the GPT-3 way, where you have some autoregressive model that all you do is look at the previous input and predict the next output, and you can just optimize this model and then have some sequence modeling model that can generate things autoregressively and continue generating them over time, similar to GPT-3, and also image generation has been able to do it this way. And yeah, this leads us to DALI and PARTI, which are transformer-based image generation models. So PARTI is this architecture that we see here, where we have some encoder transformer that takes in some text, and then we have a decoder transformer that I described before, and tries to predict the tokens of this image one by one. And the tokens are extracted using some encoder, in this case VQGAN, because VQGAN gives you some discrete representation of the image, and so you can kind of do a language translation in a way from the human language to the visual language, because you have some tokens, so you're doing a translation from one to the other, and then you end up with something that you can visualize using the decoder from this VQGAN that was trained. And then you get images such as this ones. And for DALI, It was similar, but except they have, if I recall correctly, they have only a transformer decoder, which has some separator between to tell the transformer that it should generate image tokens instead of that it's reading image tokens and generating image tokens instead of reading text tokens. But the idea is similar. And here's what methods like party can generate. That again, similar to diffusion, they can do some type of so-called compositional generalization, which means you can grab concepts from your training data and recombine them in ways that are not present in the training data. And you can have this panda reading a book, riding a horse, wearing this hat, and so on, that are literally just, you have some text tokens, translate them to image tokens, and decode these image tokens into pixels. And the more recent, at least to me, way that people have been doing image generation is actually using the so-called masked language modeling, but on the visual tokens. So this is the masked language modeling similar to this works called BERT, where it's a transformer encoder, but it's trained to complete some missing information. So in this case, we have Z1, Z4, and Z5, which are missing. And this transformer encoder is optimized to predict those values or those vectors given all the other inputs. So they're just trying to do completion. And this can be not just completion in between, it can be to the right, to the left, anywhere in between. And this way, these models actually learn something useful about the data and translate in some really cool properties in the image models that are trained using this approach. Which leads us to Maskit. So Maskit is not autoregressive, so this is the autoregressive model like Party that I mentioned before, but Maskit actually is a model that is similar to diffusion, where you can give some time steps to generate your image, but it does it multiple tokens in parallel. So you start with a blank canvas here, and then you generate one token, and then given this token, you can, using some predefined schedule, you can generate some other number of tokens, and little by little complete the image, and until you have the final image. The good thing about this, and I'll show some timings, is that this is way faster than doing autoregressive generation. And it's also, to me, it's like more natural because, I mean, you can look at image as a language, as some sentence or something where it has to be done autoregressively, but I think for images, doing things in parallel, similar to diffusion, make more sense. And again, this is based on the same, first you encode, you learn some tokenizer, where you encode the image into some discrete tokens. And the model is trained by masked visual token modeling, which is, again, same as MLM, masked language modeling. That's where you drop some tokens and you train to generate those tokens, which can be dropped in whatever way randomly during training. So all you have to do is train this single step prediction or completion, which to me is also kind of similar to diffusion in a way, because in diffusion you can grab some random time step in the diffusion process and then train to denoise that. And here it's kind of similar. You grab some random number of drop tokens at some time step that could be possible, and then you try to predict the denoised version of this. But the noising here is just randomly dropping the tokens and replacing them with masked tokens. And the way, so this is really easy to train, but the way to do inference is more complicated. Oops. Inference is done in the following way. So first, you have some blank canvas, and then you compute some probabilities. And given the probabilities, you sample some tokens. Once you have all these sample tokens, you have a schedule of how many tokens you want to keep or drop, and then you sort all these tokens, put the highest probability ones first, and then pick the K number of tokens based on that probability, which gives the confidence of the model of how it's how confident the model is of those tokens. So you can just, based on the schedule, you can keep the top K tokens and then iterate. You drop everything else, remask them, keep the previous tokens, and then do inference again, get probabilities, sample tokens, grab the top K, and so on for some number of steps that are predefined. And then this way you can complete the image in a very fast way using transformers. And so here's a comparison. X is the number of tokens, Y is time, and Maskit versus autoregressive. The autoregressive, just like the time goes up quickly, while the Maskit, it doesn't go up. While also the FID and FEDs are also are comparable or better. And so this brings us to one of the recent Maskit-based models, which is called Muse, which actually is doing the same or similar approach as Imagen with cascade diffusion models, but you have cascade Maskit models. And they're able to actually generate similar or maybe slightly better, if I remember correctly, performance than Party and Imagen, but much faster, because you can build this parallel decoding from Maskit, where you have, first from text you generate some low resolution tokens, and then once you generate the low resolution tokens, you can have another network, another Maskit that increases the resolution of those tokens, and then you end up with a high resolution image, much faster than the other approaches. And Maskit, so one thing that I personally am a big fan of Maskit is that because of this masking process, there's many things that you can do out of the box with Maskit without having to train for them. So for example, here you can do editing. This is mask-free editing, so you don't need to specify a mask where you want to edit. All you do is change the caption, drop some random tokens and regenerate them, and the model eventually starts replacing those tokens with the caption that you want. So here it replaces this cat as a dog, this ball, regular ball as an American football, apples to oranges, and this cat, and so on. So that's, at least to me, it's a really cool thing because you don't have to train for it. You can fine-tune it and it gets better, but it works out of the box. And same with image completion. You can just remove this background and generate something else, and remove this car and generate something else here. And this is something very important actually for the video models that the final ones that I will show here, because it just works. I mean, you don't have to do anything special to continue. You can do this in the time dimension. And another thing is that the Maskit, in this low to high resolution process, the low resolution process doesn't look, as you can see here, that great, but then once you go from low to high, the image just gets better. But again, this still suffers from the issue of the encoders that may not have as much detail as, for example, a diffusion model directly on pixels, but still gives you something that looks like this. And finally, so here's some video models using Maskit. So this is MagVid, which recently came out, which basically, this part, it's basically just Maskit. But the encoders here, they use a 3D encoder so that they can encode video. And then they also train this model for multitask. So it's for completing this image here or generating video in between, which makes this model capable of multiple ways that you can use it. It's based on Maskit, which just Maskit allows for these things to be more easily modeled. And finally, so this is a model that we recently had, this accepted to iClear, where we also use Maskit. It's called Fenaki. But what's different from the previous one is our encoder. It's an encoder that encodes video in an autoregressive way. So you can, with the same encoder, you can encode 1 frame or 3 frames or 5 frames, depending on the setup of the model. But the good thing about it is that if you input some blank frames in the future, the representation will not change, which helps Maskit actually be able to allow us to to generate videos that are basically endless, and by changing prompts in the middle, and you can generate these stories that happen here. But again, Maskit allows for this to actually be possible. And yep, so that's all my talk, and thanks for your attention. Any questions? I think.
Hello, thanks for the talk. So I wanted to ask you, seeing the phase in which these models get better and you get more resolution, what do you think is our role as data scientists and computer scientists to guarantee ways in which we can keep the population safe from things like deep fakes and forgery and hazards like fake news with these technologies?
So yeah, that's a good question. So that's, I think, one thing that people working on this are thinking about, because they're getting better, and then it starts getting to the point where it's hard to tell whether it was real or fake. I think, so one way, but I don't know if it's the best way, it's to try to remove data that we don't want the model to know about, like humans or something like that, so that if you say person, it cannot generate a person, or if you say edit person, it cannot edit the person's face into something else. But, so that's one way, but then there's other things, examples that are more fuzzy, because the model, I think, eventually, because of prompt engineering, you can always figure out a way to get whatever you... Prompt engineering is kind of like an adversarial attack. You can kind of figure out what the input should be to get exactly what you want out of the model. And you can basically attack the model to get things, even if they look blurry or something, that are not what the makers of the model intended the model to generate. So it's a very tricky thing. The other way is also to have filters post-generation, where we detect something and then we just block it. But then also those maybe are based on neural networks, which are not perfect, and something will slip out. And it's a very complicated issue. But I think we consider this while we're working on this on these models. But I think there's a whole community trying to figure out how to prevent this from happening, because these things are useful. So in a way, for example, in conversations, I like to give to share memes to express what I feel. So I created memes that are funny, and share with my colleagues, internally. So applications like that are cool. But then you always have if the model is too good at generating memes, it's going to be very good at generating some undesired things. So it's something that we still need to work on. It's very difficult.
Thanks.
Hi, thanks for your talk. Very interesting indeed. I wanted to ask if there is a kind of issue with copyright related to the image generation that resembles some work of art, like Picasso or something like that.
Yeah, so that's another thing. And it's not just image. I think also video can generate Van Gogh style monkey giving a thumbs up or something. So yeah, it's another thing that we need to figure out how to address. And again, maybe for like art pieces, specific art pieces that you don't want the model to know about, you can just remove the data. Like Picasso, Cubism, or the Van Gogh style, you can just generate it. And then if you say Van Gogh style monkey giving a thumbs up, the model is not going to know what Van Gogh style means, so it will not generate it. So I think those are probably more easily fixable than the problem that she mentioned, where you can generate some person like doing undesirable things. So yeah, I think those are, but it's still a problem. Yeah.
Hello, my question is about when you mentioned about cascade diffusion models, you say that the diffusion process is applied in multiple stages and multiple resolutions. So my question is this similar to what is being done in the LabGAN model? I mean the Laplacian GAN?
Oh, yeah, you're right. I think there was some work, but this is back from the 2000 and
15?
at least, yeah, by Emily Denton, I think, right? Yeah. It's similar. I think, it's the same flavor. Yeah, because I think there was like a multi-resolution generation. Yeah, I think it's similar, but except there's diffusion going on here. Yeah.
Okay, thank you.
Okay. Hi. Maybe it's a silly question, but we were using GAN and some generative models for creating data related with biology. And my question is that I'm assuming that the answer is no, but I would like to know your opinion on this. If we are trying to create kind of image related with cell growth or kind of biological images, you know, like growing cells or related with this kind of things, and you let's say that we succeed and we have some amount of images created with this, do you think it's possible to train any classification model then with using this as an input, or you think it's gonna be biased, or it's kind of making or cheating or something like that?
I think that's an interesting, so you basically want to use these models as data generators for your downstream task. I think that's something that's possible, but yeah, of course it depends on the data that you train. If you train with a very small data, it's probably going to generate some things that are not very diverse, and they may negatively affect your downstream model. But I think if you have like a good data distribution, you can probably generate something that is useful. You have a model that is useful for generating data. But then again, you said assuming they work, but it's going to be difficult. Like, let's say I was discussing yesterday with someone that can we generate physical interactions? Maybe it's not the same, but it's something similar. But then how do we measure that the physical interactions generated are correct? So that's another thing because you want your model to be able, if you generate whatever data, to be actually correct to train the downstream task. Like in this case for the physical interactions, but that's also difficult because we don't even know exactly how to evaluate these models well, like FID or FED, but then, it's...
No, but when you are talking about cells, cells are bigger than molecules, so you can grow cells actually, and maybe, you can try to reconstruct actually real images of growing cells, so could be a possibility to check with real data. When talking about chemistry or physics, maybe it's kind of tricky, but when you have cells, it's kind of possible. Okay, so, yeah.
Is there some? Over here? Okay.
Hi, I was wondering, in a model, in an algorithm like Fenaki, how do you assure temporary consistency? Because, for example, in this example here, we see contextual consistency, so we see a monkey in all the frames, which are generated, but the objects themselves, they appear a bit flickery, so there doesn't seem to be consistency in the flow, for example, of the objects.
Yeah, so that's probably the compression part, the video compression part. So another thing to note here, this is GIF. So GIF has like some discretization there that can cause noise on the GIFs. But yeah, so one thing that of course we're working on improving the encoders and so on. But one thing that actually, even though you see some flickering there, still like the overall, when we extend stories for a long time, it's still it's somewhat consistent. And the way that we try to do this is by this causal attention over time to make sure that the representations, even if you encode 1, 2, or 3 images, doesn't change from what you would see on a full video. But yeah, I agree that there's still, there's still some work to do, a lot of work to do actually, so yeah.
Yeah, but my question specifically is there a mechanism in the design of the algorithm, like
for consistency?
Right now, like in this version, yeah, for consistency.
The only thing is the causal attention over time. So we don't do, there's an objective with FVD in the encoder, which should help a bit, but the only thing where we actually make sure that, or try to make sure that things are consistent no matter what we encode, is the causal attention over time. Yeah, this allow, actually what we notice allow the model to even transition into different things. Yeah.
Okay, we have one final question.
Hi, thank you. Mostly you talked about image and video generation, but is there also work on like 3D model creation for like video games or virtual reality or?
Yeah, there are works, I forgot the name of the person working on this, but I saw some work on text to actions, and you have some skeleton that you can just move around and make it do things by typing commands. So I think this is applicable to many, like there's music generation, music LM, there's the handwriting thing from back in 2013. So there's multiple applications. If you can figure out how to do text to something, I think you can just optimize a model to do this.
Thank you.
Oh, all right, so let's thank Ruben for the very exciting presentation. So our next speaker is Jose Eduardo Ochoa Luna. But while he prepares, I have one announcement to make. We're gonna have a voting for the poster for the poster session. So everybody here is invited to cast their votes to what they found to be the more interesting posters. But the way that the voting is gonna work is that everybody's gonna get a code, and the code so everybody's gonna get a code from their emails, and you might have received the code already. So just check your email. If you didn't get it, check your spam. It might have fallen in the spam box, and otherwise just reach out and we can see what's happening. Okay, another announcement.
Yes, we have seen that there were many people standing in the back part, so there are seats here. If people can move to the center a little bit and release the borders so that people that are sitting on the stairs can go in, that would be great. Or if you come here in this row, in this row, you can just come in. Thanks.
Cool. So let me introduce Jose Eduardo Ochoa Luna. Ochoa Luna. Jose is a professor in the Department of Computer Science at the Universidad Católica San Pablo in Arequipa, Peru. Jose holds a PhD in science from in computer science from the University of São Paulo, Brazil, and is a coordinator of the Artificial Intelligence Group and the recently created master program in data science. His current research interests include machine learning applied to natural language processing, probabilistic graphical models, and data science in health and education. Let's give him a round of applause. And wait for the thing to work. It's not going.
Thank you very much for the introduction. Good afternoon, everyone. Today I'm going to present the research in artificial intelligence that we are developing in the Department of Computer Science at Universidad Católica San Pablo in Peru. But first of all, I want to show you where is the department located. The department is located in Arequipa city. It's the city of the southern region of Peru. And as you can see in the picture on the right side, this is a picture of our campus, and the city is surrounded for 3 volcanoes, and there is also a river, the Chile River, that runs through the city. And our campus is near this river. And this is the AI programs and groups that we have in our department. I am the leader of the artificial intelligence group, but in the past we have had the full-time master in computer science, and we are currently running diplomas in machine learning, data science, computer vision, and we are going to open a master in data science. And this is the team. This is the UCSP faculty. As you can see, all my colleagues are obtained their PhD in Brazil, so we have a special connection with this country. And it is important to note that our external collaborators, we have external collaborators from, for instance, Jorge Poco from Brazil, Guillermo Câmara from Brazil, Javier Montoya from Switzerland, Edwin Escobedo and Germain Garcia from Peru, and Viviana Kotick from University of Buenos Aires in Argentina. And I hope we can expand this list during this Khipu event. And this is our main research areas related to artificial intelligence. We develop computer science, computer vision, virtual reality, data science, optimization, machine learning. And today I'm going to emphasize the work we are developing in natural language processing because it's my main area of research. In particular, in NLP, we focus on the Spanish language because despite being one of the most spoken languages of the world, we still have a lack of corpora and native data, and we have still several challenging tasks. So today I'm going to present 3 projects that we are working on. The first project is NLP for digital surveillance. This is a joint project with Viviana Kotick from University of Buenos Aires and her team. And the goal of this project was to create a system to trigger alerts about possible outbreaks of diseases that are prevalent in Latin America. In Latin America, we have some diseases such as Zika, dengue, Chaga, Guillain-Barré, and we wanted to construct an automatic extraction of these diseases incidents. And we wanted to answer these kind of questions. For instance, after analyzing several texts, what are the articles or texts that mention a given disease, how many cases are reported, what is the date of the report, and so on. So in order to solve this task, we wanted to use a corpus and automated extraction tools such as NER and information extraction. So this is the proposal of the project. The main contribution of the project was, in fact, the annotated corpus that we have constructed. And this corpus is based on PrometMail. PrometMail, if you don't know, is a public resource at internet, a collection of articles for people from the entire world that reports about incidents of disease in several languages. So aquí you can see an example of a report of Chagas in Argentina. So based on these texts, we have constructed a corpus, and then we have developed some automated tool to extract information from this corpus. In fact, the hard part was to construct a corpus. We analyzed about 800 articles from PROMET in Spanish. We follow this stage. The most difficult stage or step is the annotation process, but was a process that we carry out between a Spanish native speaker from Argentina and Peru using BRAD. Some of these members were computer science students, linguistics, and NLP researchers. And this process lasted about 3 years because of pandemics. And the result was several set of entity, annotated entity about the date of disease, a disease, the cause of the disease, location, number of cases, origin, transmission form, and some modifiers such as negation, past, and uncertainty. We also annotate relationships within or among some entities, for instance, disease, number of cases, disease, the place, etc. As a result, we published some papers. The most important is this paper on BMC, Bioinformatics Journal, that was published in December. And I was to emphasize that this project was supported from CONCITEC, which is a national agency from Peru that promotes science and technology. But again, the most important result is the corpus, which is it's a public corpus that you can access in this website. You can download and try some machine learning algorithm for NER or for relation extraction task. And we tried some information extraction tools, algorithm. Preliminary results were obtained using recurrent neural networks and transformers. But there is still room for improvement. Our preliminary results obtained 0.64 on microphone. So there is still for improvement for this task. The second project was the use of NLP for personality detection, and then use this framework to try to predict suicidal tendencies from text. And this was a project with Ricardo Lasso. So in psychology, there are several psychology personality models. MBTI is one of them. There is Big Five. And the system categorizes or classifies a person according a label. For instance, a person classified as INTP is a person that loves problem solving. So our objective in this project was the following. It is possible to extract some personality traits from text, and the answer was yes. Fortunately, there is a public data set in Kaggle, MBTI Kaggle data set, that has some text labeled according these categories: introversion, extraversion, intuition, and so on. And we have trained this data set using several transformer models, and we have built a framework that allows us to detect personality traits from text. Interestingly, we have extended this work for the use case of suicidal tendencies. And in order to do so, we have used this work of Janowski et al., that psychology work, that found similarities among MBTI labels and suicidal tendency profiles. So concretely, if a person presents this kind of labels, it's possible that this person can have suicidal tendencies. These labels are INFP, in other words, introversion, intuition, feeling, and perception. So now we have complete the framework using these labels of Janowski et al. And we have a framework to detect suicidal tendencies from text according to the MBTI model. But this is a work, this is an ongoing work. There is still room for improvement. The aim of this project was only trigger alerts, because we are not psychologists, and it's only, the objective is only trigger an alert, okay? Finally, I'm going to present a project from my colleagues, Eric Gomez, Daniel Gutierrez, and Miguel Nieto, about the using of AI for predicting student dropout. They use a combined approach using classification and survival analysis. But the interesting thing is they constructed an interface in NLP in order to do this kind of prediction. And this is an interface. As you can see, you can enter with some variables in natural language. For instance, here, the student is female. She's a student from a public school. Or he's single. She's 28 years old. And the system returns a prediction according to this input. And the prediction is a probability of dropout for each semester using machine learning and survival analysis. So, thank you very much for your attention.
Does anyone have any question? Yeah, so I'd like to invite Germán. Just a minute. You can put it here. Yeah, do you want to put it here? Let me present Germán Mato. Germán Mato is a researcher at the is it all good? Okay. Is a researcher at Comisión Nacional de Energía Atómica and CONICET, and professor of physics at Instituto Balseiro. He obtained his PhD in physics at Instituto Balseiro in 91. His research interests are processing and analysis of medical images and computational neuroscience. He has worked on image processing using both Bayesian techniques and deep neural networks, and applies the theory of dynamical systems to large neural networks. Yeah, okay, so before that, let's do some additional announcements.
Okay, there's two announcements. The first one is that those that have travel reimbursements should go before lunch to the secretary to pick them up. And the second one is that we have available chips for cell phones with preloaded data and phone calls, so you can also get them for free in the secretary in the reception. So important for those ones with the reimbursement, please go as soon as possible. And the chips for the cell phones is, if you are not connected outside of the venue, it's a good choice. Okay. Yeah, please, after the talk. Please don't go now. But before lunch. Yeah, obviously. Sorry. Okay, sorry, Diego.
Why is it not?
Do you want without the presenter mode?
No.
Hello.
Oh, I see. Now. Okay. Thank you. I'd like to thank you, the organizers, for the invitation, for working for preparing this wonderful conference. I'd like to talk about our experience at Centro Atómico Bariloche and Instituto Balseiro on artificial intelligence. Instituto Balseiro was created in 1995 with an agreement between Comisión Nacional de Energía Atómica and Universidad Nacional de Cuyo. The first career was physics, and then later were created several engineerings, such as nuclear engineering, mechanical engineering. There is also now a master's degree in medical physics, telecommunications engineering, and very soon we will have a PhD in medical physics. All the students have scholarships from Comisión Nacional de Energía Atómica. Most of the students are from Argentina, but also we have students from several other countries in Latin America. The main activities of Comisión Nacional de Energía Atómica are research in basic and applied physics and research and development in engineering. Most of this staff is integrated by physicists and engineers, but recently there was some addition of biologists, medical doctors, chemists, etc. Most of the personnel don't have a specific background in artificial intelligence. Essentially, it's people that have come from other disciplines, essentially from two main groups. One is there are physicists that were interested in complex systems, neuroscience and neural networks, and on the other hand, we have also engineering applications, specifically from control theory and signal processing. There has been recently the courses at Instituto Balseiro that incorporate subjects of artificial intelligence, such as neural networks, that incorporates neuroscience and artificial neural networks, deep learning and artificial neural networks, with emphasis on image processing, introduction to machine learning, with emphasis in classical methods, introduction to bioinformatics, introduction to numerical computing with GPU, and information theory. Recently, we have created, there have been a lot of interest in biomedical applications, taking people from both backgrounds. In in 2015, it has been created the medical physics department that, whose main lines of research are advanced radiotherapy and medical devices, biomedical sciences, computational neurosciences, nanomedicine, neuromagnetic resonance, spectroscopy and imaging, and signals and image processing. We have in the department more than 20 full-time researchers with backgrounds in physics, biology, engineering, and computer science. This is the web page of the department if you are interested in the details of what we are doing. In the department, we have, on one side, a strong emphasis on the uses of local data. We have established relationships with several clinical and medical institutions in Argentina, and also we have a strong set of collaborations with different countries. Here is we are showing some of the institutions with which we collaborate. The main subjects of the signal and image processing, that's where the applications of artificial intelligence are being developed, are feature extraction through multimodal recording, image denoising, image segmentation, image registration, image analysis for clinical studies, machine learning, neural modeling for neurological disorders, oscillation analysis, optimization strategy for real-time image and signal processing, and physiological signal processing, and real-time signal processing using programmable logic devices. Regarding medical imaging, the main modalities we are studying are ultrasound, MRI and diffusion MRI, MRI PET, and intracranial EEG. So let me talk a little bit about the projects we are developing. Some of them were shown in the posters from yesterday. But if you have interest, just contact me, and I can give you more additional details. One of the project that is one of the posters from yesterday is about diagnostic of cardiac disease. When the heart suffers an infarctus, there is some part of the tissue that becomes deteriorated and is not able to contract properly. This lesion is difficult to detect this lesion is called fibrosis and is easy to detect in magnetic resonance image when a contrast agent such as gadolinium is used. Unfortunately, this contrast agent is contraindicated in some fraction of the patients, and is considered to be an invasive procedure. So we are trying to see whether this lesion can be detected taking as input of the system an image without contrast agent. At first sight, there is no lesion, right? But we can train a neural network to detect the lesion using the magnetic resonance without contrast agent as input. This is the poster that we showed yesterday. These are the main integrants of the project. Let's see, there are two medical doctors. The doctors were the ones that provided the image and made the segmentations of the image in order to have a learning set for the neural network. Another project is cardiac strain quantification, right, in which we take what we call the cine image in magnetic resonance with all the time frames and try to quantify how the heart is contracting and expanding as a function of time. We are developing an end-to-end system in which the software receives the inputs, that is the image, and generates visualization, quantification, and strain report. And we are incorporating this as a plugin to a standard visualization program that is called the Slicer, that is used by the doctors. These are the members of this project. Another one that was one shown in a poster yesterday by Marcos Obando is a reconstruction of optical projection images. This is a quite new and promising technology for biomedical imaging, in which one puts a sample that is semi-transparent or semi-transparent, illuminates with light, and takes a photograph. And then there is a rotation such that one can evaluate projections on several axes. And the problem is to reconstruct the volume using as few images as possible. For this, we developed a scheme called 2Mod-L, which incorporates a network that performs denoising with another system that takes into account data consistency in order to achieve the desired reconstruction. This is a sort of recurrent network that here is shown unrolled in time. Here is a scheme of the network, right? That incorporates the block that performs the denoising. Here are the results. We can see that we can achieve a good reconstruction of the image, even with acceleration factor of 26. This means that, in fact, we can make an acquisition 26 times faster with less projections, and even and in this case we achieve a reasonable quality of the image that is competitive with other methods. These are the responsibles of the work that is done in collaboration with researchers from Portugal and Italy. And finally, we also are working on EEG analysis for detection of heart attack. This is essentially, the purpose of this is trying to analyze signals that were obtained in the emergency room, right? I mean, when a doctor takes EEG, there are two situations. One is in his practice, right, in a well-prepared, in a well-controlled environment, but also EEGs are taken in an emergency room. These have lower quality, right, and are much prone to error. So it's important to try to develop a tool to improve the quality of the analysis, and we are working on a neural network to make classification of these EEGs. These are the examples where not only we classify the EEGs, but also we find the regions of the EEG that the network looks, right, to take its decision in order to have some interpretability for the doctor. These are the responsibles or the integrants of this project. So finally, if you have any interest in these projects or in principle or at Instituto Balseiro, please don't hesitate or look at the page www.ib.edu.ar for Instituto Balseiro and Física Médica. Física Carnea Bovar, Física Médica for the Department of Medical Physics. Thank you.
Thank you, Herman. Yeah, now we're going to have our lunch and poster session hour. We're going to start about 15 minutes later, so we're supposed to start at 2 p.m., but we're going to start at 2:15, so you have more time to look at the posters. But yeah, so we meet back here again at 2:15.
Hello, can you hear me? Great. Well, it's a pleasure to me to introduce you to Alejandro Ribeiro. Alejandro received his bachelor degree in electrical engineering from here, the Universidad de la República, in 1998, and the master and PhD degrees in electrical engineering from the Department of Electrical and Computer Engineering at the University of Minnesota in 2005 and 2007. He joined the University of Pennsylvania in 2008, where he is currently Professor of Electrical and Systems Engineering. His research is in wireless autonomous networks, machine learning on networks data, and distributed collaborative learning. Alejandro's work has received more than 15 Best Paper Awards, including IEEE Signal Processing Society, IEEE Brain Initiative, Cambridge Ring Publication of the Year Award, and conferences such as EBSIPCO, ICASS, and Sound Workshop. Also, his teaching has been recognized with awards from Distinguished Teaching, Penn's undergraduate students' body for outstanding teaching, and the TISA Awards here from Facultad de Ingeniería. Alejandro has received an outstanding research award from Intel University Research Program in 2019. Thank you, Alejandro. The floor is yours.
Okay, well, thank you, Fede, for the invitation. Thank you, all of you, for being here ready to listen to me. And thank you to Federico and the rest of the organizers. I have a friend who has told me that organizing a conference is about the same work as organizing a wedding. I am married, but I did not organize a wedding, so I still don't know what that means. But I hear from my lovely wife, Gabriela, that it's a lot of work. So thank you all. So that's the title of the talk. So, you know, I always like to begin my talks by asking the question of why. In this particular case, the question of why has a simple answer, because I teach a class on graph neural networks. That's the website, so you can visit the website and leave. I'm gonna give you a shorter version of that course. Now, but anyways, if you like what I say today, you can visit that website. The video lectures are posted there. There's a little bit of a small roadmap to tell you how to make use of those videos. If you're not a student at Penn, I think it's useful. It's a relatively popular resource as these things go. There's a few hundred people per day that watch these videos, so maybe you'll find them useful. But I do like to ask more meaningful why questions, and in particular, graph neural networks are a technology used for machine learning on graphs, which begs the question of why would you care, or why should you care about machine learning on graphs? And let me give you 3 reasons why you should care about this. The first one is that graphs are models of a structure, or genetic models of how components of data, how components of signal relate to each other, right? So that's what we learn in our computer science courses. We learn of graphs as a data structure. Well, you know, the graph itself is a data structure, but it's also a structure that relates the data that lives in the nodes of the graph. Okay, and here you have a couple of examples on that. These are, you know, just taken from things that I do. One of them is on authorship attribution. The other one is on recommendation systems. And the commonality here is that in both of these cases, there is a graph that contains meaningful information about the problem that you want to solve. So for example, in the case of authorship attribution, what you have here on the left is what we call a word adjacency matrix. So this is not NLP, by the way. So it's interesting that in this morning we heard that we eliminate all of the function words. So these are actually precisely the function words. And the point is that this is kind of like a signature for the writing style of a particular author. And more to the point, that's the signature of the writing style of William Shakespeare. The one on the right is a signature for the writing style of Christopher Marlowe, and it is possible to compare these two networks and see that they are different, right? So for example, you know, there's some weird things that Marlowe likes to do that Shakespeare, there's some weird things that Marlowe likes to do that Shakespeare does not, and vice versa. And leveraging that information, you can do a little bit of detective work and conclude that Henry VI, beautiful play, worth reading, is in all likelihood, a collaboration between Marlowe and Shakespeare. And that is actually what the, I don't remember if it is the Oxford Shakespeare or the Cambridge Shakespeare, but I think it's the Oxford Shakespeare encyclopedia says is true. So, and this was partly based on the conclusions of this work. Now, another example of a graph as a data structure is a recommendation system. In here, you have different products that have been rated by different users. And you are trying to predict ratings of products that haven't been rated. And to do that, you construct a graph of product similarities. When you go from the left to the right, what you see is that this signal is kind of like more low pass, for those of you that have training in signal processing as I do. And the reason why this signal is more low pass is because that signal is high pass because it has missing ratings. In this other signal, we have completed the ratings using essentially a low pass filter, although, as you will see later on, this low pass filter is actually learned. And it's not actually a low pass filter, it's a graph neural network. Now, these are examples of a graph representing a data structure. What I like more, and that's just my personal bias, are problems in which the graph structure or the network structure is inherent to the problem. And this is an example of, related to the processing of brain signals, which are not signals that have the kind of Euclidean structure that most of the other signals we work with have. This is very well known that our eyes are processed in the back of our head. Right? So this thing apparently has not been designed, or if it's been designed poorly. It processes data in weird ways. Now, given that fact, you would like to say, I am going to go and develop tools that leverage the network structure of the brain to process data that I collect about brains. In this particular paper here, what we do is we look at the problem of brain age prediction. Why would you like to predict brain age? Well, because if you predict brain age, you can predict gaps between the predicted brain age and the actual brain age. Like, for example, in my particular case, I'm very brilliant, so my brain age is very young, whereas I am getting relatively old. For other people, the opposite would happen. No, jokes aside, this is important if you're trying to diagnose dementia or Alzheimer's early on, right? So before symptoms manifest. Because, before symptoms start to manifest, the brains of these people start to age more rapidly. Something that is actually even closer to my heart is the appearance of graphs in cyber-physical systems. And I am showing you two examples of this here. So this is a group of drones that are trying to, all of them, coordinate so that they drive at the same velocity without bumping against each other. This is not Uruguayan sky, that's actually a simulation, but it is a simulation in a physics engine. This is actually Unreal, if you guys are into gaming. Thank you, PDF. Okay, so anyway, you can see that this is a problem where a graph appears because of several reasons. Like the first one is there's clearly some underlying structure of proximity between these agents, and that's the information that you would like to leverage to avoid collisions, for example. And there's also the fact that you want to operate without central coordination. So if you, the keyword here really is decentralized. You don't want to solve this problem in a centralized manner. You want to be able to solve this problem without central coordination. That's why we call it decentralized. In that case, you're relying on communications between the agents. That communication is literally a graph, and that's exactly the other thing that is happening on the right, where we have wireless communications network or a cartoon picture of a wireless communications network where you're trying to manage resources. In both of these cases, there is a graph, and based on that graph, you want to allocate some kind of resource. What is interesting about these two problems is that in both of these cases, the graph itself is the source of the problem. When we talk about the first two, and actually the first three, in all of these three cases, the graph is something that you're trying to leverage. Here, the graph is an inherent problem that you're trying to mitigate. And the reason for that is because the goals here are typically global goals, like coordinating the team or making sure that everybody has an enjoyable quality of service when the decisions are local. And this transition from locality to globality is mediated by the graph, and that's why we like to say that the graph is the source of the complexity here. Now, these kind of problems in cyber-physical systems are the ones that I study the most in my research, so I can't keep talking about them for the rest of the day, but I figured that would be a little boring. There are nevertheless a couple other examples here. This one on the left is another example of a decentralized system. We have a team of green agents that are trying to navigate this set of red points. This is a navigation problem that is of interest, for example, when you're trying to construct a map of this area, okay? You can do this by brute force, or you can do something smart. Doing something smart is surprisingly difficult. Therefore, you can learn to do something smart. In that learning process, you would like to leverage the graphs. And what is interesting about this particular example is that there are two graphs, the graph that connects the points of interest and the graph that connects the robots. So you have kind of like a GNN on top of GNN situation, which is pretty cool. On the right, or well, whatever, here you have an example in which the problem we are trying to solve is what we call mobile infrastructure on demand. So you have here a few red robots that are moving around, doing something. Mapping is the typical thing that roboticists like to say that their robots are doing, so you can think that we have a mapping problem similar to this one. But these things are going to eventually get out of communication range, and in order to avoid them getting out of communication range with each other, you deploy an autonomous, on-demand team to provide this infrastructure connectivity. And that's why you see, things moving around at the beginning of time. These red dots were disconnected. Eventually, the blue dots position somewhere in the middle so that this communication can go on. And in these two problems, again, the situation is the exact same thing as before. I mean, the graph itself is the source of the problem because, again, you have local decisions that have a global impact. The transition from global to local is mediated by the graph. Okay. Now, this is why. The next question that you need to ask in research is how. And the how, in the year 2022, in Khipu, which has the name AI on the title, is, we should use a neural network, right? So what else? The challenge here is that I showed you maybe examples with a few agents, but these problems become interesting when the number of agents is large. Now, when the number of agents is large, you have the scalability challenge. And we know how to solve scalability in different situations. In particular, we know how to solve scalability when we're given an image, right? In that case, we use a convolutional neural network, and we call it a day. This is technology today. It's barely research anymore. But we do not want to scale on a structure like this. We want to scale in a structure like that. Well, if that is the problem, here is the solution. You get this graph, you generalize convolutions, you then compose your convolutions with pointwise nonlinearities, you stack that in layers, you call that a graph neural network, and that generalizes a convolutional neural network, and it would inherit the properties of convolutional neural networks, therefore it should work. And that's actually what we will do. I mean, in all of these problems, I was not showing you just the problem, I was showing you solutions, and those solutions are built or can be built utilizing graph neural networks. And graph neural networks are based on graph convolutions, therefore I'm going to consume the next 10 minutes of your day talking about graph convolutions. Now, in order to generalize graph convolutions, this is what I need you to realize, which maybe some of you already know. If not, I'm going to explain it pretty soon. But what I need you to realize is that convolutions, the usual convolutions that you guys know about, already are operations on graphs. Okay? The convolution in time is an operation on a line graph. Convolutions in space are operations on a grid graph. Before I tell you how convolutions are performed on this graph, let me tell you that these are representations of time and space, right? So if you want to represent time, time 1 follows time 0, time 2, well, I ruined the surprise factor. So time 1 follows time 0, times 2 follows times 1, 3 follows 4, and so on, right? So here, node 23 is close to the 4 adjacent ones, and so on. Now, if you want to write down convolutions, you begin by doing something like this. You get your signal, and you just multiply it by a certain coefficient. There's an s to the power of 0 here for reasons that will become apparent pretty soon. You then get the signals of your neighbors, which you can get by multiplying by the adjacency matrix of this graph, and you multiply that by another coefficient h1. You get the information from your 2-hop neighbors, you multiply that by a coefficient h2, the information of your 3-hop neighbors, you multiply that by a coefficient h3, you keep going to infinity if you wish. That polynomial on that shift operator is the convolution. The convolution that you know, it is written in a language that is somewhat unfamiliar, because you probably are more used to seeing the convolution written in terms of kernels, in terms of pointwise operations, but you can do the math later on and you will see that it is the same, okay? And that's why I have this animation, by the way, because the animation kind of makes that obvious, right? So you get your own signal, then the signal of your neighbor, then the signal of your 2-hop neighbor. So these H's here are your kernel sliding through the data. But, I wrote this in a manner that will allow me to generalize it to graphs. Because if this is my definition of a convolution in time, I propose that my convolution in a graph begins by considering my own signal, multiplying that by a coefficient, then getting the signals of my neighbors, multiplying that by another coefficient, the signals of my 2-hop neighbors, multiply that by another coefficient, 3-hop neighbors, I keep going to infinity, if you wish, and that we call it a graph convolution. Now, if you didn't know what a graph convolution was, well, now you know it. This is a graph convolution. A GNN is built by stacking these graph convolutional operators. It is interesting to know, right, that nothing has changed, yet a lot has changed, right? Because I am utilizing in both of these definitions the exact same expression, but of course, what changes is what S represents. In this case, S represents a shift in time. Here, S represents a neighborhood aggregation in a grid. In this case, S represents, well, whatever the graph tells you that it represents. But intuitively, it has the right properties also, by the way. It's, it has the locality and the compositionality of convolutions. Now, it is possible that you have heard of the term message passing. So I wanted to tell you what the term message passing comes from. It comes from unrolling these matrix products. Okay, so you begin with your own data, you diffuse it through the graph once, you diffuse it through the graph a second time, you diffuse it through the graph a third time. Each of these things is multiplied by a different coefficient. You sum them all. That's the definition of convolution that I gave you a minute ago. But you can see that in each of these multiplications by S, you are passing messages with your neighbors, because this is a graph. The sparsity pattern of the graph is the sparsity pattern of the network which connects you only to your neighbors. Therefore, on that matrix product, you have only those entries. Okay? Ignacio Ramirez, who didn't bother to come today. Thank you, Ignacio. Ah, there you are, Ignacio. Sorry. Look at Ignacio. He's dressed in black against a black wall. How am I supposed to see you? Okay, so Ignacio told me to make sure that I presented this in an educational manner. I don't know why he wanted me to do that, but I had slides that were dumber than these ones, so without equations essentially. But I hope that you like the level of refinement here, Ignacio. Is that what you wanted? Thank you. Okay. Now, okay, guys, I'm telling you this. I know that this looks like a relatively heavy mathematics, but I'm doing matrix products, right? So, it looks difficult because it's 2 p.m. But, let me go back and tell you what I'm doing, right? I'm telling you, I want to define convolutions on graphs. Why do I want to define convolutions on graphs? Because I want to define graph neural networks. And what am I going to do? Well, I will first define convolutions on graphs, then I will say, yeah, just use pointwise nonlinearities and stack them into layers, same as we do for CNNs. Okay, excellent. Now, how do I construct this generalization? By realizing that the convolutions we've been using for a century now are already operations on graphs. It's just that they are operations on particular graphs. And what are they? Well, they're polynomials on a particular adjacency matrix. How do I generalize convolutions to graphs? By not generalizing, really. I just let the graph be whatever the graph is. And that has this message passing interpretation, which I think is useful to know because of several reasons. People do use this concept of message passing. It also gives some intuition about what is going on, right? So you get local information, somewhat local information, less local, somewhat global information. So as you keep doing more and more message passing, you are going from local to global, which I told you, that's the fundamental problem you need to resolve. Yeah, it depends on the graph. I mean, it depends on the graph. You don't typically want this to be too long. If this index gets to be too long, you rather cutting it off, putting a nonlinearity, calling that a layer, and following the diffusion in the next layer. You will see that when I introduce GNNs, it will be more clear then. Okay. Now I did this pause because I do want to introduce a little bit of very tiny little bit of somewhat abstract math here, okay? Which is that I'm going to define a convolution as a polynomial on a shift operator with coefficients hk. And these are just squiggles in a piece of paper, okay? So this is an algebraic abstraction, and that's why I'm calling that an algebraic convolution. And I'm doing that to point out to those of you that understand what this means, that this generalization of convolutions from time to graphs is not a generalization because they are really the same algebraic object. Okay, it's just that it is an algebraic object that when it gets represented in a different way. But the use of polynomials endows these convolutions with compositionality. That's because we have these operator powers, and we know that compositionality is important in nature. And they also endow this operator with some kind of equivariance. Okay, and we'll talk more about that later on. The other thing that follows from that representation is that a frequency representation exists. And that really, I am talking to my people here, but anyways, that's like a Fourier transform, okay? So whenever you have a convolution, you have the equivalent of a Fourier transform. And that's relevant, guys, because it means that your filters are pointwise operators in some domain, in particular in the eigenvector basis of the shift operator. But this is really very important property that convolutions has. It kind of explains why convolution works. It is the tool that we utilize if we want to understand what convolutions are doing. Now finally, and that's only because of Ignacio, I also want to point out here that in practice we use convolutions with multiple features, which have this form, in which these signals, x and z, are not signals on a graph, but they are matrices, in which one of the dimensions represents the graph, the other dimension represents multiple features. But if you look at this structure again, it is still a structure that has the same algebraic structure of the convolution that I defined before. Therefore, it also has the same properties. It is compositional, it has some kind of equivariance, and it admits a frequency representation. But this definition here matters only if you want to program GNNs or filters, because we don't really use these ones. We use these ones because they have more expressive power. Okay? Good. So let me see where we are. I'm going to finally talk about graph neural networks, which is the promise that I made at the beginning. There are some of my doctoral students here. I always told them the most important message of your talk has to be given within 5 minutes. I want to talk about GNNs. I've been talking for 20. I still haven't defined GNNs, but I gave you the gist of it already, which is, we're going to compose these convolutions with nonlinearities. But let me go back and tell you what I've been trying to do. Okay? I've been trying to tell you, first of all, that you should care about this, because there's a somewhat large number of applications that we can handle that involve a graph one way or another. I told you about authorship attribution. I told you about recommendation systems. I told you about brain networks. Told you about 4 different examples of cyber-physical systems, which were the consensus problem, which really, that's kind of like a toy nobody cares about, but it's a toy that we use as a canonical example. But then I did tell you about 3 real-life problems. Problem A was the allocation of resources in a wireless communications network. Problem B is this multi-vehicle routing problem. That's what that figure represents. And I told you about the mobile infrastructure on demand problem. I not only told you about these problems, I told you about the solutions. So you already know that these GNNs work in practice. You just don't know what they are. I'm trying to explain to you what GNNs are. And in order to explain what GNNs are, I went through this analogy, which is we know what CNNs are. In order to construct GNNs, we just need to generalize convolutions. And that I did, surprisingly, by not generalizing. Make sense? It's pretty cool, right? I look like Cantinflas, baby, but I'm trying not to. Right, so I'm ungeneralizing convolutions by not generalizing. Why? Well, because time and space are graphs. We know how to do convolutions in time and space. We just need to let that S be what that S needs to be. And that has some meaning, okay, in terms of algebraic representations. It just means that at some level, all of these convolutions are the same. That's at the level of the algebra. When we instantiate the algebra in a particular representation, that's when the convolution on a graph and the convolution on time becomes different. But if you don't understand that, you don't have to worry about it. I do want you to remember that in reality we use convolutions with multiple features, because that's important in practice, and I wouldn't be doing my job as an educator if I didn't make you aware of that fact. We are now ready to move on to define GNNs. To define GNNs, let me do something elementary here, which is to define a neural network, which, as you all know, is a cascade of layers, each of which is a composition of a linear map with a pointwise nonlinearity. Okay, so we compose linear map with a pointwise nonlinearity on layer 1, linear map, pointwise nonlinearity on layer 2, linear map, pointwise nonlinearity on layer 3. And that produces the output of the neural network. A convolutional neural network replaces the linear maps, or actually restricts the linear maps to be convolutions. Convolutional filter number 1 convolutional filter number 2, convolutional filter number 3. This filter is composed with a nonlinearity, produces an output that goes to the next layer, where it is processed with another nonlinearity, and so on. How do we define a GNN? Well, we first get these convolutions, and we rewrite them using shift operators. This is not a GNN yet. This is a CNN written in a different language. But it is also a GNN over that graph. If I want to actually define a GNN, I replace the graph. So these two slides are designed to look like a typo, but they're not, okay? So this slide and this slide are identical because nothing has changed except for the graph. Something has changed, by the way, which is that the output now is a function of the graph, right? So the graph is not useless. So sometimes when you get people like me talking in terms of representations, you know, we kind of obviate things that are important, which is the instantiation of the representation. And the instantiation of the representation here really is what we are going after. Okay. Finally, just you know, a final description here. The graph neural network, therefore, is a cascade of layers, each of which composes graph convolutions with pointwise nonlinearities. You can therefore think of the GNN as a neural network in which the maps are restricted to graph convolutions. Therefore, this is a particular case of a neural network. Or you can think of this as a generalization of the CNN because it recovers the CNN if the graph S describes a line graph. So it's an interesting observation, right? The GNN lies somewhere between a CNN and a fully connected neural network. I do want to point out something that, you know, is a personal pet peeve of mine, which is that a GNN is a minor variation of a graph filter, okay? Why? Well, because, you know, these are pointwise nonlinearities, right? I mean, we know they're very relevant in practice, but from the perspective of understanding the architecture, that's not where the magic is happening. The magic is happening, I would argue, on the blue blocks here, okay? And I think that this is a property that they share with CNNs, and both CNNs and GNNs, they scale because, in a sense, they exploit the signal structure that is codified by the graph. Okay, I spent some time talking about GNNs with multiple features, so let me just tell you that this is not a real GNN. This is a real GNN. It's one in which the inputs and outputs of each layer are not individual graph signals, but collections of features at the nodes of the graphs, meaning they are based on convolutions between signals with multiple features. But, you know, this is just to increase the representation power. It does not really affect any of our fundamental observations. Now, this is all I had to say about GNNs. We have a lab planned for tonight, and I've heard that there are several labs happening at the same time, and I want ours to be the best attended, so I decided to make some publicity. So this is the yeah. This was not a joke in any way. It's just I 100% meant that. This is the lab that we have prepared for you. So, you know, we are trying to do collaborative filtering with a graph neural network. Collaborative filtering is a recommendation system or a particular case of a recommendation system. So, you know, here this is how this describes the problem. So we construct, you know, we construct some graphs. We construct some matrix of similarity between movies, and then we pose the problem as the problem of training a graph convolutional neural network on this graph to solve this problem. So this is the architecture that I showed you like a minute ago. So what we will do in the graph tonight, actually what Tatiana Guevara will do in the lab tonight is teach you how to train a graph neural network to solve this collaborative filtering problem. We put a lot of effort and thought into this, so I hope that you will take advantage of that. Okay. So we are halfway through the presentation. Yeah, so we started at plus 13, so I am assuming we finish at plus 13, yes? Good. Huh? Okay, so plus 10. So we are halfway through. What I've been doing so far is I've been constructing the architecture. I don't know how successful I was, but I do hope that you notice that I haven't done anything very difficult here. I just say, this is a convolution. I try to justify why this is a convolution, but if you don't care about the justification, that's just an operation, okay? You know, you get your individual signal, you pass it through your neighbors, that message that was passed is passed again, that message that was passed is passed a third time, and so on. So you construct this recursive architecture. Each of these different things is multiplied by a different number. We call that a graph convolution, okay? And if push comes to shove, all I have to tell you, this works well in practice. Now, how do we construct a GNN out of that? Well, we just get the graph convolution, we compose it with a pointless nonlinearity, and we stack that in layers, okay? So, you know, that is slide 25. That's enough of a summary of what I have been doing. Graph convolution, nonlinearity, a bunch of layers. In the rest of the talk, I want to tell you about what we understand about fundamental properties of GNNs. In particular, I want to tell you a little bit about stability, and I want to tell you about transferability. Both of these require that I perform a little bit of a spectral analysis that is kind of like a Fourier transform analysis, which means that I will compute a Fourier transform. And you know, if you don't know what a Fourier transform is, you just believe that, okay, that's what a Fourier transform is. And you will focus on what are the interesting properties that we can infer when we look at these filters in the spectral domain. Now, but let me talk first about equivariance. I mean, there's a property, these are your 3 minutes, Fede. There's a property that GNNs have, which is called permutation equivariance, which people make a little bit of a big deal about this. Actually, I heard this from my friend Joan Bruna. He tells me, don't talk too much about permutation equivariance. People overdo it. But that's what permutation equivariance means. It says that if you permute the graph, you permute the output of the GNN. It's kind of like a trivial thing to say, actually. It says that if you relabel the graph, you are relabeling the output of the GNN. Okay, so there's the equations there, but just look at the pictures. I mean, you give me this signal here, you process that with a GNN, you obtain this output. If I relabel the graph, you just relabel the output. It's kind of obvious that the GNN will have that property. But that property is actually more important than you think it is, because it's the property that is allowing you to exploit the symmetries of the graph. Because sometimes you have graphs that can be permuted onto themselves. Okay, like in this particular example, right? I have kind of like rotated this graph, and as I rotate this graph, that's a permutation, and the graph doesn't change. And therefore, you can learn to process that signal when you are given this signal without ever having access to this permuted signal, right? And of course, you very well know that this is the same property that convolutions in time have. When you process convolutions in time, you know that they're equivariant to shifts, and if they are equivariant to shifts, you can learn to process shifted signals without ever seeing them, just by seeing one version of that copy. But the reason why we shouldn't make too much of permutation equivariance is that in reality we don't have graphs with this level of symmetry, but we do have graphs that are kind of close to symmetric. Okay, so we have graphs in which some pieces kind of resemble some other pieces. Some parts of the graph kind of resemble some other parts of the graph. And by the way, it's the same situation in time, right? So you know, like a shift in variance is not a big deal. What really is a big deal in convolutions is that, you know, when you process this signal and when you process this signal, the outputs are close. Okay? So in a nutshell, what I mean is that the real question that you would like to ask is that of stability. Meaning, if I run a GNN or a graph filter on this graph, how close it is to the output that I would obtain when I run it in this different graph. This is one of those cases in which understanding the question is the most difficult, right? So what I was saying before is something like this. So graph neural networks are obviously permutation equivariant. That means they're impervious to labels. I mean, which, yeah, good for you, but so what? Well, the so what is that if you have a graph that is symmetric, then you learn to process things without seeing them. Unfortunately, that is still good for you because graphs are not symmetric. But graphs are sometimes kind of symmetric. If they are kind of symmetric, then the question is, well, is the output of processing this signal close to the output of processing this other one? If we have that property, then we can make claims about generalization. And that's what I will try to explain now, which is that GNNs do have interesting properties in terms of the stability with respect to these quasi-symmetries. Now, this is the spectral representation of a graph. It's just built from looking at an eigenvector projection. Okay, so if you know what an eigenvector projection is, that equation over there is obvious. If not, what you need to understand is that a graph filter is completely characterized by a polynomial of one variable. You may wonder what happened with the graph here. The graph hasn't disappeared, but the role of the graph is to instantiate this function at different points in time. Again, if you understand what an eigenvector decomposition is, this makes perfect sense, but if not, you can still understand this. Because what's going on is the following. I am saying my graph filter in all of its complexity is determined by that polynomial, okay, which is just a polynomial of one variable. What is the role of the graph? The role of the graph is to get this black function and select the eigenvalues at which this black function is instantiated. Okay, now when that happens, you encounter something pretty sweet. Actually, pretty bitter, I should say. Consider, for example, a simple case of a perturbation in which you just get the graph and you scale it by a factor epsilon. Just, like you tweak its edge by a very little amount. What happens is that the eigenvalues of this tweaked graph, they move in proportion to their value. And that is good when you look at the small eigenvalues, but not when you look at large eigenvalues. And this is a fundamental property of convolutions, I should say, a universal property of convolutions. This happens on CNNs as well. It happens on group neural network, on group convolutions, if you know what group convolutions are. Whenever you have a convolution, these convolutions are unstable to perturbations that tweak high-frequency components. What do I mean by that? Well, you can have small perturbations in the original domain that will get these high frequencies, these large eigenvalues, and they will move them a lot, even if the perturbation is very small. If you want to avoid this problem, you need to have filters with this form, because here in low frequencies, the eigenvalues don't move. Here in high frequencies, the filter doesn't move. But if you don't do that, and you say, well, let me design a filter to isolate these two features, right? You may have good reason for that. By the way, if you know anything about control, you know that my consensus problem is about isolating some eigenvalue. If you look at all of these problems that I describe on cyber-physical systems, they're about changing the eigenvalue composition of the output signal relative to the input signal. So it is not meaningless to manipulate the spectra. But anyway, so you decided to isolate that feature. That's good, right? When the graph moves, you're still able to identify the feature pretty well. You then said, well, I'm going to isolate this medium frequency feature. That's still not a big deal, right? Because it has moved quite a lot, but you still capture it with your filter. However, when you look at high frequencies, you completely missed the feature after the graph is perturbed. And this is kind of a catastrophe, right? Because these graphs, we don't have them. These graphs, we measure them. These graphs come with errors. So you train on some graph. When you turn around to execute it, you are executing on a different graph. In these examples that I show you, where you have robots moving, the graph is changing over time. Right? And what I'm telling you is that if you're isolating frequencies, if you're isolating features associated with high eigenvalues, your filter will always be unstable. It will be incapable of processing those features. Because for the filter to be stable, it has to have this shape, right? So it has to be flat at high frequencies. But that's the reason why graph neural networks are useful, actually, because they will scramble the spectrum. So this is just a numerical simulation. I took this signal here. I isolated these two eigenvalues, and I then computed the spectrum of these two eigenvalues after passing them through a pointwise nonlinearity. So let me go again, right? So I isolated these high eigenvalues. So I can do that with a filter having this shape. I then pass that through a pointwise nonlinearity, and I end up with something that looks like this. And what is relevant about this is that now I have some crap in low frequencies, but that's okay. I mean, that crap is crap that I can now identify in a stable manner. By the way, I'm not going to explain this, but I am showing you pictures. I do want you to know that we have an actual theorem substantiating this picture, so that's fine. I mean, this theorem says what the pictures say. I don't want you to read it. I don't want you to understand it. It's just to show my credibility. I'm a very unsecure person, let's say. Now, I'm going to talk about transferability in the last 10 minutes of the talk, okay? But I think it's a good time for me to give you a summary, right? Because I've been talking for 40 minutes. You are likely somewhat lost. You say, what's this guy saying by now? But this guy is not saying anything that is that difficult to understand. So let's see if he can do a better job of explaining the important concepts here. The first important concept is the architecture. Remember, the title of the talk was Graph Neural Networks, Architectures, Stability, and Transferability. Well, that's the architecture. It's pretty simple, right? So we have a graph convolution followed by a pointwise nonlinearity. We stack several layers. What are these graph convolutions? Polynomials on a matrix representation of the graph. And by the way, you can learn more about this if you come to the practical session tonight, which I am pretty sure is going to be pretty exciting. I then told you about equivariance and stability. What did I tell you about equivariance? Well, that you are invariant to permutations. But I'm going to rely on Joan's advice here once again and tell you, permutation equivariance is no big deal. It just tells you that if you relabel the graph, you relabel the processing. So what? Well, I mean, the so what is that you can have graphs that are symmetric, and in that case, you learn to process things that you have never seen. Same as happened with CNNs in time. But in reality, you don't have graphs that are symmetric. You have graphs that are quasi-symmetric. And okay, I did some analysis here, but the conclusion of this analysis is, the most important fact about this analysis is summarized in this picture, I think. It is possible that you move your graph just a tiny little bit, and your filter moves a lot. This is not a GNN, this is just a filter, right? It's one of these blue boxes in the GNN architecture. It can happen that your graph changes by epsilon, but the filter changes by an amount that is not epsilon. Your filter changes, your graph changes by epsilon, your eigenvalues change by epsilon times lambda, which results on h of lambda changing a lot, unless h of lambda is not discriminative at high frequencies. So you are in this world. It is impossible, which means the following. It is impossible for you to have a filter that is discriminative and stable at the same time. This filter is discriminative and stable, but that's because I'm in low frequencies. This filter is discriminative and stable. That's because I am in medium frequencies. If I am at high frequencies, I can be discriminative or I can be stable. I can't be both. And that follows from an eigenvector decomposition. It follows from a frequency representation of filters, which you don't really need to understand this to understand this talk. You just need to understand this. Low frequencies, I can be discriminative and stable. High frequencies, either discriminative or stable, not both. The GNN, however, can be both discriminative and stable because the pointwise nonlinearity scrambles the spectrum between one layer and the next. And I do want to emphasize that this is a property that is true of graph neural networks. It's also true of CNNs. It is also true of group neural networks. It's actually true whenever you have a convolution because all of the things are algebraically equivalent and the eigenvector decomposition is an algebraic object, an algebraic property. Now to conclude the day, I'm going to go into the third topic of the talk, which is transferability. Now transferability is, I think, the coolest and most underappreciated property of GNNs. So please bear with me for 10 minutes. A GNN that has been trained on a particular graph S can be executed in any other graph. Okay, because when you train the GNN, you're training the coefficients. You can change the S. Of course, you don't necessarily expect it to work, right? But if the graph S and the graph S hat are close, you should. But in particular, you can train it in a small graph and execute it in a much larger graph. So this is the idea, okay? So here I have a movie recommendation system trained on a small number of movies. Here I have the same movie recommendation system trained on a much larger number of movies. And you get performance curves that have this shape. Here I am training on 600 movies and executing in 2,000 movies. That's the performance that I obtain in 2,000 movies. Okay, so I trained in 600, but the point here is the performance when I execute in 2,000. You see interesting behaviors here, like, once you train on 1,000 movies, the extra level of performance that you have to gain is very minimal. So it seems that you can get away here with something that is computationally quite remarkable, which is training on a graph which contains half the number of nodes of the graph of interest. Here you have the example of flocking. So you observe a similar behavior. So this orange curve here represents the performance of training in 40, executing in 90. And again, you can see once you train on something like 50, there's very little extra performance to be gained. Okay. Now the question is, when you, well, we are scientists, right? When you observe a behavior like this, the question you should ask is why? And yeah, nothing. No, you're helping me. I mean, I'll buy you a beer later for putting up with me. Yeah. No. I want to ask you a question, Ignacio. Right. So the question of why is justified. I mean, this is an empirical observation, right? I mean, scientists, when they see empirical observations, they should ask why. They should explain the phenomena, right? Do you know why this happens? Now, what is interesting, Ignacio, is that, I'm of course teasing you a little bit because, yeah, I mean, why would you know this without, me telling you the answer or Luana having told you the answer? But you do know the answer because it's the same behavior that we observe in images once again, right? So we know that after a while, images don't really have any more information. So what I'm doing here is I am extending or I am changing the number of pixels in the image. When I get from this image to that image, maybe there's a little bit more of resolution, but really there's no more information. I mean, you can perfectly identify this leopard sitting on a branch, on a greenish area, just as well from this picture as you can do from the picture on the left. Okay, so there's two things that are happening in here, right? So the intrinsic dimensionality of the problem is less than the actual size of the image, right? And actually, the filters transfer, right? I mean, your convolutions transfer from low resolution to high resolution. We should ask the question of whether the same thing happens for graphs. And in order to do that, we introduce this concept of a graphon. A graphon is a limit object of a graph, right? So 50 nodes, 100 nodes, 200 nodes, an infinite number of nodes. So here you have a recommendation system with 30 products, 50 products, 100 products. The graph is converging to a graphon, but the question here is, are graph convolutions converging to the graphon convolution? Make sense? This is not a given, right? So let's go back. The image is converging, but are convolutions converging? You know that they are. I mean, that's called the sampling theorem. But now, you have your graphon convolutions. So you have your graph and graphon convolutions. The graph converges to the graphon. Is it true that the graph convolutions converge to the graphon convolution? The answer will be yes, and it is given in these two papers. In order to explain this yes answer, I'm going to do that very briefly and very quickly. We define graph convolutions. Actually, I already showed you this shift register diagram before. Here I have the equivalent of this shift register diagram for graphons. This is converging to this, is this operation here converging to that operation? The answer is yes, but somewhat surprisingly, or maybe not surprisingly, you also have some spectral challenges, which in this particular case, they manifest for eigenvalues that are close to zero. Those eigenvalues that are close to zero in the graphon, they accumulate, and that makes it, again, difficult to have filters that are discriminative and transferable. So I know that I am just flashing this slide, so I just want you to learn the relevant fact that follows from this slide, which is that, yes, we can transfer graphs from, yes, we can transfer graph neural networks from small graphs to larger graphs, but we can do that only at the cost of losing discriminability. And this loss in discriminability is again explained by looking at the frequency domain. The graphon eigenvalues are a discrete set because the graphon is a bounded operator. Yeah. There's a theorem again. That's my, unsure Alejandro here, or Yeah, anyway, so we have theorems that show that this plot says what I told you it says. Now, finally, just one last thing, right? So, okay, so we have achieved transferability at the cost of discriminability. What about if this discriminability is important? Well, here is a beautiful idea, which is that you learn through transference. So you start training in small graphs, and as you approach convergence, you start growing the size of the graph. So you start training with 100, then after a while you start training with 1,000, after a while you start training with 10,000, but you don't start training your graph, neural network, directly in a graph with 10,000 nodes. So this is a way of achieving both discriminability and reduced training cost through the exploitation of transferability. Now that is all I had to say, so these are my concluding slides. So I did show you graph neural network architectures, which are compositions of graph filters with pointwise nonlinearities. If there's nothing else that you will remember for me, remember polynomials, okay? Because the compositionality really is what this talk is about. Now these graph filters I showed you were stable to deformations, and they were transferable under some conditions. And both this stability and transferability analysis hinges upon spectral representations of graph filters. So if you don't know what spectral representations of convolutions are, well, I hope I gave you a reason to study them. That's all. Thank you. And I'll be happy to take your questions.
We have time for questions, but first I have one question is, how many miles do you walk in your standard course in Penn, for example?
Yeah, I know the answer to that question. Yeah. In a 1 hour lecture, I do 2,000 steps.
Great.
Yeah. I know that because Apple, yeah, yes, Guillermo.
We have a question there?
Yes, thank you, Alejandro. Very interesting talk. I was wondering if, like in the complex network, complex system domain, okay, in the physics field, the underlying topology of the network, of the graph, okay, have a high effect on the dynamics, especially in diffusive dynamics. And I was wondering if in graphical neural networks happen the same, especially for transferability. I mean, a small network must maintain the underlying degree distribution of the bigger network.
Yeah. So that's an excellent question. When you know, there's a literature in complex networks. Is I wouldn't call it physics anymore, but it was developed by physicists. And in that theory, there's quite a lot of emphasis placed on the spectral properties of this graph, right? So in particular, there is evidence that a lot of graphs that appear in nature, they have this small world property, right? And the small world property in the spectral domain, what it means is that eigenvalues are very concentrated, okay? So small world networks are the kind of like the worst kind of network that you can have for you to process with a graph neural network. You go back into the nodal domain, and this makes plenty of sense because you have some local connections and also some long-range dependencies in these small world networks, correct? And yes. The GNN, or the graph filter, is treating both of these two connections in the same way.
Okay, thank you.
Yeah, so I have a very similar question about I'm here. About the structural properties of the graphon, like the limiting objects. So can we say anything about like whether the graphon is sparse or dense?
Yes. Well, this is another great question. So you're actually catching me in a small lie, perhaps. So we are constructing limits here, and our limits by choice are graphons, right? So graphons have the following property. As n goes to infinity, the degree of each node is going to infinity as well, which is a property that you would be hard justified to say holds in practice. In the case of the recommendation system, for example, that hypothesis is justified. As I keep adding more people to the recommendation system or more products, there are more things to which I am similar. In the case of the physical systems, it's clearly not true. Which begs the question, yes, can we derive analysis that hold for sparse graphons? And the answer to that question, because I mean, I'm assuming that you know what a sparse graphon is given your question. I think that Soledad has a paper to recommend to you. Yes, you can talk, you know, Soledad has been studying this problem, so you can derive similar results for sparse graphons, because really what matters is what's going on in the spectral domain. So if you have a different model for your limit, you just need to understand what that different model implies in the spectral domain, then the rest of the analysis is pretty similar. Thank you.
I have a question regarding the multiplicative change that you performed to the eigenvalues. You were doing this 1 plus epsilon change in lambdas, and I'm curious what that looks like in the actual graph. So you change how the eigenvalues change, but not really how the graph.
Right. Yeah. Great question. I went through that very quickly. The change is not in the eigenvalue. The change is on the graph itself. I get the graph and I multiply by 1 plus epsilon. I go into each edge and I multiply the weight of the edge by 1 plus epsilon. Or if you wanted to have like a stochastic model, you said, I'm dropping edges with probability epsilon. Yeah. It's a very small change on the graph, which translates into not a small change in the eigenvalues. That's the critical point. The graph changes nothing, but the eigenvalues change a lot. Therefore, the filter changes a lot. Make sense? Thank you.
Hi, so thank you for here. Okay, so I have two questions. Actually, they are related one to the other. So regarding the transferability, like property, there is a minimum size at which the graph should be, capture the discriminability, right? So as to transfer to a bigger graph, right?
Yes.
If I understood correctly.
Yeah. Of course. I am calling it transferability because of the practical implication that you can train in N and execute in M. The actual result mathematically is a limit result, which means that we compare against the limit, which means that you need to be sufficiently close to the limit. The convergence rate is 1 over the square root of the number of nodes.
And the other question that is related to that is that I think what I assume, according to your presentation, that I cannot go from higher graph to a smaller graph. Is that possible or is that not possible?
You can go from a large graph into a small graph. Yes, that would be transferability going in the opposite direction. And there are practical reasons why you will let you do that. I think that you have some of them in mind. Yeah.
Okay, great. Thank you.
Yeah. Yeah, you can ask me. You can ask me later. I am a professor with a particular quality that I like to talk a lot. And I have to say this because present in the audience is my son Guillermo over there. Yeah, that guy. Yeah. He's a chemical engineer whom I dragged here, and he has given me always this criticism that the problem you have is that you talk too much. That's a true story, isn't it, Gisha? Right now.
Thank you very much, Alejandro.
Yeah, thank you, everyone. Thank you.
Now we have the sponsors talk. Please don't leave. Joao, where are you? Is there people sitting in the stairs there? We have room in the middle. Please let them be in the middle of the room. Go. Here's water for you. The glass. Do you have HDMI?
I have what, sorry?
HDMI.
Yeah.
Okay. Hi. Hi. Yep. Okay.
Okay. Are we here? Okay, we're going to start the... Silence, please. Thank you. We're going to start the sponsors talk. Now we have Joao Araujo from Cohere. Joao is a machine learning staff member in Cohere, where he has worked with several topics in natural language processing and large language models. He's fascinated by reinforcement learning and is interested in how artificial intelligence can be leveraged for the greater good. He has a bachelor's degree in computer science from Universidad de São Paulo, Brazil. Thank you very much, Joao.
Hi, folks. Let me just see if this works.
Did you cast it recognized?
Yes, yes.
¿Recibís audio?
Yeah, I don't. Okay, maybe. It's kind of working. Yeah. Okay. Okay. So yeah. Hi, folks. I'm going to be talking about Cohere's multilingual embeddings. So who am I? As I said, bachelor in computer science from Universidad de São Paulo, and I've been at Cohere for 2 years, kind of MLE or RE, somewhere in between those. And okay, who are we? Well, Cohere is a natural language processing startup. Our main focus is trying to bring NLP to all developers, from people that are like, okay, what the buzz is about, how can I get my software to understand language and help folks, to more advanced users who understand the deep arcane arts of prompt engineering and parameters and all that. Okay. So what we do is we serve an API that gives access to our large language models. We have many cool endpoints. There are many more other cool endpoints coming up in a couple months. And so today I'll be focusing on the embed endpoint, because while Generate is also very interesting, right now Generate is English only, while our embed endpoint supports over 100 languages. So we support English, Portuguese, Spanish, French, and another 97 or so. So yeah. So just a quick recap on what Cho said. So the idea of embeddings or contextual embeddings is that we want to get an input text and generate a vector that represents the text. We want the vector to somehow represent the meaning of the text. So similar inputs should generate close vectors. Dissimilar inputs should generate vectors that are far away. Okay, so here's a quick example of, like, imagine we have a bunch of texts and we want to plot them based not on the context, but on maybe vectors from each word, or maybe a bag of words, or basically using the words individually instead of taking a look at the whole context. So you see here that, for example, Apple iPhone is close to Apple is my favorite food, and close to the golden apples in the garden of the spirit. But it's far away from Samsung's Galaxy. But like an iPhone and a Galaxy are very similar in some sense. But if you change from this like word per word and use contextual embeddings, then you could get something that makes more sense. And now Apple iPhone is close to Samsung's Galaxy, and now we have that apple in the sense of a fruit, close to apple in the sense of baking a pie and stuff like that. So now stuff make more sense. And let's go for the demo. So what I'm showing here, is a cross-lingual semantic search demo. It's powered by our API, and you have like this huge database of facts and articles. And when you search something like how is the weather in Uruguay, we will compare what happens if you just do like a lexical, so word-based search using Elasticsearch. So here you see that I asked, how is the weather in Uruguay? And it goes like, okay, here's the article about weather, here's some random stuff. Here's the article about weather, here's more random stuff. But when using the semantic search, it understands that I want to go to Uruguay and say, okay, how's the weather here generally? And even more importantly, since the embeddings are multilingual, I am doing the question, I'm writing the question in English, but I am getting the results in Spanish, again Spanish, and I also like German and all other stuff. And so that's the general pitch. So you can use one language and get results in a varied amount of languages, and you can get things that make sense in the whole context and not just word per word. So yeah. No, this is not the final yeah. Does anyone want to like test something or? No, no one wants to test anything. Okay, yeah, so I guess I'll just finish it up. So yeah, please join Cohere's community. Here you can like chat with folks from Cohere and with other users and learn more about how to use our APIs and stuff like that. And also, please take a look at Cohere for AI, which is like our research lab, or more like a research lab that Cohere is supporting. And yeah, thank you very much.
Thank you very much, Joao. Please, Fabricio, if you want to go. We have time for one question here, Omar. Sorry, it's a closer one.
A great representation. Very quick question. In a world where we are surrounded by toxic language, for instance, how contextualizing the language can help us to actually retrieve what is similar, but actually is not toxic or is unhealthy?
So, like, you mean you would like to ask some question and get a result that's non-toxic? Yeah, so you could try to, you could try to, for example, use the contextual vectors that, as I said, represent meaning to specifically filter out toxic content. So that would be something that you could do.
One last and fast.
Hi, thank you for your presentation. I just want to know if you have support for any American indigenous language like Guarani, Nahuatl, or Quechua, or something like that.
I can't say for sure.
Okay.
Sorry, the list is very long. I would say it's possible. Yeah.
Okay, thank you.
Okay, let's thank Joao again. Now I'm going to introduce you to Fabrizio Scrorini from ILDA. Fabrizio Scrorini is the Executive Director of the Open Data Latin America Initiative, ILDA, and member of the Open Data Network for Development. He co-founded AbreLatam and the Open Data Regional Conference for Latin America and the Caribbean, and is one of the lead stewards of the International Charter of Open Data. He worked with governments, regulators, and civil society at international and regional level on transparency, access to public information, open data projects, and public sector reform. He holds a PhD in government from the London School of Economics and Political Science. Fabricio, welcome.
Thank you very much. So good afternoon, buenas tardes, boa tarde, sejam bem-vindos. We welcome to Uruguay. Please rise, 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 arriba, 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 arriba. Muy bien, excelente. Lo segundo que vamos a hacer ahora, the second thing we're going to do now that we are all up, is to stretch. You stretch like this. Yes, yes. You can feel it. Yes. You can also yawn. Oh, yes. Excellent. Now you can sit. I'm the last man between you and the cup of coffee, or there's someone else? I think. There's someone else. So, okay. So we'll make it quick so your pain is less. So my name is Fabrizio Clorini, and at ILDA we explore the use of data for development. We have been doing this for the last 10 years. We were born out of the open data revolution, let's say, and we can discuss whether this was a revolution or not, but we are still trying to open data for the public good around the world. What I'm here to show you is actually to propose you three questions, two questions and one assertion, actually, that data is now a central active for economies and societies in our world. This is the reality. So what is the current state of the art in terms of data in the global south? And can data-intensive technologies, for example, Gracia, machine learning technologies, contribute to solve public issues? And if so, how? And as you probably know by now, all those beautiful algorithms you help to create are as good as the data you have. And if you don't have such data, I'm afraid that that beautiful machinery that you are developing won't be able to deliver. And that leads to a problem. How do we know which is the state of the data around the world? So we, and by we I mean a lot of people, developed an instrument called the Global Data Barometer, which allows you to assess the current state of the data in 109 countries in several aspects, in several fields. Some of them, and most of them are related to public data. There are 39 indicators, 60,000 data points. Go and check the Global Data Barometer. This is one of the few instruments that actually allows to provide this kind of pictures, and obviously it's a very imprecise and experimental instrument. But the crucial element is to put in value that data has to be available in certain conditions in order to be properly used. This is the current reality in the Latin America and the Caribbean according to this instrument that has essentially 4 dimensions: governance, availability, capabilities or capacity, and impact and use. By governance, we mean the institutional framework which allows you to access data. And to many of you that are probably wondering how to get data, a few of you probably use access to information laws or similar to that to get databases. Others, are wondering with privacy regulations whether you can access data or not. Others might not have regulation at all. And so you wonder, like, what is the kind of regulation that you need to think about? And that's the governance aspects. The availability, whether you can access or not. Whether societies are able to appropriate the value of data to democratize its use, and this is very linked to the capabilities. I mean, we are very fortunate here in Khipu because of the great job the organizers have done bringing together this amazing Latin American community of very, very smart people. But we live, at least in Latin America, in one of the most unequal continents or regions in the world. That means that not all parts of our societies are able to benefit for the work you are creating. And obviously, impact and use, we want good cases, right? This is not just about prototype. We want this kind of technology to expand and so on. And that is connected with use and impact. In our search, we also have produced policy brief, essentially trying to inform, trying to support policymakers in developing artificial intelligence policies in Latin America, with little success, I might add. But we still do that because we think it's important to structure this in the right way and to actually create a Latin American view of the right kind of policies these countries need so your work can scale, can expand in a fair and in an accurate way. At ILDA, we have also done our fair share of work exploring the use of AI for the public good in the public sector. So there's a bunch of projects that you can find in our Empatia website. Some of them in the justice sector, trying to understand how and if AI can help the judiciary to draft better decisions or to inform them. Monitoring the public expenditure in several countries in Latin America or the public budgets, or actually understanding more about the air quality and so on. The key element we found out, regardless of the technical specificity of these projects, is maybe the need in some of the areas, or the public areas, to co-produce AI or to co-produce machine learning technologies. This actually represented here in this beautiful drawing by my colleague Sophia has to do a bit more about what kind of problem are you trying to solve and developing an iterative process in which you are able to develop the right technology for the right problem. And at the moment, you know, this is not happening. At the moment, what we have in Latin America are a bunch of vendors shopping kind of, or shipping kind of solutions that are not necessarily tailored for the problems that they are supposed to address. And most of this process, obviously, a bunch of this is technical, but another bunch of this is highly about design. It's actually understanding the people and the situation in which the people are operating. And this obviously is also about domain expertise. And that remains, you know, a challenge. This is, you know, machine learning is not just about the technical aspects, but also the design, the policy, and the problem aspect. And so you can read, of course, about this guide. I'm running out of time. By now, you are probably aware of the challenges that our democracies face. We were very successful at undermining our democracies on our own. But with the machine learning technologies we are now developing, that can scale quite fast. And this is part of the challenge that we explore, and we try to bring a critical view and to reflect on this. And so we are really, really happy to have these conversations here in front of a technical audience. We have a few recommendations of the way forward for AI in Latin America. Some of these recommendations are about more education, more inclusion, better data governance aligned with human rights principles, and of course, cross-cutting diversity and inclusion policies. But I will leave that to invite you to the next AbreLatam con Datos here in Uruguay as well, in Montevideo, in November, where we hope to see some of you. And on that note, to thank you for these minutes, to congratulate the amazing team here at Khipu, and to invite you to reflect on these critical issues for the future and the future you are going to build. Thank you very much. Muchísimas gracias.
We have time for one question. One question? Yes.
Hi, very nice presentation.
Hi, thank you.
I would like to know what kind of relationship have you built with any of the governments in Latin America? Have you had like any transference of the knowledge that you have built?
Yes, the Uruguayans are quite nice, and they usually work with us, but this has been quite of a challenge for us. Like, in essence, we engage governments in a constructive way. We engage them in order to transfer all this knowledge the best we can. And so, for instance, with the Uruguayan government, we developed AI courses that are targeted for the public sector. We did that as well with a bunch of international organizations like ECLAC and the Organization of American States and so on. But the problem here is that at the moment, a bunch of governments in Latin America, they don't really have a clue of where to go. There's not such a thing as a Latin American view on AI. And so part of our work at the moment is actually to help to so these governments are able to understand what's at stake here. Because the other problem is that many governments don't know what the stakes we are having in this field. So that's part of our challenge at the moment. So we engage them in forums. We try these relationships to be constructive, open, but also, if necessary, critical.
Thank you very much. Let's thank Fabricio again. Thank you. And now we have Pablo Brusco from SAAPP. Pablo is a researcher scientist at SAAPP, where he specializes in speech processing. He's also a member of the Applied Artificial Intelligence Laboratory at the University of Buenos Aires, and an adjunct professor in the Department of Computer Science at the same institution. Pablo earned his PhD in computer science from the Institute of Computer Science at the University of Buenos Aires, where he studied spoken conversation using machine learning techniques. His research has been published in academic journals and has contributed to the advance of the speech technology. Pablo, you're welcome.
Thank you very much. Do you hear me well? Yes, okay, thank you. Thank you, everybody, for being here, and especially the previous speakers that keep you awake, and thank you for all the great presentations. So, my name is Pablo. I'm here in representation of our Khipu team. You can see pictures of us there. Probably you have seen us in our booth. And today I want to talk a little bit about what do we do in our company, and some particular AI products that we work on. So ASAP is a company that works in customer experience for contact centers, what some people know as call centers also. Every time a person reaches one of these companies through chat or through phone call, we will have AI systems working in the background that will improve the experience of the customer and the agent by a lot, I would say. So the metrics that we care about are how do we minimize handle time, how do we increase the average speed of answer, how do we increase the customer satisfaction score, how do we keep track of the customer satisfaction without asking the customers to fill out a survey or something at the end. So those are the type of things that we solve in our company. For that, we mainly provide 4 AI services called Auto-Compose, Auto-Transcribe, Auto-Summary, and Journey Insights. Today, I will focus mostly on Auto-Transcribe. Auto-Transcribe is a system that will transcribe every call in a spoken conversation. But we also have Auto-Compose, which will auto-complete the messages an agent is writing. It will suggest messages automatically. That is an NLP problem, as all of you know. And then once we have the call finished, we also have Auto-Summary, which will create automatic summaries of the call, and Journey Insights, which will analyze the whole interaction and also provide recommendations for actions, not only to what to text, to what to write in a chat. So Auto-Transcribe is translating speech into text. And we are proud to say that we are very good at it. We have been very good in the last couple of years at beating most of the companies in a particular benchmark, which is very common for the speech recognition community, which is LibreSpeech. But, and you can see the blogs, you can see the papers supporting that. But most of our work and most of our value arrives from customizing our models. Customizing, meaning that the majority of speech transcription solutions are trained on generic, unspecific, and unrelated data sets. So that means poor quality insights for the customer, right? So what we do is to provide solutions that are specifically built for customer-agent interaction. That is a domain-specific task. We continuously learn from mistakes, from feedback, from evaluations that we run. And we have a very high efficiency, high speed service that runs in real time during the conversation, so that, for example, the agent do not have to ask the customer again for the address or something, because the address will be transcribed and they will be able to copy and paste, for example. So this, we continuously measure our system. Again, other important solutions like the ones you know, common APIs, and we always beat them in our data sets. That is because we are very good at customizing. So why is it important to beat other systems in terms of accuracy? Well, the thing is that accuracy is not that important itself. We actually use word error rate, which is a measurement of speech recognition. But accuracy is not that important if you don't take into consideration the distribution of words in a spoken conversation. If you start counting all the words in a conversation, you will see that 80% of the words are very, very common, then the 90% of them are not that common, and the tail of the distribution is very uncommon, and those are the ones that the customer cares about. For example, there you can see some ID numbers and, or street names or custom entities for a particular customer. If we are not good at catching those, then auto summary, for example, won't be able to produce a great summary out of the conversation. So we specialize on that, and the way to do that is by having data, as it has been mentioned before. And we have a lot of experience in the domain. So when I first said that we beat the competition, it was kind of unfair, because we beat them in particular data sets and in the domain that we work on, which is very difficult also, right? So we have a very, very nice blog that will show most of our work, not only on ASR, but in other technologies. I really encourage you to just go into the ASA blog and scroll. You will see things like language models, you will see things like speech modeling, like evaluations of systems, that data science apply into our problems. It's a very, very complete page with a lot of examples and pointers to the papers. So that's it. You can reach us on those email addresses. You can search for the open roles in our webpage. And also I encourage you to visit our booth, our stand. Also to visit our Khipu poster on speech sentiment analysis. And on Friday we have a talk in the industry panel by Nicolas Dipolito. So I really encourage you to attend to that. Thank you very much.
Thank you very much, Pablo. One question. We have time for one question before the coffee. There's no coffee, there's no question. I do have a question.
Yeah.
How much data, don't worry, we have coffee. How many data do you need to customize to a certain domain or customer or client?
Yeah, lately we have been trying to scale up to support many customers, and that is making us having the need of less and less data over time. So at the beginning, I would say we need at least 1,000 hours of conversations to have something that works. But today, with 50 hours, even less than that, of transcribed speech with some particularities will be enough. And that is due to the improvement in the processing and the fine-tuning and all the technology that we bring from the papers into the product, right? So more or less, that is the answer.
Thank you very much.
Thank you.
No question. Thank you, Pablo, again. So we have a coffee break now. Let's try to be back in 25 minutes. That's okay? Thank you.
Hi. So it's my pleasure to introduce Gonzalo Mateos. Gonzalo Mateos is an assistant professor of the Department of Electrical and Computer Engineering in University of Rochester. He's also a member of the Institute of Data Science and has a secondary appointment in the Department of Computer Science. Gonzalo got his bachelor's degree from here, Universidad de la República. Since then, he has maintained a very intense contributions and collaborations from courses, students, as well as very research collaborations. Gonzalo has a very prolific research production and has received many awards. For instance, the NSF Career Award. His research interests lie in the areas of statistical learning from big data, network science, graph signal processing with applications to dynamic network health monitoring, social power grid, and big data analytics. Please welcome Gonzalo Mateos.
Well, thank you, Pablo, for the very kind introduction. I'd like to thank everybody for sticking late today. My, again, deepest congratulations to the organizing committee for putting this amazing event together. I heard how much work it takes, and yeah, it's amazing that this is happening, seeing so many people personally. It's always great coming back home, seeing some familiar faces, good old friends for many years, and looking forward to making new friends during the course of this week. So yeah, very happy to be here. I'm gonna be, again, I have this title, maybe saying too much, Graph Neural Networks in Action. It's the second part of what Alejandro presented early on. He did an amazing job, and again, I'm glad to be GNN too, because a lot of the motivation and, I don't know, the why, the how has been already, you know it. So I'm just gonna try to, my goal today is to kind of give a little bit of a high-level overview of the breadth of applications and diverse domains where studying and learning from network data can be actually important. And that's something I've been doing in my research with my group for several years, and that's kind of something that fascinates me, actually, that network science and the learning from graphs. Graphs are kind of all over the place, as Alejandro showed, and then you can see basically elements and interactions. Namely, a graph is relational data. We collect it more and more frequently today, coming from all across various disciplines, all the way from molecules, so then you can work with small graphs, for instance, but then you can have very large graphs like online social networks, you have infrastructure networks, communication networks, the brain in particular, and maybe even fancier structures like knowledge graphs, where you have multimodal elements, multi-relational interactions. So then things can get heterogeneous and then as complicated as you want, but I hope this at least slide conveys that kind of the diversity of application domains where these problems and learning from network data can be, of course, important. Now, again, I just can go quickly over this material. I kind of have these slides just for completeness, assuming that people maybe then are going to look at the slides eventually. I'm assuming this is going to be shared through the Khipu website, but again, we know very well we've had amazing talks on natural language processing, computer vision, and beyond. Clearly, if you are here and you, I don't know, if you follow Twitter, you see like there's a new amazing model today in half an hour, maybe another one, and so forth. So then we become kind of pretty good at learning from data in regular domains or grid domains, namely speech or time series, for instance, using various types of architectures, also grids, namely images or video as well, using convolutional neural networks, and so forth. So now that the challenge clearly is what happens, how can we learn from network data, with the challenges that Alejandro actually mentioned and addressed, right? Things that we typically take for granted, right? To define a convolution, a translation, right? That's not obvious when you're thinking in a graph. You don't have a regular grid grid structure, if you want to move up, down, or left, what does it mean? Because neighborhoods are typically very regular. Some nodes might have a few neighbors, and another node might have a bunch of other. The names kind of are changing. Graphs can be dynamic. There's heterogeneity in connectivity patterns. So clearly, things that sometimes we took for granted then have to be re-examined. But as Alejandro said, the generalization is not quite such thing, right? So then we can figure things out, and because, for example, the time domain, those are graphs nonetheless, so then we can naturally extend convolutions and graph neural networks to work with this type of data. So then, before I just give a brief recap of what we learned on GNNs, let me start by just going over the notation. This talk, as I said, is going to be very much high level, so not a lot of mathematics, more a focus on applications and then the history of how we got there. But I just have a few symbols I'm going to be using throughout. We're going to be working with graphs, of course, a set of elements or of interest. That's the vertex set V connected with edges, right, which are ordered if you have a directed graph, or unordered pairs of elements in the vertex set. And we can encode, right, that topology in what we call an adjacency matrix. Matrix that has number of nodes as columns, number of as rows, excuse me, number of nodes as columns, and then we encode, right, entry Aij, for instance, in that adjacency matrix. It's to some extent strength of a level of relations between nodes I and j. And the graph could be weighted, capturing that continuous strength value. Could be binary if you want, just saying there's a connection or not. And we can have variants of that, directed graphs, undirected graphs. We're going to keep it kind of general, always looking at the simplest types of examples here. And then also important to define is the neighborhood of node I. For instance, there, node 1 has neighbors 2 and 3. The set of nodes that connect to a given node, that's the neighborhood. Now, important also in learning from network data, and again, in data sets of relational graphs, we often encounter signals or attributes defined on the nodes of the graph. And that's my vector x over there. Its length is, again, the number of nodes as well, assuming I have a scalar value per vertex. For example, if you have a molecular graph, then nodes could be the atoms, and I could have a feature, for example, what type of atom it is it a carbon, a hydrogen, and what have you. But of course, we can think of more general feature vectors of length f, say. If you're thinking of a recommendation system, then maybe for a different product, you have in the catalog, you can have different features, how much people liked it, and then, I don't know, if you are I'm going to be talking about tennis rackets or tennis balls as well. You can have the brand and so forth. So then you can conceive that there's a bunch of features associated to different elements in the graph. And in that case, I'm going to have a vector xi per node. I can collect my features or my signals in a number of nodes, n, let's say, times f matrix. We could also have features tied to the edges of the graph, conceivably. That's perfectly fine. Many of these results I'm going to be mentioning here, or applications actually are going to leverage those, also message passing or aggregations on edges. That's perfectly fine. And then finally, for many of the tasks I'm going to be discussing today, we often have, if that's a supervised task, we're going to have some labels tied to different objects of interest, depending on the task we're going to be conducting. Maybe node classification, then we have node labels, maybe graph classification to classify properties of molecules. We could have labels in that vector or matrix Y tied to the particular object of interest, right? So then that's my notation in a nutshell. Just to recap what we saw in the previous talk, in a nutshell, right? Alejandro argued, GNNs basically are minor variations of graph filters. We just interleave nonlinearities with graph filters, and we compose those over multiple layers to obtain a deep learning architecture for processing signals on graphs. Things to notice here, those graph filters, again, and thinking of scalability and convolutional filters, the number of parameters, right, in this very particular simple instance of a filter is basically k, right? That doesn't grow with the number of nodes. That's clearly important, different from a fully connected, for example, neural network, and that makes the scalability kind of, that's where it manifests, of course. Some other interesting properties that we observed, kind of just by construction, we have permutation equivariance, which is something that you must have, otherwise you are doing something wrong, which means that if you permute your nodes and your signals accordingly, then the outputs, right, phi of your neural network is going to be permuted accordingly. So in a way, the functions that we're parameterizing and then eventually learning should be invariant, right, to arbitrary, in principle, node labeling. So then that's some symmetry we want to actually enforce, leverage, and then that's going to give us, of course, better properties in generalization, as Alejandro explained very clearly. Now, other things we saw is like looking at graph CNNs, they exhibit a better trade-off when it comes to stability to perturbations versus discriminability as compared to just simple linear graph convolutions. And another very important property is also that GNNs can be transferred, right, across different graphs, thinking of the density matrix or the underlying graph topology that we use in those polynomials, in those convolutions, as an input as well. And as you can see there, you have a semicolon, because I'm first thinking of A and the filter tabs H as parameters in the model, something that parameters the architecture, and then the input is only X. Well, over there, I just have to the left of the semicolon, also A, thinking of A as well as an input potentially. Okay, so then that's something worth noting. And clearly, a nice point of contact that makes all this theory and all these generalization and constructions pretty satisfying in a way is that we recover convolutional neural networks as particular cases of GNNs when the graph is a directed cycle. There's other points of contact as well. It's often very common to work with covariance matrices as graphs. Many times we have signals on different elements. We compute covariances like in functional connectivity in the brain to build graphs, where in that case, processing or building up GNNs with covariance matrices as graphs, then it's pretty much related to doing principal component analysis, right? If you think about the spectral analysis that Alejandro described, looking at eigenvectors of covariances are what in a way shape up how we process our signals using these convolutional filters. Well, that pretty much relates to doing like PCA with learnable responses in a way. So then there's also connections there, and we have explored that in some recent work as well. Now, what is this lecture about? Well, building on all this we've learned, I just want to first start by giving a taxonomy or just examples of different types of tasks that we can accomplish or are kind of motivated in machine learning for graphs. And I'm going to give a taxonomy typically tied, and a bunch of examples that follow, tied to different elements in the graph. For example, we can think of learning properties of nodes or of edges in link prediction. We can learn properties of subgraphs, paths, or communities, let's say, in cohesive subgroups, or we can even learn properties at the level of a graph itself. As we said, for example, predicting some property of a molecule. Does it have an antibiotic capability or not, for instance, right? So then I'm going to start with that, and then I'm going to focus on one particular instance I mentioned, link prediction or relation learning. And with that, I'm going to kind of go back in time, maybe 20 years, and then tell us a story of how do we get to where we are today, kind of leveraging the powers of GNNs. Namely, I'm going to go back and then see how people were doing link prediction back in the day, early 2000s, working on handcrafted features, and then maybe training classifiers based on them. Then we had a revolution leading to graph representation learning, and then we find today working with graph neural networks. And then I'm going to move on and talk about what I'm calling there GNNs in the wild, given a bunch of what I believe are high-impact success stories of graph neural networks that are really important part in machine learning technologies across various disciplines, from navigation to drug repurposing or finding, predicting side effects of pairs of drugs, or just actually state-of-the-art recommendation systems that are run by Amazon are actually leveraging, for instance, GNN. So I'm going to give you also a bunch of examples just to show how these are really impacting our world today in real-world applications, and I have some concluding words to wrap it up. So then that's kind of the story for this talk. So let me just start looking at these canonical tasks and this taxonomy, and as I mentioned, this can be traced to the different elements and aggregations of those in a graph. So you have nodes, of course, you have edges, and then you have, as I said, subgraphs, maybe communities or paths, or even the graph itself. And at all those levels, one can think of tasks that relate to prediction of particular properties of those elements. Again, going to more basic things like graph visualization or pattern discovery. Arguably, there might be machine learning or not over there, but then that's an important task nonetheless. Very active area of research now. I'm not going to focus too much on that today. It's clearly graph modeling and generation. You have generative models talk this morning, then the question is how can we extend those successes to generate graphs? And these are discrete objects, so then one has to be careful. The problem is challenging, but of course there's a lot of applications that motivate that. For example, generating new molecules after learning from a distribution of such molecules that have some properties. Can we synthesize, let's say in silico, new ones that have maybe some desired properties that we cannot just come up with through experiments or could be time consuming in the lab? So then really that's very well motivated. Of course, classical unsupervised problems for which there's also supervised versions of community detection, identifying groups of nodes in the graph, namely clustering of vertices in the graph such that they typically exhibit high cohesiveness among themselves, like high edge density versus sparse connections across different type of groups. And then applications could be finding social circles, identifying people with common interests to kind of deploy a marketing campaign to target them with a particular product that we believe that all of them will appreciate. And then finally, as I said, going to more, again, maybe the most classical problems, you would have classification or regression at the level of nodes. For instance, can we identify a protein function from physical bindings from a protein-protein interaction network, for instance? Can we identify fake accounts in Twitter? All of those are instances of node classification problems where we want to leverage the graph structure to successfully carry out that particular task. I haven't read over there, as I mentioned, link prediction. I'm going to focus particularly on that one as we proceed today, but again, very important problem as well. If you think about recommendation systems, you can think of a bipartite graph where you have users on the one hand, then you have items, products, and then you may know some of the links because some users have rated some products. Then the idea is to use that information to predict other links and then make recommendations accordingly. For instance, we're going to see, again, many problems that were maybe discussed yesterday of drug repurposing, of identifying side effects of different drugs, then can be cast, as we're going to see, as a link prediction task where, for example, you have nodes as pairs of drugs, and then you want to see if they're going to give you some side effects. And then finally, at the level of a whole graph, you can have classification as well to, for example, I don't know, something we've been working, I'm going to tell you about in a second, is looking at networks of the brain. Can we predict cognitive decline, for example, if you drink a lot over a long period of time? Then we have data for that, and we've been studying, and I'm going to show you some of the results in that particular context. So then, now, from tasks that, in a way, will dictate how do we process outputs of the network in its last layer. Let's suppose the final layer is a layer L. It was 3 in my previous example, but could be anything depending on how I design my architecture, of course. And well, the idea is that the outputs, they are XL. Those are representations, in this case, at the node level, generated by the neural network, let's say after training. Now, if I want to do node classification, then I will go ahead and just pick the ith row. If I want to predict the label of node I, I can go and pick the ith entry of XL. That could be a vector potentially if I'm working with multiple features. And then I can train a joint classifier, right, over all these XIs to predict, given some supervision, right, minimizing a loss function, the corresponding responses YI, right? And then that, of course, given it's a shared classifier, is going to actually still be permutation equivalent, which is what we want. If we just arbitrarily permute node labels, then the assignments are going to be correspondingly permuted. Link prediction, the idea now is, again, in the readout phase or in the prediction head of the model, just take, if I want to predict a link between I and J, I have representations for node I, node J. I'm going to somehow combine them, maybe via concatenation, via inner product, and then learn a classifier, right, based on those pairwise input signals to predict, for example, if there's a connection between I and J, just to predict A hat IJ. I want to spend a little bit of more time in the particular instance of graph classification, because there the idea is that, again, starting from node representations, right? I have a calligraphic V of those. I need to pull them into a single graph level representation. A must-have there is that that pooling operation should be permutation invariant, right, at the level of the graph. Not equivariant, invariant. And then typical aggregators we use are, for example, sum, mean, max. You can just sum up all your representations. Then if you permute nodes in your graph, then the graph level representation will remain the same. We don't want it to change. It has to remain the same, so then that's important to have there. And then we often train that over a set of graphs, right? We have a training set, we have a collection of graphs indexed by T, we have input features XT, and then corresponding labels. And then that's something just to contrast and hopefully you're not confused. That's different to what Alejandro was referring to in the context of transfer, right? Because there we had a collection of signals with maybe corresponding responses that we train for a given graph. Okay, so we train with a single graph, and then eventually we can test, right, or implement our neural network on a different graph. Here, we're training over multiple graphs to start with, so then that's a different type of data set. Is what people call, for example, an inductive setting versus a transductive setting where we actually train on a single, maybe large graph, and then we can predict elsewhere, let's say, links over there. Okay, so then that's just the idea, and then how tasks affect, in a way, what we do with our learn representations for a particular end-to-end learning. And clearly, these classifiers here could be MLPs and what have you. They have some additional parameters. We will learn them end-to-end along with the filter coefficients, calligraphic age in the whole architecture. Okay, so that's the idea. Very simple. So then, just to go to some examples of these tasks, this is a protein-protein interaction network, an example of a node classification task, for instance. So then, nodes are proteins, edges are protein interactions, and in this case, we would like to classify a binary level, which is a functional notation of this intracellular signaling cascade. Again, what is in doesn't matter, has to do with signaling transduction, right? How cells react to the environment, and then we can have a binary level, right? If protein Y is annotated ICSC, we color that as, let's say, yellow there, 0 is blue, and then the problem we're facing in this case, first let's look at the data. So clearly you can see there's some notion of a smoothness here, right? So then you have common colors in a way that propagate over neighborhoods in the graph. So then leveraging the graph by just thinking, I don't know, over neighborhoods, I'm just gonna look at averages and so forth, that's gonna be a strong predictor. But the graph is important. There's some binding, right, between the graph structure and sort of a smoothness of the profile of labels, which suggests, as we would expect, that the graph can give us a strong prior for prediction. And then a concrete problem here would be, suppose that you only observe maybe 10% of those labels, you want to predict the rest, or just predict a few of those. And then people often call this semi-supervised learning, because we are given the whole graph, but only a few nodes are labeled, but we still want to learn representations over all nodes, because we want to potentially learn or predict over those nodes that we don't know the labels, of course, but we use the whole graph to propagate messages to actually run your convolutional filters, learning hidden representations in all of the nodes, but we evaluate the loss only on the nodes which are labeled. And then once we have a classifier, we can use our readout function over there to do predictions. I hope that problem is clear. Again, it's a classical 101 no classification problem. Now, if you think about community detection, again, a very classical problem in network science of partitioning the node set into different communities. As I said, that's very common in online social media to identify social circles, in launching marketing campaigns. Also, even in infrastructure networks, for example, here partitioning the electrical power grid can be meaningful to carry out different monitoring or operational functions in the grid itself in an efficient way. There's a blackout, what you switch off, let's say, without affecting the others. So then that can be important. And of course, in many, many other domains. Now, another fertile ground for applications, and Alejandro had an example of this as well, is where networks can be important and naturally arise as graph data, is in network neuroscience, right? One of the most fundamental challenges of this century, and maybe probably even the next one, is to try to understand or make some progress towards understanding brain function and in a way how it relates to brain structure. And then clearly advocating or looking at networks of the brain where we partition, let's say, the brain cortex, for example, into different regions based on a parcellation like the Desikan Atlas, and then running some tractography algorithms on diffusion MRI data to get those very cool, like maybe artistic images of the different fibers, let's say, mapping the brain at that level. Then we can look at density, right, of those fibers. We can kind of register the atlas onto the tractography, and then each of these regions in the atlas are going to become nodes in a structural network. And then what are the edges? Well, it's the density of axonal bundles between different regions, right? And then the idea is that we go from an imaging modality, if you want, diffusion MRI, to a network of the brain. That's a structural network, which in a way tells you how the brain is wired. And then these networks typically are not too large necessarily. The Desikan Atlas has 68 regions of interest in the cortex, so then they need not be so large. Of course, you can go all the way to the neurons, and then that's kind of astronomical, right? But here, these graphs need not be too large. Now, Functional connectivity, on the other hand, basically refers to the covariance matrix of functional MRI signals that can be, or pairwise correlations of functional MRI signals that can be measured, right, in an MRI scanner. And clearly people have observed, right, that there's a correlation, of course, between structural connectivity and functional connectivity. Kind of, you can think that neural activity signals, of which bold signals measured by MRI is a proxy, should be, and its statistical properties, of course, should be somehow shaped by the underlying structure of the brain. And there's been different ways of trying to explain what that relationship actually is. We've, again, in recent work, advocated a graph neural network sort of encoder-decoder architecture, just to try to learn a representation of the mapping, let's say, from structural to functional. So our input is, again, across different subjects, structural connectivity of a cohort of subjects and their corresponding functional connectivities, and then we want to learn a latent representation using a graph neural network encoder that allows us to reconstruct that second modality, right? And then in particular, we trained that end-to-end with data for which we had some labels as to whether they were non-drinkers or heavy drinkers, and the idea is to classify by just observing, right, if we can extract that information in that latent mapping from one to the other one, and if there's anything actually that's happening on how the brain maybe is reconfigured if you drink too much over many, many years. And indeed, you can see that this is just a two-dimensional representation of the embeddings, and you can clearly pretty much distinguish, again, members of both of these cohorts, the control groups and the heavy drinkers. And then if you look at those connections at the functional level that were significantly reduced when you drink too much, then you see a bunch of them. And I don't know, not to get too worried, but that's okay. I don't drink, so then that's fine. I'm happy. But on the other hand, at the same time, then you have some other connections that kind of increase for the heavy drinkers, and then people typically associate those as a phenomenon of neural compensation. There's some function that's lost, and then some connections are established to keep that functionality going to some extent. But anyways, lots of things that can be done by learning from networks of the brain, and kind of an exciting area as well. I have this slide because I like this application a lot, and just also I want to differentiate some of the applications that Alejandro mentioned are, of course, very important, but they're somewhat different, as I mentioned, to some of the tasks I just described. Here, you have networks, let's say in this particular case are these word agency networks that capture signatures of different, in this case, playwrights, Shakespeare and Marlowe. And then we want to do classification, right, for example, by looking at signals defined on those graphs. Okay, so then the graphs are fixed, and they serve as a prior, as a structural prior. Then we have signals, for example, histograms of those corresponding words, the notes they are over other plays. And then we have labels, of course, as to those plays, who wrote them, and then the idea is, can we classify that? But in a way there, we have X's signals and then Y labels for a given graph, right? And then we want to train a graph neural network to solve that classification problem. And that, for me, is kind of more of a graph signal processing type of task, where the graph is fixed, and we have a data set of signals and responses, and we leverage strong priors given by the graphs, and that, in a way, is different than training over multiple graphs or classification or what have you. But again, a lot of interesting applications arise as well in the graph signal processing domain. Okay, the idea is to work with the signals on the graph. Okay, as I said, let's maybe go back 20 years. You'll find myself maybe they are, I don't know, going to a thermodynamics class, I would guess. And that's exactly where people started looking at problems of link prediction from handcrafted features, and I'm going to get to the very basic renditions of those. I just want to go through the story of and the history of link prediction, just to see what people were doing, let's say, throughout the years and actually over the process of 2 decades, and then actually see or witness in the context of network data the same revolution we saw with deep learning, in a way, let's say, going from handcrafted features and very kind of task-dependent, time-consuming, artistic, let's say, but valuable nonetheless, and we're going to see well-performing solutions to automatically learned generalizable representations of network data. So what's the link prediction problem in a nutshell? Suppose we have this graph on the left, and then solid edges means that the edge is present, then these dashed lines means that there's no edge, and then suppose I'm given arguably optionally some node features, but what I get to observe for sure is edge status only for a subset of node pairs. Okay, I'm going to call that set calligraphic V ops, a subset of V times B. So kind of for each pair of nodes, like you have a slot, right? There could be an edge or not an edge, and then you observe some of them, and that's what you see over here, right? Like I observe that there's an edge over here. I observe there's no edge over there. I observe there's edge over here and so forth, but I don't know what's going on here. So then the goal is that given that data, I want to predict the edge status for potentially all other pairs that I haven't observed. Okay, so that's the problem in a nutshell. Now, again, same thing. If I have a graph using our notation with the density matrix A, then I have A ops and A miss, which denotes the entries in the observation set and in the missing set that I want to predict. And the goal is to predict those given observations and possibly also vertex attributes. If that can help, I can leverage those. And I'm going to see that critically to leveraging those features is to use parametric functions like graph neural networks eventually. Okay, and there's various reasons as to why links may be missing. There might be just like the system is too large. I just cannot sample. I don't have the budget to sample everything. An edge might not yet be present. If it's a dynamic graph, it may arise in the future. I want to predict and go ahead. Or in the context of recommendation systems, I just don't know, and I want to kind of assign a link there if given the past user behaviors, then a given product is something that I believe that he or she would like. Now, how do we go around trying to tackle this problem in a probabilistic fashion? Suppose I have some model for the features and then the observed and missing entries. Kind of the gold standard will be to predict the entries in the missing set based on the conditional distribution of a miss given the observations and the features. Naturally, it would be a more manageable task to try to predict the variables individually, maybe just doing some approximations, neglecting dependence, and so forth. Well, as I said, going back to 2003, 20 years ago, and that's where I say let's take the time machine and go there. Well, first thing that people were doing is just building these carefully handcrafted features for potential target edges. Let's say I'm going to focus to predict if there's an edge or not between nodes I and J. These features boil down to scores for each potential edge. I'm going to get scores for all of those I want to predict. I can rank order them and then make predictions on the top n scores if that were to be of interest. So then, what are some examples of what these scores could be? Well, classical ones are based on distance, based on the small wall property. Other ones which are very simple to understand are kind of very local neighborhood based, because we know that triadic closure is typically at play in social networks. Triangles tend to close, friends of friends become friends. So then if I want to compute a score of how likely I and J are to connect, I can look at the number of common friends that I and J have. Maybe I can normalize as in the Jaccard coefficient over the total number of friends they have, because if they have 1 million friends, then, I don't know, just them being having a few common friends doesn't tell you a lot, right? And then that's exactly also the idea in this atomic ADAR score, where the idea is to favor loosely connected neighbors, right? I penalize a lot. I sum over common friends of I and J, right? And then I penalize if that common friend is one out of many, many friends of that particular user, right? I look at the 1 over the log degree. So then if that individual K, that's a common friend to I and J, has a lot of friends, then the fact that I and J are friends of K doesn't mean much. On the other hand, if K has a small group of friends, meaning that this is small, the score is large, that will kind of boost up that score. And as we're going to see, right, it works pretty well predictively. And again, doesn't matter. Here in this particular study, John Kleinberg and a collaborator back in 2007 studied a bunch of these handcrafted features in classifying or predicting links in 5 data sets constructed. These are co-authorship networks based on archive. And then you can see that, again, this is predictive performance relative to random guessing. All of them have some predictive power. The one that seems to be working better is this atomic ADAR score I just defined at the bottom right of the previous slide. Here is you compare everything against just common neighbors predictor as a baseline. A few of them do better, high variability as expected. But again, even these very simple ideas that capture some knowledge on how links are formed in a way, then have some predictive power. Okay, but it's very basic. Then what will be the next thing we would do? Given features, we can train a classifier given those handcrafted features, right? So indeed, we can think of tackling this problem as, again, formally a classification problem. And then here's another toy example where we can see this at play. The goal here is to predict lawyer collaborations. This is a lawyer buffet in New England. It's, again, a data set that kind of is also very old, back in 2001, which has nodes as different partners, and then edges indicate whether partners work together or not over a period of time. Interestingly, we have a bunch of node-level attributes. For example, seniority, that's the number you see over there. 1 is the most senior, not working a lot at this time, kind of close to retiring, you can see. And then 33 is kind of the youngest partner, the most junior one. You have office location encoded on the shape of the nodes. You have type of practice, 2 types, litigation or corporate law, encoded in the color. And then you have gender data. Only 3 of the partners here are female, 27, 29, and 34. So then the goal is to predict cooperation among social actors in our organization. So suppose that, again, some of these links are not observed, right? And we have the remaining graph with node attributes, and then some of the observed edges in my set be obs, then can I train a classifier to predict those links between those unobserved pairs of nodes I and j? What could be an approach here? Again, just looking at some results, you could define some explanatory variables, for example, some main effects on seniority. And again, this is something that you define as a feature for each potential edge, right? Pair I and j. You look at practice as well. You have some homophily effects. You would believe that it would be predictive, for example, that if both partners work at the same office, they are more likely to collaborate, so that's kind of a reasonable feature. And then also the 6th one over here is one that takes into account the network structure. The first 5 of them do not use the network at all. The 6th one does. And then let's just, for the fun of it, compare a few methods. For example, just basic logistic regression with the first 5 network agnostic, purely based on nodal attribute features. The second one is a logistic regression as well, where I incorporate as well that 6th feature that has to do with the network structure. Then I can just go back to what we said before and then just use as a single feature the score based on number of common neighbors, for instance, and train a classifier based on that as well, just purely looking at the network from the perspective of a single feature. And then finally, maybe we can use a more fancy model, which I am not going to describe, but it's a logistic regression with just the network agnostic features plus some latent variables per node, latent positions, where the probability of connection is modeled as well as the inner product between those latent positions. And again, I can learn or infer from data those latent vectors using Bayesian inference. And again, that's a work that Peter Hoff proposed at a model for network data back in UDIP 2008. So again, here are some results, kind of anecdotal. We can just see that this behaves kind of well. Important to measure here is that clearly method 1 seems to perform worse. That's the one that relies only on network attributes, doesn't use the network at all. All the other methods actually do. Hard to say, I don't have the area under the curve values over here, but all of them are kind of competitive. 4 does a little bit better using that more fancy modeling, taking into account the latent variables. But again, that's kind of how far this can take us, right? And kind of, we cannot continue with this modus operandi of just for each given problem we're facing, try to handcraft particular features. That really is not flexible. It's too time consuming. And then why not take the usual step, right, of can we try to efficiently learn? As I said, they are potentially task-independent features that capture the structure of the graph, and then that's useful for some downstream machine learning tasks as the ones I described before, be it link prediction, as we're doing over here, but could be node classification, graph classification, and beyond. And indeed, a next kind of wave of approaches came to be, right? Even before getting to graph neural networks, right? This area of graph representation learning broadly arose. A critical problem that this area wants to address as a general methodology, right, is that of network and embeddings, right? And that's exactly what a graph neural network does. It builds through filtering, right, representations or embeddings of different nodes, which are combined with neighbors to build, again, complex representations of the network structure, taking into account features. Well, an embedding is basically just, the goal is to learn, again, in loose terms, to learn a mapping from a discrete object, right, for example, a graph, into a continuous domain. For example, embed nodes into RD, Euclidean space. So, formally, just to introduce the notation, if we have a graph, I want to learn some low, typically dimensional representations, D being much smaller than the number of nodes in the graph, and I'm going to call those embeddings ZI, right? So then the idea is to build those or optimize for those representations, maybe in a unsupervised fashion, we're going to see, potentially in a supervised fashion, but in the former case, the goal is that these mappings, right, I embed through some encoding function, say, vertices in my graph into vectors in RD, and the goal is that some similarity measure between pairs of vertices, whatever that could be, for example, if they are connected or not, or some high-order similarity, can be in a way decoded and preserved in terms of the embedding vectors. So some function of Zi, Zj, maybe the inner product, captures or approximates, for example, whether I and J are connected or not across embeddings. So kind of something is preserved in the embedding space from the structure of the graph. Kind of information is kept in those embeddings. And as I said, typically we need to be much smaller than the number of nodes for scalability, and then all these methods effectively act as dimensionality reduction schemes, and then that's clearly, of course, useful. Many methods were proposed, starting from shallow embeddings. I'm going to describe a few of them, leading to graph neural networks. It's very common to categorize them using this general framework of an encoder-decoder perspective. It's, I think, didactic just to look at many of them can be categorized under that common umbrella, and then there's two references over there which are good reviews of many of these approaches, using, again, this encompassing model just to compare many of the methods that were proposed. But basically, how does this work? You start from a graph, then there's an encoder module that then generates encodings for each of your nodes, and then the idea is to decode those embeddings so that then you can maybe reconstruct some property of the graph itself in a supervised fashion. For example, here to decode the connections, right, or the neighbors or the links incident to this red node over there, kind of to preserve graph structure by encoding and then decoding that using that linear representation. But even if you have supervision, then you can think of learning embeddings which are informative or discriminative for some downstream classification task, being graph classification, node classification, or what have you. Now, let me just spend a second and then give you a few examples of two general categories of these shallow embedding approaches, and kind of the next step is going to be indeed graph neural networks. But I want to show you this so that then we can show or argue on some of the limitations that these approaches have that actually GNNs came to overcome, and kind of just to appreciate even better kind of how we got there and then what have we gained in the process over basically 2 decades. Now, a general class of approaches are known as matrix factorization methods, and then these are also, as I'm going to describe in a second, relevant to link prediction. If you've ever heard about matrix completion, we're talking about sparsity. Yesterday, something that kind of was all over the place from 2010 and beyond, or even earlier. Well, then kind of the next wave of that was matrix completion as well, also looking for low-dimensional structure in high-dimensional data. Well, here, the idea of these matrix factorization methods is to learn some low-rank representations of some similarity matrix that's depending on the application for us to decide, so that we minimize the following loss, right? So then I want to use an outer product decoder. Z is my matrix of embeddings, where for each row I have the embedding of the particular nodes. And then the idea is that with ZZ transpose, I want to reconstruct whatever similarity matrix I want to preserve from my original graph, some function of the Gensi matrix. Indeed, if you have this outer product decoder, what this actually implies is that the similarity between nodes I and J is approximated by the inner product between the corresponding nodal embeddings Zi and Zj. Okay, that's the idea. Now, one of the earliest approaches in this context, and again, I think people have thought of this much earlier in context before graphs, for example, in recommendation systems via collaborative filtering and so forth. But for graphs, people proposed this in 2013. The graph factorization approach basically preserves first-order similarity. So the question is, what is my similarity I want to preserve? In this case, it's just first-order adjacency. Okay, whether nodes are connected or not, I want to approximate this Aij with inner products, and then only measured over pairs of nodes in VOP. So then what you should think is that you only get to observe some of the entries in matrix A, namely links or non-links. Most of them you don't know. But still, because you are going after an approximation model which has limited degrees of freedom, basically number of nodes time d, because ZZ transpose is a low rank matrix, then if the matrix you want to approximate is truly low rank, and then, for example, in recommendation systems, think of an adjacency, users versus items, for various reasons, people believe that that matrix actually is indeed low rank. For example, there are similarities or dependencies among different products, right, or among different users. People have studied how do we think or value different products, and then we typically take into account a few variables. So the kind of low rank models are well motivated, and then we can even get away with approximating a matrix by observing only very few of its entries, that is, the cardinality of the ops being very, very small, with a low rank model. And again, that's something we can use to obtain embeddings for a graph, but it's actually a solution, a matrix completion solution that's kind of very widely adopted in the community of recommendation systems for solving a recommendation system problem, which in this case amounts to solving a link prediction problem if you want. And then one can think of various other similarity scores, for example, looking at higher order similarity. You know, if you raise matrix A to the power k, then the ijth entry of that matrix is counting the number of length k paths that go from I to k. So I maybe would like to preserve that particular structure, maybe looking not just at one-hop paths, but maybe longer paths in the network. If that's what I want, then that's what GraphRep does. And for example, the hope approach looks at not necessarily symmetric matrices, so then it looks at directed graphs, and then I'm going to use a z-in, z-out type of asymmetric matrix to reconstruct, for example, some of the features we saw before. For example, the Jacquard coefficient, the Adamic Adar for different pairs of nodes. That's what I like to preserve through my embeddings in a way. Okay, so then there's many, many methods, but just to give you a sense of those. Now, the final class of approaches I wanted to introduce is those that rely on random walks, and kind of the motivation is going from text to graphs, thinking of sentences in NLP, of course, or in language models as random walks over the vocabulary, right? So then the goal here is to assign similar embeddings to nodes if they tend to occur, right, in typically short random walks over the graph. Okay, so then if you do a random walk over the graph, and then you start from I, you say my random walk is going to be of length t, and then you frequently visit node j, then that means that I and j should in principle have similar embeddings in the graph. So then how do we accomplish that? Well, as I said, we generate random walks to sample node sequences. That's going to be my training data. And then the goal is to learn node positional distributions, just like we do for words in skip-gram models. Okay, that's kind of the motivation for this set of approaches. Viewing sequences of nodes as sequences of words in sentences, and then just carrying over whatever we knew from kind of old-school language models. So then the similarity score we want to decode in this case is the conditional probability of visiting j, given that I start a random walk in I. That's my similarity between I and j. Notice in this case it's an asymmetric similarity, right? So then I can look at it both ways. And I want to decode that from the learned embeddings z, right? So then how can we do that? Well, I can maximize or minimize, a cross-entropy loss, where my predictions, right, of whether the probability of I and j is given by just a composition of an outer product decoder, zi transpose j, with a softmax function. That gives me my estimated probabilities that starting from I visit j. So then I have, through my sample random walks, I have some data of pairs of nodes I visit, and then I train minimize that loss to actually learn my embeddings. Okay? Now, one has to be careful here, just minimizing this, or even evaluating this denominator, right? The sum over all nodes can be computationally expensive. I have to do that over all nodes, linear in the number of nodes, for each sample over which I'm training. So then that's not great. A first famous approach in this context is DeepWalk, which used a so-termed hierarchical softmax methodology that kind of leverages binary trees to go around this complexity. Another also follow-up work that is very flexible and scalable is, again, a well-known embedding method for graph that goes by the name of node to back. What's the idea here? Well, is to look at random walks, but give some more flexibility. In the previous approach, right, in DeepWalk, random walks are basically just unbiased. You just follow neighbors, all of them are equally likely. Now, in node to back, the idea is to use biased random walks to control and somehow in an homotopy fashion look at or interpolate between walks which are akin to breadth first search or depth first search, kind of doing random walks that more explore locally first before going deep in the graph, kind of going multiple hops away, versus just going deep first instead of exploring locally. And then that gives the model or the resulting embeddings kind of enough of flexibility to learn, on the one hand, more structural roles versus community structures. And then what do I mean by that? For example, let's look at these embeddings obtained using Node2Vec for this toy example of a graph here, which are character interactions from the novel Les Miserables. For example, on the left, look at the embeddings. They are capturing, by using actually breadth first search first, they are capturing or embedding similarly nodes that belong to the same community. Right? On the other hand, using now deeper random walks, what we get are embeddings that capture more the structural roles of different nodes. For example, nodes which are deeply embedded in communities have the same color or kind of embedding. You have these gatekeepers that play similar roles, kind of entry connections to the communities are embedded differently, and then that flexibility is afforded through this particular method. And of course, they deal with negative sampling as a additional trick in their implementation to make this actually very scalable, and then deal with this kind of partition function problem I mentioned before to manage it, to do it efficiently through sampling. Now, we've talked about shallow embeddings as a first family of approaches in graph representation learning, which basically we optimize directly over the embedding vector. So then the encoder itself is nothing more than a table lookup. Right? I have one embedding vector per node, and then that I optimize directly to decode some particular similarity that I care about. Now, what are some limitations of those approaches? On the one hand, of course, there's no parameter sharing, right, in the encoder, because each node has its own parameters, and then that, of course, is inefficient both statistically, right? We know that parameter sharing can regularize, but also computationally, the number of parameters grows with the number of vertices, and that's something that we mentioned at the beginning, right? Scalability through convolutions hinges on the fact that the number of parameters in the model doesn't grow with the number of nodes, and then that's, of course, essentially. These methods do not leverage graph signals or attributes during the encoding. The goal is only to reconstruct properties of the graph structure itself, but oftentimes these attributes can be highly informative, and then you can use parameterized functions like GNNs to actually leverage those as we do the aggregations and embeddings. They, of course, have a limited expressive powers because we are not capturing complex nonlinear structure, and that's where neural networks can be, of course, very useful and expressive, right, if we use those at the encoder, at the decoder, or both, and then you have family of methods like graph autoencoders and beyond that actually leverage those, and of course, graph neural networks indeed do leverage deep architectures. And finally, these shallow embeddings are inherently transductive, right? So then they are fine to compute when we have a given graph. But what happens now if a new node shows up, or I want to compute embeddings for a different node in a different graph? I need to start running random walks again, all over again. So they have to recompute it from scratch. So then it doesn't afford, for example, learning embeddings that then, or representations that can be applied to different graphs in an inductive setting. And then that's exactly as we said before, a graph neural network affords, for instance, because you have these filters which you can instantiate in any graph. So then it allows you to maybe train on some graphs and then test on some others, for instance, whereas these approaches, of course, do not afford this particular functionality. And again, I just went through this historical, maybe, parenthesis, just to see how we got there. What was, again, we saw that revolution, right, from using features, and again, I liked what René Vidal, I heard it many times saying, I think he said it here in 2019, right? We went from optimizing features to optimizing architectures. That was kind of the revolution of deep learning. And then the same thing, of course, happened when working with network data. And I just wanted to kind of capture that of how we got to the great things we heard from Alejandro early on graph neural networks. Now, just to conclude, I want to go over a few that I believe are high-impact success stories of GNN deployments in today's technology, some applications that I kind of like and hopefully excite you as myself as to why you should pursue, and then maybe, again, there's not too much we can tell you in 2 hours of GNNs, but then you can, if you want to learn more, follow some resources we'll share later, and then use them in your own research or industry applications. Continuing with the issue of link prediction. The first example or application I want to mention here is that of a complementary product recommendation that has been deployed at Amazon and at scale. The problem they are dealing with here is the following. Given an item purchase query, for example, I like playing tennis, and suppose I want to buy a racket, right? Then you know that Amazon wants to figure out what else to recommend to me that in a way is related to the tennis racket, for example, tennis balls and whatever. So then it wants to recommend multiple related products, but also they should be complementary, because they don't want to suggest me like buy a can of tennis balls and then a pack of 3 cans of tennis balls. Those are kind of redundant, so then they have to be related, but at the same time complementary, like for example, a wristband or shoes and then balls. So then that's the problem they want to deal with here. Now, what's interesting about this application, I'm just going to focus on the graph they work with, which is a kind of very rich, and also the graph representation learning module based on a graph neural network. And then there's some other modules, which again, I'm not going to spend time on those here today. But the idea is to do graph representation learning at the level of this behavior-based product graph. And then what's the graph they are dealing with? Well, nodes, and I have a picture of a sample subgraph over here. Nodes are catalog items or products, right? As the one you see over here that could include features. For example, what's the category, the type, and then some additional features over there. In that case, one of the nodes is this tennis bag. And then each out of 3 different types connecting different products, actually reflecting, for example, historical browsing and purchase behavior. You can have links that say, okay, you bought this and then also view this other one, or you bought that one after viewing this one, or also bought. Okay, so then there's these 3 types of interactions, like you saw something and you bought both of them, or you also just viewed after buying a particular product. So then we have this particular graph. And then something that's done online is to learn embeddings for each of these nodes, which is in the order of millions of products, right, in the Amazon basket. And the architecture is kind of as simple as following, right? The idea is if you look at the BPG snapshot, where you have a particular product and then 3 neighbors based on these different relations, like co-view, view to buy, and co-view. The idea of the encoder is as following, right? You have these 4 items, I, J1, J2, and J3. There's a first feed-forward network that uses only these catalog features to learn some embeddings. And then you have a neural network with an attention layer, a graph neural network that actually combines the embeddings, right, of node I and the embeddings of the neighbors, also with the attention, weighting the relative importance of the different nodes that are actually related to the node of interest. For example, this racket over here. And then those embeddings are computed offline, and then they go through different modules to eventually come up with predictions. And again, I don't want to go into the details of that. You have the reference there if you want to see more. But kind of they have deployed this in production, and they have demonstrated that there's significant gains in terms both of sales and profit, and then kind of that's an element of the recommendation system which is running today. There's a GNN working in Amazon's recommendation system. Now, another interesting application that also relates to link prediction using graph neural networks is this interesting problem of how to discover side effects due to polypharmacy. As we get old, people start to use multiple drugs, again, and then the question is, by using multiple drugs, there's the risk of suffering for some adverse effects, right, that we oftentimes don't know. And the question is, can we predict, right, or to unveil side effects due to polypharmacy as a problem of predicting drug-drug interactions? Okay, so we're going to work with a following graph, and then that, I think, is what I believe is interesting in this particular problem. They're dealing with some multi-relational graph and multimodal graph indeed. So then we have first, these nodes in orange are proteins, and we have edges from databases of protein-protein interactions. Okay, so that's one component of the graph. The other mode are nodes which are actually drugs, those triangles over here. And then we have drug-drug interactions that can be potential side effects. And then they have identified, I think it's in the order of 964 different types of relations that correspond to different side effects. For example, here, gastrointestinal bleed, or maybe bradycardia, or vomiting, or nausea, or whatever. These are different types of relations on the edges between different drugs. You also have links between drugs and proteins, right? The drug is targeting a particular protein, so then you have those connections. So then the problem here is to perform, as I said, multi-relational link prediction predicting links, right? That could be one out of multiple clusters, or potentially, well, there could be multiple side effects in multimodal networks using GNNs. And then to that end, what they propose over here is an encoder-decoder architecture where what they obtain are node-level representations for the different drugs by performing the following. For example, you want to obtain a representation for this drug over here, labeled C. There's two different types of relations which are in the data that we know, R1 and R2. For each of these relations, we're going to use, again, a graph neural network to learn representations for these particular neighbors. We combine those with also a neural network layer that takes into account the proteins that are targeted by that particular drug. So then we do multiple layers of aggregations or graph convolutions based on that particular graph to learn representations for each of the drugs. And then on the decoder side, we want to predict triplets in a way. So we're going to look at pairs of drugs and then the corresponding relation, right? And then that is done not by a matrix decoder, but by a multi-way array, actually, a three-way array or a tensor decoder, where you have drugs, and relations, right? So then ultimately what you do is you want to learn these probabilities, right, for each pair of, or the target pair of drugs, in this case the triangle C and S. I want to actually predict what's the probability, right, that relation 1 is active, namely side effect 1, side effect 2, and so forth. And interestingly, they have trained this on a database of, I think it has in the order of 20K proteins, and then drugs are in the order of 20,000 that they have, again, all this information to train, and they have discovered a few side effects that were not kind of de novo side effects that were not reported in this database, and then they have actually validated those by finding some evidence in the literature as well, kind of a good in silico approach to discovering side effects that were not known experimentally or in the lab. Now, something else I just want to mention, kind of a nice success story on something we use very frequently. Navigation tools such as Google Maps are kind of under the hood, relying on neural networks to predict time of arrival for particular trajectories that you want to, I don't know, go. For example, going from the airport here to the university, it says like 30 minutes whenever I did this screenshot back in the day. But the basic idea is just Google is collecting anonymized traffic data all the time, right, from drivers and so forth. Now, the key ingredient here is to construct a network graph, what they call super segments, that is a particular subgraph, right, which basically entails adjacent roads that share a particular traffic volume, something that looks like that. For example, if you care about going from A to B, then you are going to look at this particular nodes are road segments which are adjacent in a way, and then you build this subgraph, and the idea is to predict this particular property. They want to predict kind of the time to go from A to B. For example, what's going to be in 10 minutes, I believe, then in half an hour and 1 hour. And to that end, they actually use a graph neural network that exchanges node messages as well as edge messages, and then combines everything to obtain a representation of the whole subgraph. And with that, they come up with predictions, which are then, again, continuously updated dynamically as new data comes. Again, the architecture, if you look at the paper, is, again, very, very simple. The trick here is how to train this model at scale, again, because the graphs or the subgraphs are very variable. Some of the super segments have just a few road segments. Some of them are actually very long. There's huge variability, and then there's actually a reinforcement learning algorithm they use based on meta-gradient just to actually carefully schedule how's the learning rate to train this in a very stable fashion. And again, the message here is that there's a GNN in the Google Maps at the heart of predictions. And again, when you want to go from A to B, and you see it's going to be half an hour, 15 minutes, and so forth, then that's predicted using a graph neural network. Again, a simple model that's, again, trained in a challenging environment, as you see. Now, I have a couple of more examples to go through. I like this application as well that has to do with antibiotic discovery. The goal is to predict, this is an example now of a graph level classification problem, right? So you want to predict antibiotic activity, in this particular case, E. coli, this resistant bacteria growth inhibition, in molecules. And so then our graphs are going to be molecules, and we want to predict that particular property. It's a graph classification problem at the level of whole graphs, whether they have this antibiotic property or not. Right? And again, that's a very important task that, again, people have been doing forever, right, in terms of figuring out these new drugs. It's a very, as it was mentioned yesterday, right, a very expensive, time-consuming, and typically low efficiency task. And again, what you can do in the lab, right, kind of bounds to what extent how many molecules you can actually test, right, in the lab. So then that's kind of challenging. And now the idea is to train a machine learning model where what they did is the following. They trained a GNN-based architecture that you have there on the left. The innovation is to use or pass messages. Again, for molecules, nodes are atoms, and then edges are bonds, and then the architecture lends representations for different edges and nodes by doing message passing on the edges, and then eventually aggregating representations to obtain a representation for each of the individual molecules. And then they try to predict and are trained based on labels on whether the molecules have this antibiotic property or not. Right now, the nice thing is that once you have that trained model, then you can test it efficiently on very large molecule databases for which we don't know what's their antibiotic properties. Interestingly enough, they have identified, again, the idea is then you train, you have some scores on how likely they are to have that property, and then you can pick the top 10, top 15, and actually test them in the lab to see to what extent that prediction was actually accurate. Interesting enough, kind of one success story that they point out in the paper, right, is that they were able to predict, indeed, antibacterial activity in this molecule halicin. But the interesting thing is that the structure of this particular molecule is very different from others that were known before. And actually, halicin, they tested in mice, and then they found that they have very broad spectrum of antibiotic activity, also not only against E. coli, but against some other infections as well. So kind of, and they tried it on several other databases and identified in the order of 8 new antibiotics through this purely in silico approach. So just to comment in 1 second, graph neural networks have also been used in a kind of chip design task that kind of have defied automation over the last 50 years by just looking at representations and reinforcement learning. I just want to mention that they used this design to actually floor plan the TPU V5, which is the next generation of Google's AI accelerators. And again, just there's lots of interesting and exciting and high impact applications where GNNs can indeed have been shown to have impact, and of course there's many more to explore. That's just to conclude. Bunch of software resources, you can look at that then from the slides, different frameworks for training and building models. You're going to play with out in the lab later today. Some GNN courses that I believe are very useful. The one at UPenn that Alejandro mentioned. There's one at Stanford University. If you want one in Spanish, there's one as well here at the Universidad República that my friends put together. So plenty of resources, slides, collabs, videos, and that's basically all I wanted to say. Thank you.
Thank you very much, Gonzalo, for the great talk. So we have time for a couple questions. There's one there.
And the back, I guess.
Hello.
Yes.
Thanks for your talk. I was wondering, since graph tend to, in some way, encode the relation among the nodes. To use those kind of dependencies and to take advantage of them to solve our problems. My question is there any care we should take when thinking to split data in training and validation, training and test, to make sure that they are independent but yet make sense for the problem?
Yes. Yeah, that's a very good question, and indeed, I didn't go into details, and particularly link prediction, that can be tricky in a way. Oftentimes, we want to train a model, and then what we do is we ourselves hide whether, let's say, hide for the sake of training the model whether edges are present or not, that become part of the test set, and then some others are observed. Of course, even in semi-supervised learning and so forth, our usual paradigm of machine learning, right, where you have IID data for training, well, that kind of breaks up, because here, for example, in semi-supervised learning, then data points are nodes which are clearly related, so then we have to rethink in how we view that. But typically then, for training, you would like to, again, make sure that in the context of link prediction, for example, then you set aside some links and then negative samples, no links for training. Then you set aside some other ones which are not touched, of course, for testing, and then a part of the training ones are in validation. And indeed, then things carry over. Of course, then if the problem is transductive, basically that's all there is. If it's inductive with other graphs, you have to be kind of more careful. But indeed, kind of those similar principles arise. And of course, typically you would like to, in a way, sample more or less uniformly again, the space of edges in the graph, not to focus too much in a part of the network, and then otherwise it's going to be hard to generalize. So kind of those are the general principles, but again, the basic things of a training set and a held out test set are relevant. But in a way, it's very pertinent question that the way we think of training data as IID samples in a way kind of breaks down in the context of these transductive problems, for example, then not too much. For example, if you look at the GSP approach, where you have a collection of signals, xi, let's say, from 1 to t, and then you want to predict a response, in that case, you can still kind of work on that regime of IID training data and still regularize it with the graph. But yeah, it's a very good point.
Thank you for your talk. Excellent insights. My question is regarding, in the case of graph representation learning, where each graph is a single sample.
Yes.
How do you deal when each graph scales in its nodes counts? For example, if you have really huge adjacency matrices, such as tens of thousands, which type of limitations arises?
Yeah. That's a good point. Scalability, in a way, is still an issue. I don't want to escape that, but I just want to say that clearly we should appreciate that kind of, not all graphs are huge. For example, molecules are very relevant and they can be small. But when graphs are huge, then people have dealt with this in several ways. For example, there are, when you're doing filtering or aggregation, like multiplying with A, right? For example, a first order filter, a signal with the adjacency, it's just like you're combining the values of your neighbors, right? Well, people, for example, do to reduce computational burden, they just say, okay, I'm gonna not use all my neighbors, but just sample a few of them at random. For example, based on some property, for example, based on some scores, you could have similarity, and these probabilities could be learned as you go. That's one well-known trick, and if you may want to check, for example, that's the Graph Sage model, kind of does that, and for example, has been deployed at scale for doing recommendations in Pinterest, where they learn embeddings over billions of nodes, or whether maybe billion is too much, but I think it's really high millions of nodes for sure. So then that's one way to deal it. Then, of course, when you're working really at scale, you have to look at distributed processing platforms, like using MapReduce, for example, because you're computing many things multiple times, so you can do those efficiently. So then there's a lot of things that go, let's say, under the hood to do actually implementations or infrastructures for learning from large-scale graphs. I'm more of a theory guy, I would say, so then that's not my forte, I don't know, kind of, but I understand that people have to be, again, very careful with large-scale graphs, which are common. Sampling are tricks, then carefully doing the calculations are other things, but that's kind of what I can say.
All right, thank you very much. So let's thank Gonzalo again for the really great talk.
Thank you.
We now have Fernando. Bueno, mientras vamos a tener ahora we're gonna I went to autopilot. So we're going to go ahead with some sponsored talks. We have now, okay, well, let's wait to set up. All right. So we have Fernando Cormenzana. He's a computer engineer working in AGESIC in the Emerging Technologies Division with an emphasis on artificial intelligence. He has a master in ICT management, and he's passionate about the use of technology to improve education, team coaching, and knowledge management. Please welcome Fernando.
Okay. Hello? Okay. That's fine. Okay, well, thank you. No? After the other talk, this is... Hola, hola, hola. See? Okay, can everybody hear me? Yes? Okay, thank you very much. No? ¿Por qué mejor así? Okay. Bien. Okay, thank you very much. Thank you for coming, and thank you for all the stuff you are presenting here. After the other talk, this will be very short. It should be. And I want to present some solutions that we put on work here at AGESIC. But first of all, let me talk about what is AGESIC, because maybe some of you don't know. Here you have the definition. It's a very simple one. And our mission, that is a little bit different. You know, for us, we are always focusing on people and transformation with equity, okay? And after 16 years of work, AGESIC is a very young agency. We have some indicators, international indicators, that show a little bit of our work, okay? And the achievement we made. So there you can see there's some important figures that put us on the map. There we believe in this statement because we believe in the benefits of automation. And the solution that is based on AI that we will present automates a service widely used in AGESIC. What is the service? The service is called Help Desk. Maybe you should know them. And what is the objective of this service? Is to find a solution to the problems that the user may have. We seek for a quickly and efficient solution bring by the service. Oh, sorry. So how does it work? When the user have a problem, it must fill in this ticket. We call it a ticket, okay? This is a form that is filled in very different kinds of fields. But in particular, there are two fields here, subject and description, that the user types in natural language the description of the problem. And with this input, we try to predict three fields of the form: the site, the group, and the category, okay? And if the system fails, the technician has the ability to mark this failure so the system can learn from its own mistakes. What are the features of this solution? As I say, we try to automate these three fields. We have an average of 2,200 tickets per month, and there are 43 technicians involved in all this process of the help desk. We try to not interfere with the operation of the ticketing system. This ticketing system is called system desk. It's a critical system that have hundreds of users, for about 800 users. And another important thing, we use always open source tools, and we seek for an end-to-end development. The stages of the development was, I want to divide the problem in three different models, one model for each field. By the way, with the email domain, we try to predict the site. By instance, AGESIC office. The subject and description will help us to predict the group. By instance, IT support. And with the subject and description, try to predict the category. By the way, printers. What was the result of the training? For the site group, you have there some figures. For the group model, another figures, list of figures. And for the category, other ones. Here you have the solution architecture. I try to explain how it works, okay? Here you have the service desk, and each time a ticket is completed, they arrive to the models with all the information in the form. Maybe the information is complete, maybe the information is kind of fuzzy. And then we try to predict, as I said, the three fields, and if this can be done, we record the solution or the result of the process by an REST API to the database of the system desk. For the training of the three models, we use all the tickets. You know, we have kind of 45,000 tickets right now, the 2 years for the work of the system. But the times for training were very, very important. So we use the cluster UI, that's the National Supercomputing Center, which was very important to us because it permits to a work that normally uses to occupy dozens of hours, we can just do it in a couple of minutes with the use of cluster UI, okay? And by the models, we have indicators that go to a tool called Superset. It's an open source tool that graph all the results and permit us to monitor the solution, the entire solution. Now, for the monitoring, just a minute. We monitoring the operation, the backups. The model training is on demand. It depends on the variability of the technicians, of the categories, on the problems that arose. We have monitoring of the indicators to evaluate performance. And there's a change management aspect that is very important to us. This change management was a key success because we always have the help desk team near to us to help us to define the problem, to refine the problem, and to maintain the average rate. So we thank there all the equipment, Adrian Silva and all its equipment, thank you, for this app. Here you have a copy of an image, a picture of the dashboard with the superset tool. This is the historically function of the system. We are now in the second year of production of this system. It works every day, 24 hours. And there you have the results with the 4 kind of results we have with a different color for each one. And finally, for the future, we want to add more fields, generalize the solution to other organizations of the Uruguayan government, prepare user guides and manuals, and continue with the automation by MLOps or MLOps to automate development, training, and the solution itself. And to share this last image, we present our vision of AI. We think that that AI is a bridge between 2 different worlds, the human and the technological one. And AI may permit for the human to amplify the human talent, to make better decisions, and to achieve more progress. So rather than saying artificial intelligence, we like to talk to augmented intelligence. And that's all. Thank you very much.
Thank you, Fernando, very much. Thank you so much. Yes, in the interest of time, we're going to move on. All right.
Por favor.
El micrófono. Sí. All right, so we are going to have Alan Descoings. He's the CTO of Triolabs. He is an AI and technology leader with 13 years of experience serving companies worldwide with a particular focus in the United States and Silicon Valley. So please, everyone, welcome Alan.
Give me 1 second.
No.
All right, can you hear me? Okay, so I'm going to start in an unconventional way. I'm going to start thanking everybody for staying. I know it's late. I know we're tired. So I also want to thank the organizers of Khipu and start with a round of applause for them and for every one of you that actually stayed here. So okay. So then the emotional roller coaster will continue. I'm going to start with a story. A couple of years ago, I had a conversation with a young boy that was full of illusions, and he wanted to become a truck driver. So naturally, back then, I already knew kind of how fast deep learning was moving, so I had to say something. I had to warn him. So I told him, it's not safe. Maybe AI will automate that job. Have you heard about programming? Wink, wink. That will never be automated. Turns out I was a little bit naive, and I think many of us were. And reality has turned out to be a little bit more like this. So this is the young boy now. First thing you notice is that he hasn't aged very well. But the second thing that you notice is that he's constantly driving his truck with no fear of ChatGPT or large language models, and in fact, making fun of them. And if you don't understand this joke, you have some homework, because this is an AI conference. So the moral of the story is that sometimes things progress in unexpected directions, and there's been tremendous progress, as everybody knows here. In fact, 2023 is the year of mainstream AI. And this means basically that the number of problems that you can solve with AI is greater than it ever was, but also the value that AI provides is greater than it ever was. So how does this affect companies like us doing consulting? Well, everybody's talking about AI, right? So there's a lot of opportunities. Then times have changed. Project that we did 2 years ago that took 6 months, now can be done in weeks. And that's okay, we adapt, because we can do things now that were impossible just a few years ago. And then it highlights the importance of continuous learning. Basically, doing consulting, you need to be a really good generalist, and you need to keep track of the state of the art, because you need to learn about every development in a field to understand whether you can use that to give a better service to a client. So doing consulting, you are never in your comfort zone. And in Trial Labs, we never are. Trial Labs is an AI consulting company born here in Montevideo 13 years ago. That makes us the first, if not one of the first companies born here, but tackling an international market, mostly focused on the US. We have a team of about 70 members that's international. Most of us live here, but we have some people living in Europe and other countries in Latin America, so we are very remote friendly. And what do we do? We build custom AI solutions. And another way to put this is that we solve practical problems and we transform the latest AI developments and tools into actual value for companies and institutions. And in all these years, we've worked with amazing clients, some of which we are listing here. And there's other Fortune 500 companies, which unfortunately we cannot list. But these companies have been great for the development of our company. So how do these custom AI solutions look like? Well, they're very varied, so I just gonna give you some samples. And I'm not gonna go into the details of all, but as you see here, from real-time early white file alerting to a lot of forecasting, edge devices, and ML ops, which is like operationalizing machine learning at scale. Because the engineering aspects of machine learning deployments in the industry are sometimes a lot more important than which model you use. We also are very much fans of open source and have several open source projects, the most notable of which are Norfer, which is an object tracking library. If you are into video analytics, check it out. It's very widely used in the community. And we are well aware, because we've been doing this for years, that in data science, 80% of the work is data preparation, and 20% is basically complaining about data preparation. So we got you covered. We are partnering with Google, and we have to thank people from Google that are coming from Zurich. We are developing Temporium, which is a library that will make your life a lot easier when dealing with data preparation for time series forecasting. But it's not all about AI for us. We also care about the community. We partner with organizations like Redalco and Mimochi and donate to different causes to make a positive impact. And we also partner with Techi por el Día, and we inspire young girls to pursue careers in technology by doing talks that highlight the industry's diversity and inclusion. And we think these values are actually essential for success. So this is a photo of our team. It's a wonderful team, some of which are here. So it's very diverse team. It's multidisciplinary team, so we have engineers, and it started with engineers, but then we expanded. We have economists, we have people from biology, we have people from math, we have people from physics. So no matter where you come from, there is a place for you, and we have a wonderful training program that will basically compensate whatever skill you're lacking. So don't be scared, even if we sometimes look a little bit intimidating. There's always a place for you. So now time for some final announcements. So we have a technical blog. We post a lot of technical content, so make sure to check it out. Another thing is that we know how fast AI is moving lately, so we got you covered in that. We have, if you follow hashtag This Week in AI by Trial Labs in Twitter and LinkedIn, we curate the most relevant news every week. So the excuse of, hi, sorry boss, I spent half my week trying to catch up with the progress of AI doesn't work anymore. And then we also promote fitness lifestyle, so come squat with us to our booth. You have 30 seconds to make as many squats as you can, but you have to do them right, not like in this video. And hold on to your papers, because if you happen to be the winner of our giveaway, you're gonna be owning a brand new iPad Air. So it's another incentive to participate. And last but not least, we are actually organizing a code camp on forecasting with the folks from Google that are here from Zurich. So it's going to be here in this auditorium at 5:30. It was supposed to be at 5:30. Now I think it's going to be a little bit later than that. But we encourage you to stay. It's going to be great. And actually, coming from the industry, I know everybody here loves large language models and graph neural networks. But in the industry, like 70% of the cases that actually move the business needle all have to do with forecasting. So it's a very nice opportunity to learn from some of the best. So with this, if you are interested in learning more or you'd like to work with us, please contact us here. Thank you.
Thank you very much, Alan.
Do we have time for questions, or?
Does anybody have a question from the audience quickly while you set up, please?
Don't be scared. Okay, I'll stay around for the code camp, so.
Yes. So which room is the code camp?
It's right here. It's on this auditorium.
Perfect.
So you just have to stay.
Excellent.
Hola.
All right, so following up, we have Camila Palomeque and Gonzalo Herrera. Together, they lead the data science team in Quanam that works on projects of various topics such as NLP, time series analysis for sales, fraud detection and prevention, and neural networks for product recommendations. So Camila has a degree in economics and a master's in data science, and she is a data science and big data consultant with more than 4 years of experience working in the area for Quanam. And Gonzalo is a computer scientist who's doing a master's in computer science as well, with a focus on artificial intelligence and natural language processing. He works on data science and big data for Quanam with 7 years of experience. Please welcome Gonzalo and Camila.
Well, thanks everyone. Hello. So, who are we at Quanam? Okay. So, Quanam is a company with more than 44 years of experience, and we have more than 400 consultants in 7. Okay. In 7 offices spread throughout America. So, okay. We have more than 600 clients and projects in more than 25 countries. In particular, the Uruguayan branch has about 200 people, 80 of which are working in the data and analytics department. This is just a map showing different countries in which we have projects and people working for us. Well, the data analytics department has different projects in many areas, in particular, some of which are data warehousing, big data, financial analysis, insight visualization and reporting, and of course, data science and AI modeling. In the data science and AI group, which we co-lead, we have many projects solving different tasks, including client clustering and ranking, churn prediction, recommendation for entertainment and products for customers, sales predictions, including time series with long short-term memory neural networks, for example. We work with financial risk classification, and one of our main focuses is in the natural language processing, in particular in help desk support. There we developed more than one solution in which we take the tickets and using natural language processing, we classify them to go to the particular area that has to solve them, like in the AGESIC case, in fact, pretty similar, And the other thing we do is we make recommendation with automatic generation of the answer that you are expecting. Another project we have is called the QNLP, in which Camila is going to go more in depth.
Okay, can you hear me? Yes. Well, the QNLP actually is kind of a solution we envision working in LP a lot of years, so we did a solution which could be like building blocks in which we get different applications like topic extraction, text summarization, question answering, and all of that would be in a single product which then we could customize to the organization or the client. So, sorry, we did a test run in QNLP with the LOOK, which is short for Lay of Urgent Consideration, which was a package of laws in Uruguay, which was passed in 2020. And it has more than 500 articles in a variety of topics like health, economics, social structure, works. The law was actually passed in 2020, but in last year there was a referendum which allowed the citizens to vote on rejecting or not certain parts of the law. So it was a big thing in Uruguay, and it was part of the debate. So we decided to use that document, which was actually kind of a corpus of documents because it had more than 500 articles, to prove our product. So the first thing we envisioned was, we need to have something to order all that information. So we detect the chapters, the sub-chapters, and produce a summary of each article and put it all in a graph. So yeah, you could visualize the links between the entities, the entity recognition. Between chapters, you could search for a certain organization and then get to the bottom level and read a summary of the articles which refer to certain persons or, well, ministries in this case, or organizations in the government which were reformed. Then, well, the debate was mostly on Twitter, and we actually developed kind of a thermometer or something with a social media analysis in which we follow the tweets by day, which talk about the look. We follow the most prolific users. We polarize them again with graphs, and extract the topics, extract the distribution in the country, and started monitoring that, and sentiment analysis, of course, so we could see which topics were hot and in which different level. Then with the corpus of the text, we did embedding and clustering, so we could actually segment and find different groups of articles associated, or in case of using actually the documents, it would be to auto-generate a catalog. It was our hope when applied to the enterprise. And finally, the most fun part to develop, and which we are most proud of, it's we wanted to do a query, but specifically on the look. So we generate a corpus of news talking about the look, news articles from Uruguay. And from that, when a user asks a question about it, we used the Elasticsearch engine to get the 3 top news related to that question, and then use those articles as an input in a fine-tuned question answering model, which was based on Beto, Spanish Squad 2.0, and BERT-based multilingual, which then the output was, of course, the answer and the source of that answer, so you could check it. And as this was hosted, it was made public, available, and it was hosted in our servers, we then started thinking how to optimize a bit the times. So how to know when a question was valid, because it was a very sensitive topic as well. So we could say the users could say, oh, well, this question is okay, and perhaps it was not. So we put a verification box and then did analytic on that so that we could like certify the questions. And then after that, yeah, we made it to our database, so we don't have to go to the model every time someone asks a repeat question, of course. Well, other initiatives in Quanam we are currently forming an investigation team which tracks news on AIs and tries to see how we could translate that into actual innovation and things for our customers. Kind of this case, but well, following up. Then we have a yearly seminar, business seminars for decision takers in the industry to share knowledge on AI, and a podcast which currently has 2 seasons, and the season 3 is coming up, and the blog. And finally, I would like to tell you just a little bit about last year was the World Cup. So we did a machine learning competition in Uruguayan, Penca, to predict the results of the matches and the rankings in the World Cup. The team that won, actually, with the models, said to us that if they had trusted their model in a human penca in Montevideo, they would have come second. So, well, there's kind of our baseline. But now we encourage you. We are getting the second edition with the American Cup, or the Copa America. We encourage you to participate and to show to your friends who watches all the games that we could actually, beat their well-informed predictions via data. So thank you very much.
Thank you very much. Enzo, you wanna? Just a little, is there any question? Or, yeah, we're a bit tight on time, so we're gonna move ahead and have a very short announcement.
Don't worry, we could talk.
Yeah, you're in the
Thank you.
Yeah. Awesome. Just a little announcement before the practicals.
Well, we are now having the practicals. So here are the rooms. Here in the main auditorium, as Alan was saying, will be the hands-on forecasting guide. GNNs and NLP transformer practicals are going to be in the Faculty of Engineering, where yesterday we went. What? There's an error?
It's not 314, it's 402.
Okay, good. We'll correct it. Here, this is a bit dynamic, so, okay, I don't have, okay, I'm not with, okay, what's the name? 402. Okay, GNNs is in 402, okay? I cannot edit it because I'm not logged in with the right account. Finally, ILDA workshop will be in C11 here in this building in the first floor, right? Nacho? First floor, C11. The last one, yeah. ILDA, yes. Okay, C11 minus, yeah, perfect. Okay, 402 GNNs. Sorry about that. Good. And tomorrow, and I remember that at 8, we have the how to write a great paper session here, okay? And yesterday, and tomorrow, sorry, 8:30, please try to be here in time, because today we had to arrive, like to start later because people was arriving. So please, so that we can keep the schedule, try to be here in time. Thank you very much.